Poonam ji, good morning. I'm sorry for disturbing you in the morning, but I was wondering if Professor Jairam Chenglur may like to test his link. I don't see him online yet. I don't have his number. Hello? Hey.
Sasi,
एक मिनट मैडम, आवाज साफ नहीं आ रही है, मैं अभी दूसरे नंबर से कॉल करता हूँ। हाँ जी सर,
दिख रहा है?
जी सर जी, एक बार आप मूव करा करके भी देख लीजिए, स्लाइड रन फुल स्क्रीन मोड में करके। हाँ, और अब ठीक करके एक बार आप देख लीजिए सर।
ओके, और बात ठीक है, इतने से हमारा काम हो जाएगा।
हाँ हाँ जी 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 जी,
ठीक है भैया, थैंक यू।
थैंक यू सर। इसको थोड़ा सा नीचे करोगे सर? Professor Jairam, good morning and welcome.
Good morning.
You may like to test your presentation in case you want to make sure.
I can share the screen.
Yeah, please.
Yeah.
Yeah, I think it came.
Yeah. Just 1 minute. Yeah. So it has come.
Yes.
And it's in slideshow mode, right?
Not yet. Yes, it is. Yes. Full screen mode is not there, but slideshow mode
Yeah.
seems it is there. Yeah, it's okay now.
Okay, good.
Yeah, thank you, sir.
Thank you.
So, good morning all. Good morning all. Welcome back again on the fourth day of the workshop that is dedicated for existing Indian observational facilities and measure results. And this session was supposed to be chaired by Dr. K.K. Yadav from BARC, but he called and informed that due to some commitments and assignments which are kind of unavoidable related to Mace and all, he will not be available. So I'll be moderating the session here. I welcome the participants of this first pre-lunch session, which is dedicated again for observational facilities. And in this session, the very first talk is for GMRT and the GMRT and measure results. And this talk would be presented by our senior astronomer, Professor Jairam Chengalur. So I request Professor Chengalur to please deliver the talk. And the talk is divided like 50 minutes for presentation and last 10 minutes for question and answer. So Professor Chengalur, please. Hello.
Thank you. Good morning. I hope you can hear me.
Yes, very well, sir.
Yeah, okay, good. Yeah, so I'd like to thank the organizers for inviting me to give this talk. It's a pleasure to be here with you today. And as we just heard, I've been asked to speak about GMRT and major results, but I should give a small caveat over there. I will focus mainly on recent results, that is, results obtained after the upgrade of the telescope, which the upgrade itself, I'll tell you some things about. There's some more caveats that I need to give about the results, which I will present. And, I'll try and remember to give those caveats when we reach that part. So let me start with a very broad overview. Looking at the participants, I appreciate that many of you may not be familiar with radio astronomy at all. So I thought maybe I'll just give a broad introduction. The GMRT is an array of antennas, and it operates in two major modes. We could call this the imaging mode and the beamforming mode. And, regardless of which of these two modes it's working in, the sensitivity for continuum sources, that is sources which emit radiation over a wide range of frequencies, will increase with the bandwidth. And that is, something which will be important for us as we go along. The imaging mode works via a technique called aperture synthesis. And again, if you're not familiar with aperture synthesis, the two takeaways which I'd like you to sort of, the two things I'd like you to keep in mind about this imaging mode is that the angular resolution that you will get in your images depends on the largest separation between antennas, which is also called a baseline. So the more distant the two antennas, the better the angular resolution that you'll get. And similarly, among other things, the fidelity of your image, that is the accuracy with which it represents the sky, will depend on the baseline distribution, that is the distribution of antenna separations. The more uniform the baseline distribution, the better the fidelity. So just excuse me a moment. Sorry about that. So the more uniform the baseline distribution, the better the fidelity. And again, this is something which we'll come back to as we go along. In the beam-formed mode, you don't form images, but instead you can use it to do very high resolution of unresolved sources. So for example, pulsars. If you want to study the time properties, with very high time resolution, this is the mode that you would use. And in the beamformed mode, there are actually two different modes, one of which is the phased array mode, in which you add up the voltages of the antennas. That gives you a very, very small field of view, but with quite high sensitivity. And the other is the incoherent array mode, in which you add up the powers from the antennas and not the voltages. And that gives you a much larger field of view, but low sensitivity. So if you're doing studies of a pulsar whose location in the sky, you would use the phased array mode because you know exactly where to point. Whereas if you're hunting for a source whose location you're not that sure about, you would use the incoherent array mode. Now, if you want to look at it in a little bit more detail, the array consists of 30 antennas, each of which is 45 meters in diameter, and it operates at meter and centimeter wavelengths. It's been built and operated by NCR-AT-IFR. And the antennas themselves were built to a novel and cost-effective antenna design. Professor Govind Swarup, who came up with this design and who led the construction of this telescope, calls it the stretched mesh attached to rope trusses, or the SMART design. So basically you have very little backup structure, and instead the parabolic shape of the reflecting surface is obtained by attaching the wire mesh, which is the reflecting surface, to wire ropes, which are tensed appropriately to give them the parabolic, to give the whole antenna reflector the parabolic shape. The antennas themselves are spread over an area of about 25 kilometers, and they're connected to the central electronics building via optic fiber. And this also was a major innovation at the time when the telescope was conceived and built, that is in the 80s to 90s. Because at that time, optical fiber was not much used at all, definitely not in this country. And the GMRT was the first, radio telescope to actually use optical fiber for signal transport. The facility, the GMRT was commissioned as a national facility by Shri Ratan Tata on October 4th, 2001. So, coming on 20 years now. From the time it was commissioned, the GMRT operates in what we call the open skies mode. That is, any astronomer anywhere in the world could apply for time to observe with the telescope. Time allocation is done by a peer review, which is overseen by an independent time allocation committee called the GTAC, for the GMRT Time Allocation Committee. And the GMRT over the years has been used by astronomers from over 40 countries. With about half the time being used by astronomers from India. And all of the interferometric data that has been taken with this telescope from the time of commissioning has been archived, and it's freely available for download on the web. For people who write a fresh proposal, there's an 18th month proprietary period for which the data is not available to other people. But at the end of that, the data becomes automatically public. And there's quite a lot of research which also goes on with archival data. If you look at where the antenna is located, it's located about 70 kilometers north of Pune and about 160 kilometers east of Mumbai. The configuration of the antennas is another interesting detail of this array. There are 12 dishes in what we call a central compact array or a central square. Antennas are spread along Y-shaped arms. And so this shows you that configuration. Here are the central square antennas shown as a dot, and the antenna kind of symbols to show you the remaining antennas which are spread in the Y arms. And the reason for doing this is that when you, this kind of hybrid configuration allows you to get a good sampling of both small and large antenna separations. The antennas in the central square give you a good sampling of short baselines, and the antennas in the arms give you a good sampling of long baselines. And I'm just showing that to you over here, showing you the baseline distribution that you would get if you track the source from rise to set. And when you track the source from rise to set, the relative orientation of the antennas with respect to the source changes. So the effective baseline changes. And the panel on the left shows you the baseline coverage that you would get if you used only the arm antennas. And so it's on scales of 25 kilometers. The panel on the right shows you the coverage that you get if you use only the central square antennas. And so it's about 1 kilometer. So you can see on both these scales, you get a reasonable distribution of baselines. And what that means is that you can simultaneously image both widespread diffuse emission, and that you would do using the baselines in the central square. And you could also use the same data, only this time you use the data from the arm antennas to zoom in to make high resolution images of bright compact features. And I'm showing you an example over here, where this panel over here, the contours show you the brightness of acetaldehyde, of the emission from the acetaldehyde molecule towards Sagittarius B2. And you can see this has been made with the central square antennas. It shows you the wide spread emission of this molecule, the wide distribution of this molecule in this molecular cloud. But you could also use the data from the arm antennas to zoom in on some particular region and see where exactly is the molecular emission concentrated over there. And you can see that it's concentrated along this ridge, which happens to coincide with some shocks which you expect happening in this cloud. So this hybrid configuration, therefore, was again another interesting parameter of the GMRT, and it was once again, I would say pioneered by the GMRT. It was the first array to have this kind of hybrid configuration, but these are now getting more and more common in newer arrays across the world. So let me talk now about the classic GMRT. The classic GMRT offered an instantaneous bandwidth of 32 megahertz, which was originally split into two 16 megahertz subbands. So at any one time, you could only observe 16 megahertz of bandwidth. It operated over a limited number of frequency bands between 130 and 1450 megahertz. So I've shown you a picture over here of the, which shows you the focus of the antenna. And at the focus, there is a rotating turret on which feeds which work at different frequencies are mounted. And so depending on which frequency you want to observe, you just rotate the corresponding what we call a feed antenna. You just rotate that feed antenna to point towards the dish, and then it's in focus and you receive those frequencies. And some of these feeds had actually quite narrow bandwidth. The narrowest bandwidth feed had a bandwidth only of about 20 megahertz. The signal transport system that was used was based on the superheterodyne system. And again, you don't need to know, don't worry if you're not familiar with the details of it. The point is that in this kind of design, you need quite a lot of electronics at the antenna base. I beg your pardon. So if you look at all of these blocks over here, all of these blocks are situated in the antenna base. And so in the superheterodyne kind of signal transport system, you have to build and maintain a number of subsystems at each and every antenna. Finally, the processing of the signal in the central electronics building was done using a digital correlator and a digital beamformer, both of which were implemented in the hardware. They were state of the art when they were built, but since they were hardware units, their functionality was limited to whatever the designer of the board sort of built in at the time when this unit was built. So the GMRT has recently been upgraded, and I'm actually going to walk through quite a lot of the upgrade, but here is just, it's the big picture of what the upgrade consisted of. The new broadband feeds and receivers, which provide nearly seamless frequency coverage between 120 and 1450 megahertz. There are gaps in regions where radio frequency interference is strong. And so this figure over here is sort of showing you a comparison of the classic GMRT, and that is the small blue columns over here. That shows you the frequency coverage of the old classic GMRT, and the numbers that you see on top of it are what we would call the fractional bandwidth that was observable at any given time. That is delta nu over nu, when nu is the center frequency of that band. So you can see that the fractional bandwidths were quite small. The upgraded GMRT is shown over here in these sort of pinkish rectangles, and the frequency coverage you can see is significantly improved. And the numbers on top show you the fractional bandwidth that the new system offers, and you can see that it is a significant increase in fractional bandwidth compared to what one had earlier. There's also the broadband, the signal fiber, the signal transport system has been completely overhauled, and now it is much more straightforward, using techniques which were available now but were not available earlier, and I'll talk a little bit about those. So, but what it means is that there's far less equipment at the antenna shell, and you also have a higher dynamic range to the system, that it doesn't saturate, even if in the presence of reasonably strong interference from outside. The digital processing is now done in a new hybrid processor, which consists of FPGA boards as well as GPU. And again, I'll sort of say a little bit more about it later. But the thing we need to note now is that the maximum instantaneous bandwidth is now 400 megahertz, whereas earlier it was 32 megahertz. There's a new server system, a new telescope control and monitor system, and there have also been updates to electrical and mechanical systems, as well as the proposal and archival system. So what is the impact of all of this on observations? The first is that the continuum sensitivity, that is the sensitivity to sources which emit radiation over a wide range of frequencies, improves because of the increasing bandwidth. And that's what this figure over here is showing you. On the x-axis, we have the frequency. On the y-axis, you have some measure of the sensitivity, and the different colored points are for different telescopes around the world. The blue points that we have over here are for the GMRT prior to its upgrade, and the pink points that you have are for the GMRT after its upgrade. And the way this diagram works is that the lower the point, the better the sensitivity. These stars over here are the expected sensitivity for a telescope called the SKA Phase 1, which you will hear more about from Yashwant tomorrow. It's a telescope which will be built over the next few years, and so at the moment it's it doesn't exist. So you can see that at all of its frequencies of operations, the upgraded GMRT has a sensitivity which is comparable or better than all other existing telescopes. The other thing that you get will sort of impact on the observations is that you get an improved baseline coverage. I've written UV coverage, but I mean basically is the baseline coverage for continuum observations via a technique called bandwidth synthesis, and I'm showing that to you over here. So basically, separation that we are interested in is not the antenna separation in meters, but the antenna separation in units of wavelengths. And so if I'm observing over a wide range of wavelengths, I actually am observing effectively a number of different antenna separations. So the wider the bandwidth you have, the more densely you're going to sample the baseline space. So over here in this diagram, the red points show you what the old 32 megahertz bandwidth gave you, whereas the purple points show you what you get with this increase GMRT. So you can see that the baseline coverage, the effective baseline coverage actually improves significantly. And so that again would translate into improved image fidelity. And then now, because you've got a wider band that you're able to observe, even for spectral lines, that makes a difference, even though the sensitivity for spectral line observations doesn't improve. What does improve is the redshift coverage, that is the range of redshifts over you could observe H1 and other 21 centimeter lines. And I'm showing that to you over here, that I'm again just showing you the different bands that we have at the GMRT. And on the top, I've shown you the redshift range that each band corresponds to for H1 21 centimeter emission. And on the vertical axis, I've also shown you, and that's what these purple lines are indicating, the velocity resolution that you would get with the correlator at each of these bands. So you can see that the velocity coverage is the velocity resolution also that you get is quite good, because the correlator now offers you up to 16,000 channels. And so that enables a great deal of spectral line science, which was not possible earlier. And then finally, because you now have these large fractional bandwidths, you can measure many things with a single observation using just one band. So for example, you can measure the continuum spectrum, you could measure quantities like the dispersion measure, etc., with observations just in a single band, which again is very useful because A, it is faster typically, and B, it's also subject to much less systematics than trying to do observations in separate small bands. All right, so now let me move on to telling you some details about the GMRT upgrade. I won't get into too many technical details, but I'll give you a broad brush overview of what, of at least some of the upgraded systems. So let me start with the feeds and receivers. As I said, we now have new broadband feeds, and they operate in these particular bands, which we call band 2, band 3, band 4, and band 5, which operate in 120 to 240 megahertz, 250 to 500 megahertz, 550 to 850 megahertz, and 1000 to 1450 megahertz. Band the feed itself was not changed. The old feed did work from 1000 to 1450 megahertz, so it was retained. But the electronics behind it was upgraded. And I'm showing you over here the band 4 feed, which consists of what is called a cone dipole. In addition, the amplifiers which sit just behind this feed antenna, which are called low noise amplifiers, have all been changed. We have now, obviously, we need broadband amplifiers. They also have high dynamic range and good noise properties. There's also sitting at of the antenna, after this low noise amplifier, we have a second stage of amplification, which is common to all of the feeds. So each feed has its own low noise amplifier or LNA, but the second stage is common to all of them, and that's called a common box. And that now we have a new high dynamic range common box with additional monitoring capabilities. There are also better filters for radio frequency interference rejection. Now, the optical fiber signal transport has also been completely revamped. We have a new signal transport system. And what it does is it does broadband 0 to 2 gigahertz transport of analog radio frequency over fiber. So the amplified radio frequency signal is simply just sent over the fiber to the central electronics building. That gives us improved, the new system gives us improved dynamic range as well as headroom. And also, and this is something I'd mentioned earlier, it greatly reduces the electronics that you have to maintain at the antenna base. And one of the interesting things about this optical fiber transport system is that it actually uses multiple wavelengths to transport signals. So this is called dense wavelength division multiplexing. And what that allowed us to do is to transport the signal from the legacy system as well as the upgraded system. So, that ensured, among various other things which were done, that the upgrade could proceed without disturbing the legacy system. This is just an example of one of the fiber racks. So here is, the new signal transport block diagram, and you can see it's significantly simpler than the earlier one. You have the front-end electronics sitting at the focus of the antenna. Then you have the fiber optic and transmitter, which sits at the antenna base of optical fiber signal, taking it to the central electronics building, where it's converted again from optical to electrical. And then we have what's called an analog backend, which does some conditioning of the signal before digitizing. And after that, the signal goes into the digital backend. So the signals received in the central electronics building are basically conditioned, as I mentioned, before being digitized. And what the steps that it involves is down conversion of the radio frequency to baseband for digitization. There's also a variable gain stage for power equalization. You can select bandwidths of 100, 200, or 400 megahertz. If you want finer bandwidths, that can be selected in the digital system. And it also has integrated power level monitoring for troubleshooting. You'll see over here, there's something called an LO master over here. That's basically the local oscillator, which is part of the time and frequency standard at the observatory. And the time and frequency standard at the observatory has also been upgraded. Earlier, it was rubidium based, whereas now there is a hydrogen laser. And that, again, makes a difference for various things, particularly pulsar observations and VLBI. And you'll probably hear something about this later today afternoon from Bhalchandra Joshi. So here's a quick look at the digital backend. As I mentioned earlier, there's a hybrid digital correlator, which is a combination of FPGA boards and GPU. And the design is what's called an FX design. That is, the voltage coming from the antennas is Fourier transformed first to give you spectral information. And then there's a channel by channel multiply of all antenna pairs done to measure what is called the visibility. And so the digitization of the data and something that you need to pre-process, which is called delay tracking, is done in the FPGA, whereas the FFT and this multiply and accumulate, that is the X, is done in the GPUs. And the CPU of the host machine does some housekeeping like data handling and time slicing, etc. So the digital backend, the correlator can handle 32 antennas and it can accept two streams, two data streams per antenna, and that's typically coming from the two polarizations of the feed. It could be two linear polarizations or two circular polarizations. A maximum bandwidth of 400 megahertz, a maximum number of spectral channels of 16,000, and it provides 4 products per baseline up to, which means that these are the 4 Stokes products that you would need if you're doing polarimetry, and integration times between 0.6 to 16 seconds. That is, by integration time is meant over here the rate at which the data is output to your system. So it can be output once every 0.6 seconds to all the way up to 16 seconds. The digital backend also has a beamformer, and it can produce up to a total of 4 beams at one time. These could be either coherent or incoherent beams or phased array beams, which I'd spoken about earlier, that you add the voltages or you add the powers. And the antennas that you want to fold into any given beam can be chosen independently. And that again is very powerful flexibility, which means that I could put half of my antennas in one beam and the other half in the other beam. And I could put different frequencies in these two sets of antennas. And therefore I would be doing 2 frequency observations simultaneously. The beam can produce either total intensity or all 4 Stokes parameters, and the shortest integration time you can get out is about 20.5 microseconds, because this is the mode that you want when you're studying pulsars and other fast time varying phenomena. And for up to 2 of these beams, you could actually send out the Nyquist sampled voltage data, and that when you do that, it allows you to do, more sophisticated signal processing on the signal. And an example of that is being shown over here, which is called coherent de-dispersion. And so, and I'll say something about this when I talk about the science, that, when a pulsar signal propagates through the interstellar medium, it gets smeared out. And when it gets smeared out, it you can see that you won't be able to time it very accurately. You won't know exactly when it arrives. Your sensitivity also will reduce. And you have to correct for that smearing in some way. And this upper panel shows you the traditional way of correcting it. And when you correct it in this traditional way, this is what 2 consecutive pulses look like. Whereas if you're able to do this other processing for which you need the Nyquist sample data, which is called coherent de-dispersion, this is what those pulses would look like. So you can see that when you're able to do coherent de-dispersion, you can actually much more accurately correct for the dispersion in the interstellar medium. You get much sharper pulses, and that makes a big difference when you're trying to do pulsar timing and other such things. Okay, and the last thing I wanted to say about the digital backend is that it also allows you the facility to filter interference in real time. And that is, in the Nyquist sample data, outliers are sampled and filtered in real time. And, I'm just showing you examples over here. We need not get into the details of it, but the basic point is that the red signal is what you get without this filtering out of impulsive external interference, and the blue signal is what you get after you've filtered it out in real time. And therefore, here's an example of the difference that it makes, for example, to pulsar observations. The left is what you get with the unfiltered data. The left, Thank you. Sorry about that. The left is what you get with unfiltered data, and the right is what you would get with filtered data. And you can see there's a very significant increase in the signal to noise ratio. Then, as I mentioned, there have also been upgrades to many other systems in the antennas. And I'll just, the one thing I'll walk through is the servo system, where there's been a lot of, the entire system has been replaced. The old system used brushed motors, which are now obsolete and difficult to maintain. That has been replaced with a modern brushless system. The corresponding drives and controllers also needed to be changed. The interlocks earlier were relay-based, which again are obsolete and not that reliable, and they've now been replaced by solid-state interlocks. The old control computer was an 8086-based board that has been replaced by a PC104 system. And the final upgrade, which is going on right now, is a replacement of the feed positioning system. You remember I said that whichever frequency you want to observe, you need to rotate that feed into the focus. Earlier, there was an open loop system based on an incremental encoder that is now being replaced with a closed loop system with an absolute encoder. And that has a kind of multiplier effect on many aspects of telescope operation. The control and monitor system has also been upgraded. So the old system, which served us very well, was control line control, sort of terminal based and commands which had to be issued on the keyboard. The new system is much different. It's a role-based GUI system with authentication and authorization. It supports up to 5 observation arrays and 1 array for engineering. That is, you could run 5 observations at one time using subarrays of the total array, and also have one array which the engineers are using for testing and debugging. It has automated observing schedule execution and scripting. It has auto alarm exception handling. It archives the data, and it has an automatic fault sheet generator. And also it provides a web-based facility for absentee observing. And I should mention over here, and you'll hear more about this later tomorrow, that the same system that is being deployed at the GMRT is also a prototype for the SK Telescope Manager. And finally, there have been, many other upgrades which I won't talk about to the electrical, civil, and other infrastructure. The one picture that I'm showing you is of a new high lift platform, 2 of which were obtained, which greatly eased the bottleneck in accessing the equipment at the focus, which was important at the time when we were working on the focus and replacing the feeds and all of that. The entire reflecting surface on 2 antennas has been replaced, which has made a measurable difference to their sensitivity. The new UPS systems in the antenna shells, this may not sound like much, but what needs to be appreciated is that UPS systems switch currents, and so therefore they produce a large amount of interference, and we can't just put them in our antennas. We need to shield them thoroughly, and it took a lot of work with the vendor to get systems which are shielded to acceptable limits. And there have also been upgrades to the proposal submission and archival system. And if we talk about how the upgrade itself was implemented, as I mentioned, it was ensured that observations could continue throughout the upgrade. There was an incremental deployment of upgraded capabilities with a phased release to the user community. And the final formal launch of the system happened in March 2019. But prior to that, already segments which were ready had been released for use. So I'll now, I should mention this. This is, as some of you would know, the GMRT was recently accorded the IEEE milestone status, and that is a great honor for us. It's only the 3rd such milestone status for work done in India. The earlier ones were the work on microwaves. done by Acharya J.C. Bose and the work done by Sir C.V. Raman leading to the Raman effect. And so, it is a real tribute to the vision of Govind Swarup and the team which built the GMRT, as well as the teams which have sort of kept it at the cutting edge of technology and upgraded it over the last few years. All right, so now let me move on to talking about science from the UGMRT. And as I mentioned, I will, talk only about science which has been done post the upgrade. And I will also, I've been asked to talk about major results. I certainly believe that the results that I will be talking about are important, but I haven't tried to make, trying to find the ones which are the most, important in some sense. And so was not the idea at all. What I have tried to do instead was to choose results across a spectrum of areas to give people a feeling for the different kinds of science that the GMRT could do. So let me just start with this, because I had said that there was a phased release of new capabilities, and that parts of the system were in use even before the formal release. And I'm showing you over here results from 2014 at a time when there were only 11 antennas which had been upgraded with this new band 3 feed. And what this new feed allowed was observations of hydrogen at a 2, which was not available earlier, and this kind of this hydrogen at high redshifts can be detected in absorption if there's a bright background radio continuum source, and if the column density of the gas is quite high, about 2 × 10⁻²⁰. So typically column densities of what are called damped Lyman alpha systems. And so shortly after there were a few antennas available at this redshift range, Nissim looked at a couple of absorbers using the system. And that was a very interesting experiment, because there weren't a great deal of H120. Actually, one could estimate the spin temperature accurately, and it was found that it has a low spin temperature, which was consistent with the anti-correlation that had earlier been seen between spin temperature and metallicity, because the metallicity of this gas also was high. The UGMRT's large bandwidth also allows good spectral resolution and across multiple radio recombination lines. So radio recombination lines, particularly the lines which are nearby in frequency, they carry essentially the same information. So if you can observe multiple of these radio recombination lines at one go, you can stack them together to improve the signal to noise ratio. So what's being shown over here is a stack of 7 carbon recombination lines with principal quantum numbers between 244 and 250. And now you have sufficient signal to noise ratio to allow high resolution spatial imaging of this carbon emission, and that's towards gas A. And if you compare it with you've got good velocity and spatial resolution, you could compare it with other tracers of the gas in that region. And when you do that, what it indicates is that these recombination lines, which come from carbon, are probably arising from gas which is in the envelopes of molecular clouds. And there's another very interesting set of observations which were done with the upgraded GMRT, and this is of stars. A small number of magnetic B stars produce highly circularly polarized radio pulses. And the pulse period typically corresponds to a rotation period. So it's understood that these pulses arise from, excuse me a moment. It's understood that these pulses arise from what is called electron cyclotron maser emission. That's basically from auroral rings near the magnetic poles, and that's what that cartoon figure is showing you. What's interesting about it is that it ends up being a probe of the magnetic field orientation, of the magneto-ionic plasma distribution, the rotation rate, and so on. So Barnali Das, Poonam Chandra, and their collaborators have been observing these stars with the GMRT for a while, and their observations have resulted in the discovery of the majority of such known sources. The UGMRT, because it has these broad bandwidths, it also allows you to study the variation of these pulses that you receive as a function of frequency, and that allows you to probe different distances from the star, because higher frequencies arise close to the star. I'm showing you, for example, over here, pulses which were observed towards a particular star, from a particular star, HD 13880, and it's a mixture of both GMRT and VLA observations. And what they've been able to show is, one, they are able to measure, put constraints on the plasma density. They also can tell from their observations that the plasma distribution actually deviates from, the simplest azimuthal symmetric distribution that you might assume. And because the received pulses are sort of in phase with the rotation, and they have observations spread over a long period of time, they actually can quite accurately measure the rotation period. And what they conclude is that either the adopted rotation period is slightly wrong, or it has evolved at a very, very small rate, at the average rate of about 0.025 seconds per year. Now moving on to talk about pulsars. And as I mentioned before, when the pulse from a pulsar goes through the interstellar medium, it gets dispersed, and that's what's being shown in this grayscale over here. We have frequency on the vertical axis, and what we could regard as time of arrival on the Earth on the horizontal axis. And so you can see that the high frequencies arrive first and the low frequencies arrive later. So if you were to just add up, the pulse at all of these frequencies, it would get smeared out. And what you need to do if you want to get an accurate measure of the intrinsic pulse is that you have to correct for this dispersion smear. The dispersion smear, of course, is interesting because it is a probe of the ionized ISM. And so people look at it for that reason, to understand the ionized interstellar medium. But if you are trying to do high precision pulsar timing, it's of nuisance value. High precision pulsar timing is important, and it's a growing importance now because of the possibility of detecting gravitational waves using them. So basically what you do, and you'll hear again more about this today afternoon, is that you look at coherent variations in the arrival times of different distant pulsars. And that is the only way to detect gravitational waves from supermassive black hole mergers. And there are a number of national and international consortia which are engaged in these timing experiments, including with the GMRT. So, dispersion measurements with the UGMRT are interesting because the wide bandwidth of UGMRT allows one to make accurate dispersion measurements with just a single band, and that's because the fractional bandwidths of the band are quite large. You can get accuracies of 1 part in 10 to the 3 parsecs per centimeter cubed. And if you split the array into multiple arrays and you do multi-band observations, it allows you to achieve still higher accuracies of 1 part in 10 to the 4 parsecs per centimeter cubed. And monitoring at DMs at these accuracies can detect very subtle changes of the gas along the line of sight. So for example, in this paper by Krishna Kumar et al., they show a very clear excess of the dispersion measure produced by a very local phenomena, by a coronal mass ejection from the sun, which is propagating towards the Earth and which happens to cross the line of sight to the pulsar. I'm now moving towards extragalactic objects, and the first thing I'd like to talk about is diffuse radio emission in clusters of galaxies. Diffuse radio emission in clusters, and there are a whole range of these things. They're called relics or halos or mini halos, depending on exactly what, on the morphology and the origin of this of the emission. And but all of them have this in common, that they're typically steep spectrum. That is, they're brightest at low radio frequencies and so best observed at low radio frequencies. They're believed to arise from reacceleration of relativistic electrons. So in case you have a population of relativistic electrons in the intercluster medium, which maybe have arisen from the lobes of a radio jet or a radio source or something like that, they could get reaccelerated either via turbulence in the intercluster medium or by shocks produced when two clusters merge. And so these low frequency relic emissions are very important probes to understand the evolution of galaxy clusters and the intercluster medium. So I'm showing you over here observations done with the upgraded GMRT of the relic in Abel 4038. The UGMRT observations firstly were not just sensitive enough to detect this relatively faint emission, but it also, because you have this large bandwidth, you're able to determine the spectral properties of the different regions in this relic using in-band observations. And what they find, Ruta Kalea and her collaborators, is that the spectra vary systematically across the relics. In some regions, you have spectral indices which are as steep as -3.7, and some regions are actually not well fit by a power law spectrum, but instead show spectral curvature. And looking in detail at the morphology and spectra of these different regions, what they conclude is that this relic is actually an adiabatically compressed cocoon of relativistic electrons, most probably from a past episode of activity of the brightest cluster galaxy in this cluster. You've, I think, already had a talk from Sri Harsh on fast radio bursts, but I'll still just give you a very brief introduction. They're bright, very highly dispersed radio pulses, where the dispersion measure that you see is significantly higher than what you would expect from the interstellar medium of our galaxy. And so what that indicates is that the source is extra-galactic, and this has been confirmed with a few sources for which secure redshifts have been obtained. The source of the bursts themselves are unknown, but it's already clear that they are unique probes of the intergalactic medium. And interestingly, some of these sources are known to repeat. So typically these sources are identified using telescopes with very wide field of view to maximize your chances of finding a burst. But the disadvantage is then you can't locate the source accurately. But if you have a repeating source, then you could try and follow it up with an interferometer, which have typically much smaller fields of view, and then try and locate, with high accuracy where the source comes from. And that's what Vishwesh Marthi and his collaborators did recently with the GMRT with this particular fast radio burst. So this burst was known to have a periodicity of its active cycle. And so the GMRT observations were scheduled to coincide with the active phase, expected active phase of the system. And even though the observations were only done in the active phase, they actually detect in one session only no bursts, at the other 12, as many as 12, and the third just three bursts. So it clearly shows that even in the active phase, there is a high degree of variability. And two of the bursts were bright enough to allow them to simultaneously image. The beamforming mode and the imaging mode of the telescope can be run simultaneously, and that's what was done. And so because two of the bursts were bright enough, you could actually image the sky and locate where this burst was to sub-arc second accuracy. This particular FRB's location was already known, but it's a very valuable proof of concept that you can do these things with the UGMRT. I'm now moving towards the last set of topics that I'd like to talk about, which is using the UGMRT to observe neutral hydrogen at high redshifts. Hydrogen in the post-reionization universe is typically found only in galaxies, and the 21 centimeter emission from a particular galaxy is very, very difficult to detect with existing radio telescopes at redshifts above 0.2. But on the other hand, if you take a radio telescope and you ask the question, what is the volume of space that I probe with a given observation, that is within a given field of view and the radio telescope, what is, how many galaxies are in there? It turns out typically there are a very large number of galaxies inside this field of view. And of course, the larger the bandwidth, the larger the volume, and therefore the larger the number of galaxies that you're simultaneously observing. And if you know, the location and the redshift of all of these galaxies, you can actually average the H1 emission from all of the galaxies simply by aligning the spectra and adding them. And so even though you haven't detected any galaxy individually, you are able to measure the average spectrum and therefore the average H1 content of the spectrum. So stacking requires one to know precisely the 3D position of all the galaxies to be stacked. That's 2 sky coordinates and a redshift coordinate. So typically you do these observations towards regions where there's already been a deep redshift survey done. So here is one search which was done by Purba Bera and others with the UGMRT using the EGS field. Apurva should be, I hope, submitting his thesis within a week or 10 days. So what he did was stacking spectra for 455 bright galaxies with blue magnitude brighter than -17 with a median redshift of about 0.34. And having done that, he makes a very clear detection of the average H1 content. And here again, the UGMRT makes a big difference because it's got a larger bandwidth, therefore it probes a larger volume, and therefore you get a larger number of galaxies. This is the first statistically significant measurement of the H1 content of star-forming galaxies above a redshift of 0.2, I beg your pardon. And, because in addition to the H1, you get the radio continuum, so to speak, for free. You can also make a radio continuum image. This is the one that Apurva has made. It's got an RMS noise of 2.5 microjanskis per beam, one of the deepest existing images of the sky at this frequency. And from this radio continuum image, you could also, for example, estimate the star formation rate. And if you know the gas content and the rate at which the gas is being consumed to form stars, you could compute the depletion time. That is the amount of time it will take for all of the gas to become stars. And it turns out that the gas depletion time that you compute is similar to galaxies in the local universe. So between about 0.4 and 0.34 and the local universe, there doesn't seem to be a whole lot of things happening. And now Aditya Chowdhury has pushed this to still higher redshifts, to a redshift of 1. He stacked 7,568 galaxies from the deep 2 redshift fields and makes a very clear signal detection of the stacked signal. And I should emphasize there's a very modest amount of telescope time, just 60 hours. And what he finds is that the galaxies are now beginning to look quite different. They are much more H1 rich than similar galaxies in the local universe. But nonetheless, they have very short depletion times. And the reason for that is that if you look at the star formation rate of galaxies, it actually evolves very sharply between 0 and 1. And the galaxies at a redshift of 1 are forming stars at a much, much faster rate than the local galaxies. And so even though they have more atomic gas, the gas depletion time is relatively short. And what this suggests is that the reason why you're seeing this decline in star formation between redshifts of 1 and the current epoch is because the gas reservoir of galaxies is getting sort of consumed, depleted. And the last thing I'd like to talk about is searches for H1 emission from the large-scale structure in the universe. So the H1 emission from galaxies in the large-scale structures has a very characteristic power spectrum, and that you could then try and search for using interferometers like the GMRT. And again, because you have a large bandwidth with the UGMRT, it allows you to simultaneously probe a very large redshift range. And so Chakraborty and his collaborators did that recently with the UGMRT, and they have provided what are the first constraints on the power spectrum of the H1 distribution in the large scale structure between redshifts of about 2 and 3.5. So I think that's all the science I had wanted to run through. I appreciate that it might have sort of been quite a lot to digest because we covered a large range of topics in a short period of time, but I do hope it gave you a sense for all the things that this upgraded telescope can do. Thank you.
Thank you very much, Professor Chengalur, for your in-depth talk about history of GMRT and how it evolved, and when we went to UGMRT in its full bloom back in 2019, then the kind of results we obtained all the way from galactic to extra-galactic objects are kind of milestone. And with this new real international facility, GMRT, where globally more than 40 countries are now using, and with the IEEE recognition, it is definitely asset for all of us. And we are moving with this UGMRT, and with coming SK, definitely we will be in real multi-messenger era with other multi-band facilities coming up. So now it's time for questions. We have time for a couple of questions. So please raise hands if you have questions, audience. Am I audible?
I can hear you.
Yeah, yeah. So audience.
Very nice talk, Jairam. Absolutely brilliant. Covered everything right from the engineering aspects to the science aspects, very fluid. Just wanted to ask you that, I mean, of course, it's very nice to see that the upgraded GMRE is functioning so well, and then already seeing a good number of results. But can you just throw light on what could be the areas in which we could see some very significant science results in the next few years with the upgrade GMRT?
Yeah, yeah, thank you, Anupuni. I think actually, I feel that pretty much all the areas I talked about, you would expect, I think we have just begun to scratch the surface in all of these areas. And I would expect in all of them, we will continue to see, for quite some time, very interesting results coming out. I mean, some of these areas are basically where we are building up on past strengths, where, we've been doing this sort of thing before, but now we are able to do it better with higher sensitivity and so on. But perhaps in time domain astronomy, and particularly if we sort of, upgrade our instrumentation a little bit more to be more capable, of wider fields of view and higher time, where along with high time resolution, I would imagine that it would, that is a new, I mean, it's a new frontier is what I guess that's what I'm trying to say. I expect we'll see very interesting stuff in all of this. And, like in many other wavelengths, time domain astronomy is a sort of a new frontier for all of us.
Yeah, thank you, Jairam. And also, is there anything which would, I mean, as a next step, you'll be looking at the upgrade apart from the back-end instrumentation, but any noise cancellation or anything, any advances in that direction?
Yeah, so there are actually a number of, sort of incremental things being done with just the signal processing. I mean, I'm saying incremental in the sense that they're not actually involving large amounts of new equipment to be put in, but because you now have a more flexible system, you can try and build in more functionality about it. So certainly some of that is happening. There's also a sort of preliminary exploration going on as to whether we can greatly expand the capabilities of the GMRT, something which has been tentatively called the expanded GMRT, where various options like adding some more antennas or adding, wide field of view feeds, etc., are being explored. And, that is trying to see what could be a possible next step after the upgraded GMRT.
Yeah, thank you. That's quite exciting. Thanks.
Any other question to Professor Changlur?
Yeah, hello. I'm Brijesh here. Yeah, Jairam. It's,
yeah, hi.
Yeah, very nice to hear all this GMRT upgradation. And this whenever there's a sudden demand in scheduling, I mean, so how do you handle? Do you handle through a team or? Yeah. So I just wanted to curious to know
a sudden demand for what?
Yeah, change in the schedule. Let's say very short time within a night or within 24 hours.
Yeah, yeah. So the way
there's a sudden change due to science or anything else, maintenance.
No, sorry, Bridge, could you please, I'm not sure I fully understood the question. Could you please just ask it again?
Yeah, actually, this is when you schedule the GMRT observation, it is already scheduled.
Yes.
But, suppose there is a demand, sudden demand.
Yes.
In changing that schedule due to very many reasons. Could be instrument, it could be maintenance, it could be science, it could be.
Yeah.
So how do you manage? Do you have a team, a separate team for that, or?
Yes, there is a separate scheduling team. There is, I mean, there's a person who sort of, who I think at the moment is Punam Chandra, who is in charge of drawing up the schedule for the whole cycle.
Okay.
And so, then, because we have different observations which have different constraints and so on and so forth. So right at the beginning of the cycle, to the best extent possible, an optimized schedule is drawn up. But typically the schedule also has gaps in it, and that we do partly by design, because gaps are needed for maintenance, etc. And gaps are also useful when you want to test, or when some new observation comes up, or when somebody's observation fails and you need makeup time. So then there is another team which is responsible for scheduling those kinds of requests. If you have what's called, some time of target of opportunity sort of event, that something's gone off and you need to look at it quickly. There are two ways of handling it. You could either submit a proposal right at the beginning of the cycle. So for example, you're looking at GRBs or something, and you know for sure that on the average, say 8 GRBs will go off, but you don't know exactly when or whatever, when would be the right time. So you write a proposal saying that I want to observe, objects of class X. I expect that there will be so many such events during this time. Therefore, I request so much time in these particular modes for it. And then when that event actually occurs, you just send a trigger saying that, okay, the event has occurred, I'd like to be scheduled as quickly as possible. And then this other team, which looks at the scheduling, which I think at the moment is led by Ishwar Chandra and Dharamveer Lal, takes a look at the schedule and tries to see where it can be fit in most efficiently. And of course, there could be phenomena which are completely unanticipated, in which case you could put in director's discretionary time request. And again, once it's granted, it's dealt with in the same way.
Yeah, thank you.
I
It's
hope
quite
that
elaborate
answers your question.
kind of planning. Thank you. Thank you, Jara.
Any other question? Any other question from audience for Professor Chengalur? If not, let's thank Professor Chengalur again. And with this, Professor Chengalur, please take the screen off.
Yes.
For your for the next speaker, please.
Yes.
Thank you very much. Yeah. So now it's time to listen to Professor Ramsagar ji as the next speaker, and he would be talking about observational facilities 2, and primarily about the 3.6 meter Devasthal optical telescope. So, Professor Ramsagar ji.
Yeah,
Yes. Let's go off.
I'm unable to share from here.
Oh, you are unable to share from here?
Just a minute.
Okay. Please try, sir, because it has already been unshared by Professor Chengalur. So.
Okay, that might have been the reason.
Well, yeah, you please again retry.
Okay.
We can see your screen, sir.
Okay, okay. Yeah, is it visible now?
Not at the moment. Only your screen is visible, having 4 PPT files, and you are probably, you need to click it, sir.
I did it.
No, sir, it has been selected but not really clicked. Please double click it.
Okay, okay. Okay, okay. Just a minute. Okay. It looks like I am not in.
No, sir, you are in, and your screen is visible to us. आप उसको अनक्लिक करके दोबारा से डबल क्लिक करिए.
Yeah, we can see your screen, sir. Yeah, please double click. Probably that should work.
Yeah, we can see your files, not the, you have not yet opened the PPT.
Yes, yes.
Yeah. Ramsar, can you see the PPT opened in your computer?
Yeah, it is open. That's why I'm worried.
Okay,
Should
can
I
you
close
unshare-
it?
No, can you unshare the screen
Yes.
again and then share the PPT screen? PPT when you
Okay.
get the PPT part.
Yeah.
Of your video also for the time being.
Yeah, now we can see that. Yes, your cursor is also seen.
Now, yeah, I can see the, everything.
Yeah, but then you are shared the another part of your desktop. So you should be
Okay.
sharing the either the entire desktop or the PPT file.
यहाँ से कर सकते हो. इसको load.
If there are problem, can you manage from there, Sasi?
You'll have to mail them your file.
I have mailed them already.
Okay.
I am in or not? Just a minute. It looks like I'm unable to do things from here.
Probably you have to unshare it, then you share it.
Okay.
Yeah,
हाँ सर, एक बार अनशेयर करके शेयर कर लीजिए, अनशेयर कर दीजिए एक बार.
You just unshare it, then you share.
Okay, just a minute. Looks like there are some problem.
Yeah.
Because either you share the entire desktop or you just share. You have just shared, yeah. You just unshare it, then share it.
Screen sharing has stopped as the share window is closed.
Yeah.
Okay.
Now you share it.
Maybe. Is it okay now?
So when you share it, it will show you various options of which screen you need to share or which window you want to share.
Right.
You please select the one in which you see the PowerPoint. वो एक बड़ी सी स्क्रीन आएगी जिसमें बहुत सारे ऑप्शन आपको रहेंगे, स्क्रीन 1, स्क्रीन 2 और विंडो एक्सप्लोरर, पावरपॉइंट. तो आप पावरपॉइंट को सिलेक्ट कर लीजिए तो हो जाएगा. Or else Shashi ji can run the slideshow from his computer.
Yeah, I think because I am able to see at my level, on my screen, but I am not able to. Yeah.
Right, there it is.
It's there now. You can see now.
He shared from here. यहाँ
Okay,
से हम
so
share कर रहे
have you
हैं.
shared or I have done that?
नहीं, we have done it.
Okay. Okay. So you just tell me so that I can start.
हाँ, आप अब ये आ गया है और जब भी आपको नेक्स्ट स्लाइड पे जाना हो तो आप बताएं, हम यहाँ से क्लिक कर देंगे सर.
Okay, just sorry. I mean, it looks like in the morning I tested, but something has happened in between. Okay.
जी. हाँ,
So-
no problem, sir. You can
Okay.
start now.
Yeah. So thank you. Good morning to all of you, and thank you very much for giving me this opportunity to talk about 3.6 meter Devasthal Optical Telescope in this workshop. So what I am going to do to cover a little bit about the historical background and site survey, what are the importance and what things we learned from there. And then I will discuss some of the results which has been published recently along with existing back-end instruments. And in fact, in this talk, the contribution which I am using here, it's from Brijesh Kumar, Amitesh Omar, Sasibhushan Pandey, and Saurav Sharma. And this picture, what you see, it's a 3.6 meter dot, and then other two telescopes which are part of the Devasthal Observatory. So it shows the location. Can we go to the next slide, please? Yeah. So this slide basically tells us a little bit about the historical background of the project. So if you look into when people started talking about, it was still under state government, UP State Observatory in 1976. And then Chief Minister, in fact, approved the project. And that gave the way to carry out detailed site survey, preliminary site survey, which was carried out between 80 to 90. And during that period also, DPR was prepared jointly with BARC, Bhabha Atomic Research Center, and UPSO, but the project got deferred. And these are some historical, detail. If I just summarize, in fact, during 1976 to, let us say, 2006, till, as you can say, till the formation of ARIES, basically this project was in site survey phase and various approval phase. And if I say so, it may not be exaggeration. In fact, that's the reason that this project triggered state government to transfer it to the government of India, because the money and whatever was needed, they felt it will be not met by the state government. And those details are given here in, summary wise. And detail, if anybody is interested, it has been published by Brijesh Kumar in this journal, the proceeding of first BINA workshop. And we have after that also published in the current science, details are given, in this volume and page number. Summary is that between actual, activity, telescope order was in 2007. So design, manufacturing, and factory test, all these things happened between 2007 to 2013. And in fact, 2014-15, it was transportation, installation, and first light. And it was inaugurated by, as you can see, in the meantime, Belgians are also partner in it. They have contributed 2 million euro. And that's why it was jointly by the premiers of both countries, India and Belgium. It was inaugurated on 30th March 2016. Can I go to the next slide, please? Yeah, this slide basically I will highlight white site characterization is very important for these type of telescope. As you know, when we are going to install any large size telescope, generally we try to find out what are the characterization, means what is the seeing at the place, and what is the, in a sense, sky brightness. And why it is important, this has been shown in this, that light gathering power of a telescope is directly proportional to the size, which has been expressed in this equation. And where D is the diameter of the telescope, S is the diameter of pupil of eye, and T's law says due to optics and detector. And if we see, we generally talk about signal to noise ratio in these observations. So that is directly proportional to the integration time and light gathering power, but inversely proportional to the sky brightness and angle formed by the image. And this angle formed by the image, it's being a ground-based telescope, it very much depends upon what is the atmospheric turbulence and those things which are present there. That's why site characterization is essential, because it also, in a sense, specify technical parameters for the telescope. And also this part is very important, that up to what, accuracy mirror surface should be made at different wavelength range, because that will finally dictate the size of the image which we are going to get, because it's a convolution of seeing plus, these surface inaccuracies and all these things. So this slide basically just emphasizes why sites characterization is important. So looking this, we during 80 to 90, based on those observations, it became very clear that if we are looking for the dark sky and better atmospheric seeing, then Devasthal is a good location. And the reason for this, the location of Devasthal is shown here. But if you look into this topographical, picture of the Devasthal, you will see that it is surrounded by, hills. None of them are higher than the Devasthal peak, up to a aerial range of about 10 kilometer. And also, if you see, it's like a 1 kilometer high cliff, from southwest direction, that is the wind direction, and that provides a laminar airflow. And this laminar airflow is very much, in fact, useful for producing good atmospheric seeing. And these are, based on numerical simulation and other things, people have already demonstrated that if you find a place where laminar flow is observed, then that should provide good seeing. And in fact, Professor Tandon, before we measured all these things, he had given an indication that, the seeing at the top, it should be reasonably good. So considering these things, if we go to the next slide, during 1996 to 2001, in fact, 80 to 90, as I told you, we identified, but in 90, since DPR was not approved, project was abandoned. But in 96 again, we revived. And during this period, TIFR joined, IIA also joined. In fact, IIA contributed even 6 lakh for initial, setting up these facilities. And these two places we characterized. Top shows the, there was called temple, and this what we used to call in those days base camp. They have a altitude difference of more than, I think, 150 meter or so. Next slide, please. So this is the summary of those results, what we carried out measurements. They are published already. And if we summarize, details are given here, that median seeing is 1.1 arc second. Of that, if we see 10 percentile, it's 0.75 arc second. One thing which I would like to mention, it's ground level, because the mirror, telescope mirror, which was used to measure these differential image motion monitor, it was, about 2 meters above the ground. That's why we say that it's a ground level seeing. But to estimate whether we gain anything or not, if we try to go to the higher, from the ground surface, which was expected, then it was found that if we had, microthermal measurements, and they indicated that between 6 to 12 meter, the atmospheric seeing is 0.086 second, and 12 to 18 meter atmospheric seeing contribution is 0.22 arc second. So in fact, these numbers were very useful when it came to decide at what level we should put a primary mirror of 3.6 meter so that we can get best seeing. And other parameter which I would like to mention here, that intra-night variation. If you see air temperature variation in a year, it's almost, you can say 25, 26 degree. But if you talk about during a night, it was less than 2 degrees centigrade. And that also indicated that it will be a good place from the seeing point of view. Rain wise, definitely most of you might be knowing that after middle of June to September, we closed the telescope, because during this period, we get over 2 meter rainfall. And as it is indicated, about 80% of this is during this period. It's a heavy rainfall, and humidity. So we try to protect optics of the telescope and other instruments. So during this period, telescope is not operational. For observations, for maintenance and other things one can do. This is average annual snowfall. It's about 60 centimeter. And clear night during the remaining period, it's about 208 spectroscopic night. Good part is that out of them, 175 are photometric. And these are the extension measurements which were carried out in 99, 98. They are published in 2000. These numbers indicate that the sky is relatively, good. Can we go to the next slide, please? Yeah. So these few slides shows how these, in fact, one thing which I mentioned, the project could start only once the state government handed over this observatory to DST, and basically due to funding of DST, this project could see its light today, and we are able to talk about it. I don't want to talk in details about the teething trouble what any major project like this are bound to happen, but let me just show you its progress. For example, telescope building and dome structure. It was PPS, precision precast system in Pune, and Pedvec was the company located in Hyderabad. They took the responsibility of building this, and it's a rotating dome. In fact, it is one of the for this size of telescope, this is the compact dome size, and it is located 13 meters above ground for the regions which I just mentioned earlier. And on top of that, thanks to project management board led by Professor Agrawal, but technically I will say it was helped by G. Srinivasan as well as Professor Shyam Tandon, who saw to it that the low thermal mass and ventilation system and all these things are very good in the dome, which will help in achieving better seeing. And this is one of the other reason you can say that guest house and related facilities, they are near the base camp. They are far away from the telescope location. So these pictures, they just show you at different stages. And as you can see from the bottom, it took more than 2 years to complete the dome structure. And finally, that's how the telescope, which is in the bottom corner, you see the completed dome. Next slide, please. Yeah, this, in fact, this is a what we showing the pier, central pier. It's a hollow with inner diameter of 5 meters and outer diameter of 7 meters, and it's a height of 8.26 meters from the ground, and that's how it has been made. Its initial structure is shown there, and also because of compactness and other things, we have limited space. So for mounting instrument and even for installation of the telescope, it was necessary to have cranes. And this, other diagram shows existence of crane in the dome, which have been used to install the telescope, as well as they are routinely used for mounting, dismounting instrument and related, and when the primary mirror is going to be aluminized at the place. We have in the associated building, that is telescope building. Here you see, yeah, next please, yeah. This shows the ventilation system which I mentioned earlier. And in the dome, this extension building, what you say, that's where we have towards the end, aluminizing unit. And then this building also has cranes to take the mirror from telescope floor to ground floor, and then transport it to the aluminizing facility and all those things. So in a sense, it's a very compact and very good system which has been built. Now I will tell you it's about optical configuration. It's a F9 beam, which means combination of M1 and M2. And finally produce a plate scale at the focal plane at RC focus 0.1 arc second per 15 micrometer. M1 is 3.6 meter f2, and finally it has been figured with a wavefront error, root mean square, error is less than 49 nanometer, and M2 is 0.95 meter in diameter, and that has a RMS of less than 30 nanometer. Field of view, if it has 3 ports, as you can see, one is main port, what we call axial port. It has a field of view of 30 arc minute, but we can use, this mirror, folded mirror, and once it can go to one side of the port, other time it can go to other type of the port, and that has a field of view of 10 arc minute. Yeah, please go to the next, right. So this basically shows once it is built, and in fact, Brijesh Kumar has given more details about installation, telescope building, infrastructure development, aluminizing coating, and first light performance results. And it was very encouraging to see that low thermal mass, which has been used in this building construction, it has really paid dividend, and it has not degraded the scene, which significantly. Advantage and performance of the telescope has been detailed by Amitesh Somar. Recently, in a few articles, we have given the science results, which I am going to talk to you in the next few slides. So this was during the testing time. This was air-cooled microlane CCD chip, and it has a pixel of 0.06 arc second. During that time, in fact, EMOS engineer, project scientist, there was a lady, Natali. In fact, she was, during factory tests, she was not very convinced that we are going to have, sub-arc second images. And while Professor Tandon was trying to put, demand that, look, this is our demand, we don't want to budge from here, she was reluctant. But when she visited this place, I still remember one night I had chat with her, and she said, no, Ram, I'm happy that you people insisted, and we are able to get sub-arc second images. And this shows a revolution, proof that sub-arc second images of during testing period, they were obtained. Now the next slide, please. Yeah, this is another picture which is taken with SBIC CCD camera in May 2017. It's a picture of quasar, which shows clearly that they are separated. And this is a picture of a star. Can you go to the next, please? Yeah. Here, as you can see, at the telescope, we have 4 imaging, back-end instruments which are used presently. First one, which was used, it was CCD imager, and more detail about has been given by S.B. Pandey et al. In 2018. And this, as well as EdFast, these were, I will say, in-house development, and they, in fact, their result shows that it was a very good project to take upon, because these have trained a good number of scientists, engineers for participation in these type of complex instrument. And here, in fact, near IR, I'm really thankful to TIFR, particularly to Devendra Ojha, who took lead in installing these 2 back-end instruments, TIR-CAM and TANSPEC. And these 4 instruments, which are available for observations on 3.6 meter today. Next, yeah. This is, opportunity. After 2016, people have started observing. So as you can see, the calls are in cycle. C1 cycle 1, what they call, it is between February to May and October to January is the second cycle. And one can submit online, and most of the things they have made it online, which are very useful. And presently, in fact, data lock-in period is 1 year, and high resolution imaging is up to 0.5 arc-second invisible to NIR, in a wavelength range of 0.4 to 3.7 micron. It is possible. Low resolution spectroscopy from NIR 0.5 to 2.5 micron, it is also possible. And target of our opportunities, unexpected transients. They have been, in fact, a good number of them has been used, and they demonstrate importance of this telescope taking what we call longitudinal advantage. As I mentioned earlier, that 2 million euro has been contributed by Belgians. So 7% of the telescope time is given to Belgians, and 93% Indian astronomers, which includes 33% to the Aries also. So the TIR Camp 2, it has been detailedly described by Beg et al., Ojha et al., and in user manual also. Briefly, it has these filters, JHK, and a number of filters, and the CCD characteristics are given here. And these are the effective.
Go, sir.
Sorry?
5 more minutes to go.
Okay, I am about to cover. So these are the central wavelength, and this is the half width. And main highlight is that we were not knowing that what is the capability of near IR at Devasthal, but these numbers, yeah, please go to the next slide. Yeah. So this clearly shows what is the importance, and we are able to detect, at 3 sigma level, in NBL, narrow band filter, at these wavelengths, and this is the sky brightness, and this shows curve, exposure time, and for given signal to noise ratio, how much exposure time we have to go. So these numbers, which are with 10% photometric accuracy, they indicate clearly that site is good for near IR observation. Next one. Yeah, this is again some K-band images of different type of objects like globular cluster, open cluster, galaxy, and planetary nebulae. And in fact, these results are published in JA last year. This is the detail. Yeah, please go to the next one. This also shows another type of observations which TIRCAM has been used to take. It's a lunar occultation, where millisecond time domain astronomy and lunar occultation of late type stars and milli-arc second resolution of stars have been achieved. Go to the next one, please. Next slide. Yeah, so this shows this was one of the occultation program where, yeah, Pluto, it occulted, and it's very useful information in the sense that such observations are very rare. And this project was led by NMXO from PRL, but from Aries, Saurav participated in this. Can we go to the next one, please? Yeah, this shows, CCD imager, and it has broadband filters. These are the wavelength, and these are the, half bandwidth, and these are color magnitude diagram, and it's showing that up to 10% photometric accuracy, one can go below 24 magnitude in 1200 seconds. So these, yeah, please go to the next one. Yeah. These are other images which are taken in R band, and which shows, various type of objects and how these are happening. This is open cluster, this is Crab Nebula, this is star forming regions, and it has a field of view of about 6.5 and 6.5 arc minute. Can we go to the next one, please? Yeah, this I would like to spend few things that the time domain astronomy, in fact, interesting. I mean, what was expected, and I would just like to highlight one thing. If you just see GRB afterglow, you see the magnitude at the faintest end, 25th, close to even 26th magnitude, they have been observed from Devasthal. So this is basically because of good seeing and other things. And in other diagram also, as you can see, supernovae, good number of observations have been taken and they are published, and the study of galaxy and all those things have been done. Similarly, at FAST, which was again a in-house built back-end instrument, it is performing quite well. Most of the results are published by Amitesh Omar in Current Science. Just to highlight, if you just see, this is one of the deep HST image, and this is deep dot image. So at least this arc and other features you can easily see. So that's reflect resolution wise. Yeah, please go to the next one. Yeah. And this shows about its spectral capability. So dot has taken this object, and damped Lipan alpha system that is clearly visible, and this is taken with similar facility but from other place. Next one, please. Yeah, 10 spec, that is the latest edition in this, and it has already tested, and it is showing very encouraging results. For example, in imaging JHK 19.5, 18.9, and so on at 10 sigma in 10 minutes. And various type of objects have been imaged. So this again shows its capability. Can we go to the next one? This is again showing the capability of 10 spec. And 10 spec, it's a joint instrument, means TIFR Aries near infrared spectrograph. So it's working, and these two are the upcoming instruments which we expect that soon it will become available. This is DOTIF. It's led by Ram Prakash and Amitesh, and it's in very advanced stage. We expect that soon it will be at the site and one can start using. This project, which people were, we were thinking since long, but finally it has got approval from DST, and Jeevan Pandey is leading this activity. So these two instruments will be very important. So summary and conclusion of this presentation is that, this Devasthal, DOT, I have said Devasthal Optical Observatory, it's a northern sky coverage and longitudinal advantage, as it is located almost in the center of Spain in west and Australia in east for transient objects. So time domain astronomy, it's very useful. And this aspect I have already highlighted, that primary mirror with active optics technology is capable of providing sub-arc second images for a good fraction of observing time. And optical and NIR, one can observe. And this I again highlighted that because of the care taken in construction of telescope house, it has paid its dividends, and we are able to see good, sub-arc second images, it means whatever was expected, more or less we are able to see. And we expect that once the modern back instrument, of course, I just displayed a spectrum of the science results, which have been, not all, but definitely as it was thought in the beginning that it will be used for follow-up observation of GMRT and AstroSat. In fact, partly it is happening. And once the modern back-end instruments, including adaptive optics, high-resolution spectrographs, coupled with, excellent atmospheric condition, they have immense potential to contribute to the global astronomy in coming years, because the performance of the telescope is almost similar to other international telescopes. And this is the last slide. Thanks for your attention. Yeah.
Thank you very much, sir, for your talk and review about the 3.6 meter project and that how it evolved and what is the present situation. And we hope that with all backend instruments coming up in next years or so, we will have much more impactful results. So questions, please. One or two questions, although the session is a little late, but one or two questions could be taken from audience if you have.
Hello.
Yes.
Yeah.
This is Abhay here. I'm just interested to know if while you are finalizing the location for the telescope, did you consider some of the islands that India has? And do they offer good locations for future telescopes if one has to think about it?
As you might have seen from the history, since at that time it was UP State Observatory, so basically it was concentrated in Garhwal and Kumaon Hills. So whatever altitude, topographical location which are conducive for these things, they were considered, and this was found a reasonably good site from the seeing point of view.
Okay, for any future plans, do you think islands could be a good observational sites if one has to plan in future?
Actually, it's not that thing. What is the surrounding about it? Topography, what type of topography is there? Whether it is conducive for laminar airflow in that region or not. So unless we quantify, for example, sometimes people feel that, if we go just by altitude, we will get good seeing, but that is not true. Actually, even at a sea level, if you build more than 1 kilometer high tower, from the seeing point of view, it will be quite good, but not from the other point of view. So what I'm trying to say that it's not the Iceland. What is the topography at that place? That becomes more important.
Okay, thank you.
Any other question? If not, then let's thank Professor Ramsagarji again for his nice review. And with this, let us have a tea break, and we will gather again here at 11:30. Thanks,
Sasi, for helping to, I got stuck somewhere.
Yeah, no problem, sir. It was some problem, but it was resolved. Sir, thanks, sir.
हाँ, आ रहा हूँ. I just finished my presentation.
So welcome back to the post-T session. And the first talk in this session would be by Professor D.K. Sahu from IIA. He would be talking about Himalayan Chandra Telescope 2 meter and the major results obtained from it. Professor Sahu, you are most welcome to deliver the talk. And the duration is 25 minutes plus 5 minutes, in the sense that 25 minutes, after 25 minutes, I will give you a warning that only 5 minutes are there. After that, 10 minutes are there for discussion. So total 40 minutes. Professor Sahu, please.
Good morning, everybody.
Your voice is little weaker. Please come a little closer to the mic.
Okay, 1 minute. Is it okay now?
Yeah, but yes.
Is it okay?
Yes, very nice.
Yeah. Good morning, everybody. First, I would like to thank the organizers for giving me an opportunity to talk about Himalayan Chandra Telescope and major results obtained using HCT on this forum. So I will start with Indian Astronomical Observatory, which houses the Himalayan Chandra Telescope. So Indian Astronomical Observatory is located at Mount Saraswati at Hanle. This Mount Saraswati was earlier known as Dikpa Ratsari in the local Ladakhi language. So these are the coordinates of the site. This observatory is located at around 15,000 feet height from the mean sea level. It provides good number of clear nights, around 260 clear nights we get per year. Out of those 260, around 190 nights are photometric. So because of this is an excellent site for astronomical observations. Other than this 2-meter optical near-infrared telescope, there are some other facilities also located here. One of them, which is seen here, a small dome that houses this 0.7-meter Growth India telescope. There are some other facilities which are not seen in this. They are located at the base camp, which includes this high-altitude gamma-ray Hagar telescope and a newly commissioned 21-meter imaging Cherenkov telescope MACE. So both these telescopes will be operating in gamma ray. So this camera calibration and some testing of this 21-meter imaging Cherenkov telescope is on. Other than this, we have some site characterization instruments located at the top. This illuminizing facility, the top building, which you can see at the right. This is the illuminizing chamber. We have LN2 planted at the base camp, and you can see the solar panels just below this 0.7-meter Growth dome. So the full observatory is running on solar power. So this kind of a green observatory. I will just start with a little bit of background. So the installation of this 2-meter telescope was done in 2000. If in 2000, this completion of enclosure building happened, satellite link between Hoskote and Hanle to operate this telescope was installed during this period. And when the telescope reached Mumbai airport, from Mumbai to Chandigarh, it was transported by road. And you can see the team of the people who participated in the transportation of the telescope. And from Chandigarh to Leh, it was airlifted by Air Force cargo planes. And from Leh to Hanle, it was again transported by road. So the installation process of this telescope was over by mid-September or toward the third week of September 2000. And on September 26, 2000, the telescope saw its first light. And the first light was witnessed by Professor Yashpal, Professor Ramnath Kaushik, the then director of IIA, Professor Tushar Prabhu, who was the project manager, and Dr. R. Srinivasan, who was heading the engineering team of this project. During 2000-2001, some preliminary, seasonal, and final acceptance tests were made for dome automation, some part of instrument development. These all happened during 2000-2001. I just forgot to tell you that this is the first light image of the taken through the telescope of Beta Cassiopeia star. You can see the first chromatic images, and then suddenly it looked like a nice ring-shaped and circular image. So this telescope is being operated from Center for Research and Education in Science and Technology, where I'm sitting now. It's near Bangalore. It's Hoskote campus, and all the remote operations are being carried out using the satellite link between this place and Hanle. Recently, during last September, we had celebrated HCT 20 for the successful operation of 20 years of HCT. So this Himalayan Chandra, little bit of Himalayan Chandra telescope, because this, as we know, it's a difficult site, difficult terrain, very high, low oxygen level. So the telescope has to be very compact, lightweight, and designed in such a way so that it should be suitable for installation, operation, and maintenance at high altitude. So the primary mirror of the telescope was made of ultra-low expansion material, Corning, and its focal ratio is f1.75. Focal ratio of the entire telescope is f9, with a plate scale of 11.5 arcsecond per millimeter. We have provision for nice smooth focus also, nice smooth port also. So the field of view of the telescope was 7 arc minute without corrector plate, and with corrector it is 30 arc minute. Of course, we don't have corrector plate till now. For the image quality, what was specified was 80% encircled energy within 0.33 arc second diameter. And to have this telescope compact, ultra-azimuth mount was adopted. So the performance of the telescope is very good. Its pointing accuracy is less than 1.5 arc second with pointing model. This was specified, but right now we are getting around 2 to 2.5 arc second. Tracking accuracy without guiding was less than 0.5 arc second over 10 minutes. In order to make the operation of the telescope smoother, instruments were mounted on an instrument port. For all the 3 instruments which I'm going to tell about, they are all the time mounted on the telescope, and just by moving the tertiary mirror, the desired instrument can be chosen and the observation can be carried out. So these are the instruments which are currently mounted on telescope. The most preferred instrument or most used instrument is Hanle Bent Object Spectrograph Camera HFOS, which has capability of taking low medium resolution spectrum over 300 to 920 nanometer. We have this narrowband, set of narrowband and broadband filters. This instrument is mounted on on-axis port. The other instrument, which was developed by TIFR, known as TIFR, infrared, near-infrared spectrometer camera telescope, which is mounted on one of the side port. It also has both imaging and spectroscopic capabilities from 0.9 to 2.5 micron range with a medium resolution spectroscopy. During the last 2 years before, we have installed this Hanle Ishel spectrometer, that is a high resolution spectrograph, which operates between 350 to 920 nanometer, giving resolution of, there are 2 modes. In one mode, we get 30,000 resolution. Second mode, we get 60,000 resolution. So the limiting magnitude, or we can, with 12 magnitude, we can get a good spectrum, high resolution spectrum with 60,000 resolution, going up to a star of magnitude around 12 mag. So this instrument is housed inside a chamber in the ground floor, and the Cassegrain unit is attached on the telescope port and and the light from the telescope goes to the instrument control room through a fiber. For all these instruments, we have a common auto-guided camera, which is mounted on the side port. For all the instrument, telescope, everything is controlled remotely from Crest campus. Right now, earlier we were operating with 2 megahertz frequency. Now the bandwidth is increased from 2 to, there are 2 bandwidths available now. One is 3 megahertz, other is 1.5 megahertz. For the user community of SCT, it is used by both national and international astronomers. From the Indian side, we have astronomers from the institutes like IIA, ARIF, TIFR. People from universities are there who are using this telescope. And from the international side, we have collaboration or we have astronomers using this facility from Japan, France, Mexico, Australia. For these, foreign astronomers can either apply for time in collaboration with Indian astronomers, or they can go independently. So the proposals are reviewed by a National Time Allocation Committee. We have around 45 proposals. We have 3 cycles in a year, 4 months each, January to April, May to August, and September to December. For each cycle, we get around 45 proposals. And the dark moon period is oversubscribed by a factor of, on an average, 3, whereas the bright moon or the overall oversubscription is around 2.5. For the online proposal management system for applying for the telescope time, for this for its reviewing and the allotment is done in-house by IIA, and it is implemented since 2019 cycle 1. The same with slight modification was adopted by ARIF for 3.6 meter DOT. For the data archiving system for putting all the observed data and the archive is underway and it's under development. Now I come to utilization of SCT. Here we show the time which was allotted, the total time which was allotted for observation, and the green and the blue bar shows the night observed for more than 7 hours. And then the top one shows the cloudy or overcast night. So what we find that allocation for science, so based on this statistics, or based on this, we can get the number of clear nights or number of photometric and spectroscopic night, which I told earlier. So around 78% of the time is allocated for science programs, and the remaining 22% is time kept for maintenance, DDT, some of the observatory programs, like that. So the time which is allocated for science programs, around 10% or less than 10% of time is lost because of instrument problem. So we try to keep this downtime minimum. And this downtime is mainly, the major portion of this downtime comes because of this temperature. When the temperature goes below -20 degrees, we don't operate the telescope for the safety of the instrument and the telescope. So this is kind of output from this telescope. So number of referred publications are around 275 till date, and there are non-referred kind of circular telegrams, other things, which constitute around 165. The total number of citations received by these publications are around 5,000, and the H-index of the facility is around 35. So till now, total 38 PhDs have been completed who use the data from this telescope, 19 from IIA and 19 from non-IIA students, and there are around 36 ongoing PhD programs, 16 from IIA and 20 from non-IIA students. Because telescope is almost 20 years old now, we are trying to upgrade the telescope, mainly upgrade the secondary drive system, which more frequently which creates problems, which gives trouble, which leads to instability in the image quality. So the secondary drive of the telescope is planned to be upgraded. Along with that, the instrument derotator and the telescope control system, because these are all obsolete and we don't get any off-the-shelf spare parts for these. So we are planning to upgrade these components. So for these upgrades, initial work has been started. The feasibility study has been carried out, and we are working towards the final phase of this work. Now coming to the science, which the telescope has produced. So I have been asked to highlight the major science programs. I may be biased. My presentation will be biased a little bit, so for that I beg your pardon. So I'll start with transient studies using this telescope, on which I also work. and this telescope is best suited for this kind of work. So the number of papers which is produced using this facility in the different fields like gamma ray, afterglows of gamma ray burst sources, 16, supernovae around 50 papers, and novae cataclysm variable around there 14 papers are there. And there are other transients which are now popping up like tidal disruption event, the fast transient gravitational wave sources, EM counterpart. Here we are also started using this telescope for these kind of observations now. So I will just start with the first result, which is obtained with this telescope, was on a GRB 010222. It was published by Professor Kaufik in 2001. So the data was taken when the telescope was still in commissioning and testing phase. This GRB was observed with HCT 1 meter, HCT and 1 meter telescope with VBO. The time cover was 0.6 to 8 days after the event. What we found, we combined the data which was available in the literature with our observed data. It is found that there is a light curve break occurs around 7 hours after the burst, and the index of this power law for this light curve is 0.542, which steepens to 1.263 after the break. So here we see some of this fluctuation soon after this break, and this kind of fluctuations are explained by the inhomogeneities present in the ambient medium. So following a standard model of collimated jet outflow, the angle or the opening angle of the jet was estimated, and it is found to be around 3 degrees. The decay rate implies a hard spectrum of the electron energy distribution. And finally, it looks that this appear to be an example of a high energy outburst with a narrow jet angle of around 3 degrees and a hard electron energy spectrum in a normal interstellar medium. So after this, monitoring of GRB was taken as a larger collaborative program, and the participating institutes were IIA, ARIES, RRI, NCRA, and few other institutes from abroad. Under this program, the first object which was observed was GRB 021004, which was published by Pandey et al. This was a long duration GRB monitored in BVRI bands. Multi-band observations were taken from 3 hours to around 12 days after the burst. Some kind of unusual variation were seen in the different band light curves, which was kind of superimposed on underlying broken power law. The power law or the light curve break happened around 7 days after the burst, and the jet opening angle was found to be around 7 degrees. So low resolution spectrum was also obtained with HCT, which showed the spectral index of 0.6, and there are two absorbing systems at redshift 1.38 and 1.60, which could be two intervening metal line systems. So multi-wavelength observation indicated that this GRB was associated with a star forming region, which supported the hypothesis of the long GRB being the produced by collapsar origin. For the other GRB which were monitored under this program were GRB 0212, GRB 0306, GRB 0329, and there are a few more which I have not listed here. Now I come to the study of supernovae. The first supernova, although the first supernova which was observed with HCT was 2002 AP, which was a broad line type 1C supernova, but because we had only a few points for that object, so I have not mentioned it here. But the study which was made fully based on HCT data was 2003 DU, so detailed light curves and spectral analysis was done for this object. The high velocity feature, you can see the high velocity component were seen in calcium and silicon lines. But the thing which we missed was a small kink next to the silicon absorption, which was later identified as a carbon-2 line. And this line has great importance. After that, people started looking for this line in a big sample. And now we know that around 30% of the supernovae have this carbon line. And this shows that explosion mechanism of this object could be explosion mechanism of type 1 supernova could be deflagration detonation transition. So here as for the other object 2017 HPA, where we see the prominent carbon line here, right from minus 13 days till minus 6 days. In order to constrain the mass fraction of this carbon, a TARDIS model fit was made on this object, and it found that carbon mass fraction of 0.019 solar mass was required, which is lower than what we need from the pure deflagration model. So this again hints towards the deflagration to detonation transition as a possible mechanism for type 1 explosion. Now I come to type 1b and 1c supernova. By definition, type 1b and 1c supernova, 1b supernova, they are supposed to be helium rich. There is no hydrogen, whereas in type 1c supernova, we don't find hydrogen and helium. But this 2005 BF was an exception. Here I show the light curve, which shows kind of double peak, and the spectrum. So if you can see this inset of this image, what we find that the absorption, which was marked as silicon, can be well suited, can be well identified with high velocity H alpha. And we do see some signature of high velocity H beta also in the spectrum. So it looks that this explosion was a massive helium star with a trace of hydrogen in the envelope. Similar was the case with 2014 AD, which was a broadline type 1c supernova. It has a very high velocity, close to maximum, around 30,500 kilometers per second. And we see presence of weak helium. This is the spectrum of this object. And we tried to model this with SIN++. So if we don't incorporate any helium, we are not able to fit the spectrum properly. But once we include a little bit of helium, the observed spectrum can be modeled well. The arrow shows the other prominent helium line, these two, but because these are very faint as compared to this strong 5876 lines, we don't expect these lines to be seen in the spectrum. So this is another case. Now I come to type 2p supernova 2004 ET. So this is 2004 ET, which was a kind of normal type 2p supernova, but the peculiarity was seen here. The light curve decline steepens around 320 days after the explosion. Similarly, around the same time, we see the blue shift in the oxygen forbidden line as well as in the H alpha line. So the coincidence of this steepening of the light curve and the blue shift of this emission peaks was also seen in some other supernovae, and which was seen much later, more than 400 days after the explosion, and was correlated with the starting of dust formation. So what we see in this object is dust formation started in this object a bit early. The other objects, 2012 AW, for this object, major portion of this spectral data came from HCT. And here also this high velocity features were seen, like which are marked here A and B, and these were supposed to be coming from the interstellar CSM, which was present there. And this scenario was consistent with early detection of this object in X-ray and radio. So there are two some new studies, which is 2016 GFI. There are two peculiarities seen here. Here we see one bump in the early phase, we see the bump in the late phase. So the early phase bump was modeled or can be explained by this interaction with the available CSM, and that was also seen in the H alpha boxy profile. And the late phase bump was because of the mixing of the nickel in the ejecta. So if we model this light curve with Stella one-dimensional modeling code, then what we find, if we don't have any CSM, the rise of the light curve is slow. But once we include helium, or once we include hydrogen, so this light curve can be well fitted. Similarly, the later part of the bump, which I showed here, this later part of the bump can be explained by mixing of the nickel in the ejecta. The next object which we studied, or which was interesting for us, was 2018 HNA, which was the second object after 1987A, in which the cooling emission was seen. And as the other objects of this class, this object also was hosted by a very metal poor galaxy. Now coming to some studies based on novae. So one of the nova which was well studied was RS Ophiuchus. It's 2006 outburst. All the spectrum was taken with HCT. The second one, which was observed with HCT, was T Pixades. It's 2011 outburst. This outburst happened after 45 years. Earlier outburst was around 22 years before. Interval was 22 years. So the light curve shows some peculiarity, initial rise, and then some halt is there, and then decline is there. In the initial phase of the spectrum, indicate very high ejection velocity, around 4,000 kilometers, which reduces to 2,500 kilometers per second. So now I come to some other studies which carried out by XCT. So one of them was a spectroscopic study for CH stars. These stars are kind of halo tracers, and to understand them in a better way, a survey of faint high galactic latitude stars from Hamburg survey was initiated by Aruna Goswami and her team. Around 91 stars were observed to identify these CH stars. Using HCT, what they found is around 35 new stars they found, and later when they increased the sample, they found that around 37% of stars were this kind of CH stars. The same survey led to identification of a hydrogen deficient carbon star, and which was studied by bigger telescope like SWOG other thing. In a recent study, what they did, they have used HASP for getting this high resolution spectrum of 2 Lamost carbon stars, and the result is published by Zalama. The other project which was taken, which was the good project, was lithium-rich giant, because the lithium problem is a long persisting problem. So how the lithium is, whatever this observed lithium and the predicted lithium can be explained. To understand this, a systematic survey of large number of lithium-rich giant was initiated by Professor Reddy and his team. So they have observed around 2,000 simple stars with HFOS in low resolution mode. Here is the typical spectrum where we see the helium line, we see the lithium line. Lithium abundance was estimated for these stars. And some of these lithium, and what they did, finally they plotted the lithium stars in this HR diagram, and what they found that these lithium stars, they all populate a very narrow region in the HR diagram. So finally they inferred that this lithium production in the stars is there is no external agency for enhancing lithium, but these are because of the internal nucleosynthesis during the RGB bump phase. And this led to a nice publication which is published recently in Nature Astronomy by the same group, kind of extension of this work. So after this HASP was installed, this HASP GOMPA survey was initiated by
Professor Sahu, 5 minutes to go.
No, I think I was given how much time? 30 minutes, huh?
Yeah. So that's what I'm saying. 5 more minutes to go. After that, 10 more minutes would be there for discussions.
Yeah. I'll try to finish. Yeah. So this was another good survey which was started by to study this metal poor stars in the galaxy. Around 50 stars with high resolution spectrum for 50 star high resolution spectrum were taken, and they found some new carbon enhanced metal poor star and extreme metal poor stars, and which led to the high resolution study of these stars. I'll skip this. Okay, now I come to some extra-galactic sources. One of them is this blue compact dwarf galaxies, which was studied by, so blue compact dwarf galaxies, the name suggests they are blue galaxies. It was thought that they are undergoing intense burst of star formation. So these galaxies were studied to understand the star formation history of these objects using this low resolution spectrum and narrowband and broadband imaging. It was found that these BCDs harbor, or BCDs have an underlying population of old stars, which is around 4 giga-year old, and on top of the old population, there is some starburst activity occurring, which are as young as around few million years. So this result was part of Ramya's thesis. Then another work which was carried out on the extragalactic front was studying this, observing this low surface brightness galaxies in near infrared to look for the bars in these galaxies. So what this result found was this bars in low surface brightness galaxies are the fraction of bar galaxies are less, but this study shows that bar can be sustained in this kind of halo-dominated, dark halo-dominated galaxies also. So this was part of Hani's thesis. And then they tried to estimate the mass of this AGN, mass of the black hole at the center of these low surface bright galaxies. It is found that the mass of the black hole, which is there in the center of these low surface bright galaxies, they are like kind of intermediate mass black hole, around 10 to the power 5 solar mass or so. So when these mass of these black holes are plotted in this relation with black hole mass of sigma velocity dispersion, it is found that these galaxies populate the lower region of the plot. So another interesting work which was carried out by by this TIFR group was comprehensive long-term monitoring of this FU Orionis and EX Orionis star to understand the star formation or kind of episodic kind of accretion and outflow of these stars. So there are, this is the first star, V1647 Orionis, which was observed, the source, and then later this V8991 was observed. And based on this, they estimated, based on the spectrum or based on the line of strength, they estimated the accretion rate. And when the accretion rate was, when they correlated this accretion rate, so they found that when the accretion rate is high, they found this prominent P signal profile. So this shows that when the accretion rate is high, there is kind of eruption from the star. So this was the first demonstration done by them. And then the other friend, they had studied this bright rim clouds to study the sequential star formation. So as per this hypothesis, there should be some age sequence seen in the age of the stars as we go away from this bright rim cloud. So with this study, they found that the age sequence really exists. So they came up with the idea that this called it small scale sequential star formation also occurs. And this is basically influenced by the presence of massive star in the close to the bright rim cloud. Then there is another study done by in which this Orion Nebula cluster was monitored for a long time to look for periodic and stars, which was it was taken around 200 nights of data was taken, and here we see the distribution of the stars, periodic and non-periodic stars. The green symbol shows the classical T Tauri star, which were found in this survey, and the red circle shows that weak T Tauri stars. It is found that this around 72% of classical T Tauris are periodic, whereas 32% of weak T Tauris are aperiodic or not are periodic. So this shows that this inhomogeneity pattern on the surface of classical T Tauris are much more stable than in weak T Tauris. Then we come to work in which HCT participated and which led to the confirmation of TRAPPIST-1b exoplanet. In this work was published in Nature. For this TRAPPIST telescope monitored a star TRAPPIST-1 to massless star for a very long time, and they detected some 11 clear transit signatures with amplitude close to 1%. And when they tried to associate it with this to check the presence of exoplanet, they monitored this source with HCT, 8-meter VLT, and UCURD. And with that, this here I show this light curve, which is taken by HCT. So, so this led to the confirmation of this TRAPPIST-1b as a exoplanet. Coming to some of the solar system objects, the comet 2I Borisov, which was supposed to be the first interstellar comet which came close to the solar system. This was studied by Kumar et al. And it's published in 2021. So this comet was observed, or the spectrum of this comet was observed using HCT. And what we found that if we measure this element, this abundance of carbon, C3, C2 bands, it is found that this comet is similar to the comet which are coming from our own solar system. So what they infer is a high possibility of the comet formation process similar to solar system is happening in other stellar system also. So other than this, HCT participated in some other international campaigns where it's kind of multi-observatory campaign and which led to several publications. Out of them, this sporadic activity of GALT, in which this rotation period of this object was found to be 2 hours, and our HCT observation played a major role in determining this period of this object. So other science area which I could not cover in this talk because of time limitations were exoplanet, exosolar transiting planets, brown dwarf, substellar objects. There are many studies done in the field of galactic star forming regions, young stellar objects, star cluster, emission line objects, and then intranight and long-term variability of QSOs. There is some work carried out in the field of gravitational lens and microlensing also. So I think I'll finish here, and thank you for your attention.
Yeah, thank you very much, Professor Sahu, for your very nice talk and a very good summary of HCT related results during last 20 years, all the way from comets to extra-galactic sources. And it's very nice to see, and definitely HCT has helped us to carry on with the transient science during last 2 decades or so. So with this, we again thank Professor Sahu, and now it's time for questions so from audience. It seems that Abhay Karnataki has a question.
Yeah, please.
Abhay, you are Mohit. Yeah.
Yeah, hello. Thank you for a nice talk, sir. I just want to know the process of finding the supernovae, which you have mentioned in your talk. Was it that you were observing particular area of the sky and you detected a supernova, or there were some parallel observations all over the world and then you followed it with HCT?
Yeah, what you mentioned in the second part of your question, that is correct. So there are some dedicated teams which are hunting for these kind of supernovae and other transient objects. So they need some dedicated telescope, and they have different strategy, different cadence. They cover different region of the sky periodically, and based on that, they detect some new objects, and those objects were announced worldwide. So once the announcement is made, we try to follow these objects, which suits our interest, and then we monitor those kind of objects with our telescope, our facilities.
Okay, all right.
Any other question?
Shashi, may I ask?
Yes, please.
Yeah, thank you, Devendra. It was a very nice talk and a very detailed coverage of science outcomes from SCT, and I hope the very best in future as well. So you mentioned in the first slide, I think 190 photometric nights per year. That's so it has been about 20 years of operation of SCT. Do you have any means to record these photometric nights, and have you observed any evolution over time?
Evolution we have not studied, but what we are having is we have independent way of defining a night, whether it's a photometric night or it's a spectroscopic night. So not only based on our observation taken with SVT, we have people there who periodically go out in the night and check the sky, and then they record in their separate log sheets whether night was, how many octave the sky is clear. If more than 7 octave is clear, they call it photometric night.
Okay, so how frequently it is recorded in a night?
Yeah, every night they are recording it, and every year we have kind of we prepare this detailed summary of this night sky condition.
Okay.
Done in this way. But what we have not studied any this evolution, whether it's really maintained or there is any change in this fraction of the clear night.
I think it will be very interesting.
Yeah, it's a good idea to look for that. Yeah,
over time.
It's a good idea to look for that.
Yeah. Okay, I had another query related to this tracking accuracy for this telescope. I think you showed in one of the slides that it was a little comparable to the image quality as a 0.33 arc second, and tracking accuracy is even 0.55. I think it is RMS, right?
Yeah, this is RMS, yeah.
So it is really too high in comparison to encircling energy, which is very low, I would say. On FWHM, even it will be lower.
No, what we noticed was when we did not have this auto guider in the initial phase. So that time we used to give 15 minutes exposure for spectroscopy without having auto guider. Okay. And the star used to remain in the slit of around our 167 L slit.
Okay.
So with that it looked okay.
So this is without a guider, right? 0.5.
Yeah, it was without guider. Yeah.
Without guider. Okay.
Yeah.
Yeah, it was not really. Okay, I think that's all. Yeah, thank you, Devendra.
Any other question? Still, we have a couple of minutes to go. 1 or 2 questions could be adjusted. Yeah, if not, then let us thank Professor Sahu again. Thanks, Professor Sahu. And please.
If I have to stop
unshare the screen.
I'll stop sharing. Yeah.
Yeah.
Is it gone now?
Yes.
Yeah. Okay.
Yeah.
Okay.
Thank you. Thanks. So now it's time to move towards space-based astronomy and how we are doing there. And we, as we all are aware, that 2015 onwards, we have our own space-based facility called AstroSat. And in fact, AstroSat, like other facilities we heard about, it is also as an outcome of years and years of efforts. And today, as a speaker, we have our eminent astronomer, senior astronomer, Professor P.C. Agrawal, who was associated with AstroSat as PI during the phase when AstroSat actually took shape and all X-ray payloads and how it should be and so on. So as an eminent speaker, now I would like to invite Professor P.C. Agrawalji to deliver a talk about AstroSat and particularly the X-ray aspects of AstroSat project. So, sir, the way we have decided is that we have 40-minute slot and 30 minutes for talks and 10 minutes for discussions. Yes, easy. Sir, so please go in full screen mode.
Am I audible?
Yes, sir.
Are you able to see the slides?
Yes.
Okay.
But please go in full screen mode, sir.
Okay. Full screen mode, yes.
Yes, sir.
Is it okay?
Yes.
Yeah.
I think I have to go away.
It's the
Yeah.
Yes, sir.
Okay. So today I'm going to talk about X-ray instruments, their performance, and some recent results. As you know, the AstroSat satellite was launched about 5.5 years ago from Shar range of ISRO using a PSLV rocket and placed in a circular orbit of 650 kilometer altitude and 60 degree orbital inclination. Since then, for the last 5.5 years, these instruments have been working more or less reasonably well and producing a lot of data. And many of you might have recently submitted proposals for the AO, which was put out and which closed on March 31st. So before I go to the details of the result, instruments and result, I'd just like to spend 1 or 2 minutes on the genesis of AstroSat. As you know, the first X-ray source was discovered in 1962 by Giacconi and colleagues from ASNA in USA. And it was the chance discovery of Scorpius X1, which is the brightest X-ray source in the sky, which marked the birth of the X-ray astronomy. Now it so happened that Professor Shikantan from TFR, who later became director, was visiting MIT during 1965-66. And he happened to be there and he participated in the experiments which were being conducted by MIT and ASNA jointly to measure the position and size of Scorpius X1 and to the optically identify it. So when Professor Shikantan, from his experience of rocket flights, returned to TFR, he wanted to start exceptional program. And TFR had very good facility for making balloons and instruments. So I was working in cosmic radiation group. So I was, he asked me that I'll be interested. So I joined the group. And within 15 months, we developed a balloon instrument which could be oriented, which is a scintillation counter for detecting X-rays with anticoincidence. And we made a flight in 1968, which reached about 37-38 kilometers. And we measured erratic variations in the X-ray intensity of Scorpius X1, which was immediately published in Nature. So following this, a series of balloon experiments are carried out in TFR during 68 to 75, and in parallel by some experiments are carried out also by PRL group of Professor Rao. And many significant results emerged from these balloon studies during the till 75 period. and we published these results in series of papers. Several of them appear in Nature. Important results were discovery of a flare in Cygnus X1, the non-thermal component in Scorpius X1, and so on. But soon it became clear to us by 1975 that the scope of the balloon instrument and rocket flight is very limited. As you can study in a flight, typically 1 or 2 sources, for limited time. So the future of the astronomy lies in the satellite experiments. Therefore, in 1980, we prepared a proposal jointly with the Space Astronomy Group of ISRO Satellite Centers, ISAC, and sent it to ISRO. And we proposed flying an X-ray instrument consisting of 4 propulsion counters, the area of 1600 centimeters square, on ASLV rocket, which was at the time under test. Unfortunately, ASLV could not carry a 50 kg payload, and so this proposal remained just on the paper. Fortunately, in 1994, payload satellite launch vehicle PSLV was successfully launched, which had a capability of launching a 1 to 1.5 ton satellite in near Earth orbit. So I approached Dr. Kasturangan, who was the chairman at the time, and requested that our proposal be accommodated, our instrument be accommodated on the next flight of the PSLV, which was made for flying an Indian remote sensing satellite known as IRS-P3 in 1996. So he agreed to accommodate it on the condition to develop the instrument, because this happened in 1995, early 1995. So he said, if you could develop the instrument, deliver it in time, then we can fly it. So we worked at frantic pace, and in 15 months we made the instrument, and you can see the propulsion counter here. It also had a sky monitor, developed by Professor Herlock. So this was launched on March 21, 1996, and this instrument worked successfully from 1996 to 2001, when it was switched off when the satellite ran out of the gas to carry out the operation to point these instruments in space. Now let me point out that IRS-P3 was a remote sensing satellite. So in 10 months out of 12, it looked at the Earth, and our instrument had to switch off. So we got 2 months observing time to look at the sky during the monsoon period when IRS-P3 could not do much. So we used this instrument for 5 years and obtained some interesting results. And one of the most significant results was, which is now called heartbeat, what is known as heartbeat of the mass-stellar black hole. Well, we at the time called this, you can see the cosmic periodic burst occurring every 50 to 60 seconds. And we call 50 to 60 minutes, it's a second, 50 to 60 seconds. And we observed this, continuously for a month. So you can see how the burst comes. We interpreted this burst a rejection of mass from the efficient disk around the black hole. And you can see the temperature rises, which is not shown here, but temperature becomes maximum when they just near the when it reaches peak. So interpreted it as a matter disappearing behind the event horizon of the black hole, and published it in a day later. So we observed several sources, 15, 20 sources, and a lot more papers came from it. It also produced PhD thesis of Professor Paul, who is not already, Professor Naik, who is at PRN, and so on. So this was a milestone actually in the development of satellite and the development of AstroSat. Okay, so following this, we wrote to the proposal for a larger X-ray instruments, mostly proportional counter filled with xenon, for studying the variability and the spectra of X-ray sources, variety of X-ray sources. So the chairman immediately responded and said that yes, we would like the satellite proposal to be discussed seriously. But he said that we should involve the entire astronomical community in India, so that if there are ideas to observe another wavelength band, we can also accommodate the same satellite. So following this, there is a high meeting of Indian astronomers at the eastward quarter, and then subsequently two working groups were formed. One for optical infrared and UV, other for X and gamma astronomy. And these groups deliberated over 2 years, and finally the concept of AstroSat emerged. That AstroSat will be a broad spectral instrument satellite, which will carry instrument, it will cover not only X-ray but visible, near UV, far UV, soft X-ray and hard X-ray. And so what is it will be multi-wavelength astronomy satellite. That was the decision. So what is the unique thing about AstroSat? Well, you know that AstroSat cannot, there are many observatories like Chandra, extra-galactic integral, okay, and then now there is a Swift. But this I'm talking in a time frame of 2000 roughly. So these are all observatories, fantastic observatories, have tremendous capability, but you can see they are only for optical UV observation in case of Hubble. Chandra, 0.2 to 10 kV, but fantastic resolution, 0.5 arc second. Extra-Newton, resolution of 4 arc second, but you know, very large collecting area. Integral at hard X capability of 50 to 150 kV. And Swift was launched in 2006, so it also has a hard X capability, and but it is an XRT, X-ray reflecting telescope. So you can see that all these observatories are fantastic in their capability, but they study in a narrow wavelength band. So AstroSat was conceived as a multi-wavelength astronomy satellite. And you can see here a picture of the satellite, not picture, a sketch of the satellite bus. You can see the 3 leg species, instruments mounted along 3 central region. You can see the UAT, twin UAT telescope. This is the soft X-ray telescope, and this is the cadmium infrared imager. And then there is one instrument for monitoring the X-ray sky, and that was the scanning sky monitor, just developed by ISRO Satellite Center. So for the large area X-ray propulsion count instrument consists of 3 identical detectors with the area of greater than 6,000 square 20 kV, field of view 1 degree, and sensitivity in 3 to 80 kV band with low spectral resolution. Now this anode assembly which is shown here is the heart of the leg species. It consists of 60 anode cells arranged in 5 layers, each 3 centimeter deep. So it is made a deep detector with 15 centimeter depth so that you can detect photons of 80 kV. It is surrounded on 3 sides by the Vito cells, which reject the interaction due to cosmic rays and gamma rays in the wall of the detector. So non-cosmic X-ray events are rejected. The detector is filled with xenon and methane at a pressure of 15-20 torr. So the advantage of AstroSat is the multi-wavelength observatory with visible near UV, far UV, soft X and hard X band, broad spectral coverage in X-ray from 0.5 to 100 kV with the instruments, large collecting area in 2 to 20 kV, greater than 6,000 square, and largest area detected for hard X-ray studies. Because at 50 kV, you can see it's a collecting area of 5,000 square for studying high energy, high frequency QPOs, non-thermal component, black hole spectra, so on. So here is a plot of efficiency versus energy for leg species. If you use all the photons from all the 5 layers, then this is the efficiency. You can see even at 50 kV, it's an area of more than 5,000 square. And of course, I have not shown you RXT, but RXT is a very shallow detector with 2.2 centimeter depth, and so adverse atmosphere xenon. Therefore, its efficiency is low. Now, depending upon the brightness of the source, we can choose for optimizing the signal to noise ratio from which layer we should analyze the photon. If it's a strong source, then you would like to analyze all the 5 photons from all the 5 layers so that you can get very high area and collect large number of photons in higher X-ray band. But if it's a weak source, like an AGN or distant source, which is a faint source with fewer Puru counts, then best is to use only the first layer or first or second layer, which will still give good efficiency below 20 kV, okay, and again above 40 kV, but the signal to noise ratio should be optimized. The other instrument on extra-set was soft X-ray imaging telescope, which is based on the using X-ray reflecting optics for conical files, based mirror, which was developed by Professor K.P. Singh at TFR, and uses X-ray CCD at the focal plane, which gives a very good resolution, energy resolution of about 0.6, 150 eV at 6 kV. And then there is a cadmium zinc telluride imager, which has a coded mask aperture and a cadmium CZTI detector assembly here with a cesium anticoincident shield. And it has a coded mask aperture, which is transmission of 50%, and which enables determining the position of sources to accuracy of few arc minutes. And UVIT, Professor Turnbull may discuss in his talk, so I will not cover. So here's an assembly, here's a view of the full assembly of the set before just sending it to SHAR. You can see the 3 XPC instruments, this XPC, this and this, these 3, the UVIT, SXT, and CZTI here. And X-ray monitor is mounted on the side. So what are the science goals of AstroSat? Periodic and chaotic variability in evolution of pulsar orbital periods in X-ray binaries, accuracy reading millisecond pulsars, and anonymous X-ray pulsars. This is important because it enables estimation of the size of emission regions, nature of X-ray sources, orbital parameters to inform mass of neutron star, the spin rate of neutron star, accretion targeting on it, and the ideas about magnetic field. The second task, detection measurement of low and high frequency QPOs in soft and hard X-ray bands in black hole, X-ray binaries, which enables us to study accretion process, innermost stable orbit of matter and the accretion disk. High frequency QPO study output constraint mass and spin of black hole. Neutron star and black hole binaries are violent variable sources in the sky, so variation in milliseconds, days and months. So a large number of X-ray binaries, both neutron star and black hole binaries, and also white dwarf binaries, have been studied the AstroSat so far in the last 5 years, and data are at various stages of analysis. Here is an example of a high mass X-ray binary, which is 40/115 plus 63, which is observed with AstroSat. It is a pulsar with 3.67 second period and 4.3 orbital period. So in this binary, you can see the light curve for 3 X-ray detectors, which are all operational in 2016 when it was observed. So you can see like XPC1, 2, 3, there is a consistency. And you can see that there is indication, it's not very clear from this, but power density spectrum shows it, that there is a variability on a time scale of about 500 seconds and 1000 seconds. There's a QPO of 0.5 millihertz and 1 millihertz, which is the first such example in a high mass X-ray binary. The spin periods of the neutron star, the various the pulsar neutron star in various binaries also been measured and studied, and they show all the spin up as well as spin down and all the kind of episodes. I'll not go into detail. Many results have been published. I just illustrate one recent result by Jaiswal et al. On the source called 4U1909 plus 07, which is a spin period of 605 seconds when it was discovered in 2001. And you can see that over the 15 or last 20-year period, there is overall trend of spin up, which is visible even the AstroSat point is here, new star data is here. So overall, although there is excursion here, so it depends on the accretion rate and also the torque reversal. One of the objectives of AstroSat was to measure QPO, detect QPOs at high energy. With RXT, it was not possible because RXT has very low efficiency, about 20 kV. So there was no results on QPO at about 20 keV. So here's an example of a black hole source called S1743-322 in 30 to 80 keV range. The power density spectrum clearly shows a QPO around 0.7 Hertz, and you can see the QPO is quite prominent about 20 keV. So this was one of the objectives of AstroSat, and it demonstrates the AstroSat capability. The spectra of the continuum emission from all classes of UV and X-ray sources, emission absorption features, medium range resolution, capability of A60, understand the complex multi-component energy spectra of galactic and extragalactic black hole sources to understand the origin of radiation from various processes, measuring non-thermal spectral components in accreting neutron star binary black hole binaries, supernovae remnants, and AGNs. These are the additional objectives. And of course, you measure the masses of neutron star and black hole by measuring the X-ray optical parameters of binary. One of the important objectives of AstroSat was to measure the magnetic field of the neutron stars in X-ray pulsars by studying the cyclotron resonance scattering feature known as cyclotron lines in the X-ray spectra pulsars. As you know, in the high mass X-ray binaries, the neutron stars have a typical field of 10 to 12 Gauss. So the electrons spiraling in the accretion column perpendicular to the direction of the magnetic field. Due to the strong magnetic field, the orbits get quantized, and then when the X-rays pass through, they get scattered. So you get absorption lines, scattered, resonance scattered feature CRSFs, which are known as cyclotron lines. And from this, one can infer the magnetic field of the neutron star with a simple correlation that the absorption line is related to the magnetic field by this relation where Z is the gravitational redshift due to the neutron star. So large number of the cyclotron lines have been studied in large number of X-ray pulsars. So far, there is a report about 34 of the X-ray pulsars showing cyclotron lines, and they all fall within band a narrow region of 2 to 8 times 10 to 12 Gauss fields. So AstroSat has also studied cyclotron lines, and I don't have time to go in detail, but they have been detected so far in 5 pulsars from which previously there was no report of such lines. There is an example of a line reported by Maroon et al. From a source known as 4U1538-52. So here's the Lex species spectrum, continuum spectrum which is observed. These are the data points and the line that's shown here. Best fit spectrum are shown here. And if you just fit only the continuum part of the spectrum, you will see that there is in the residuals, you see a dip at 22 keV. So if you assume that this is cyclotron line at 22 keV and include it in the fit, then the residuals is shown here in the bottom one. So you can see so this shows that the cyclotron line is real, and this cyclotron line is quite high, detected quite high significance level. So this is a new result. Then there is a well-known pulsar called Hercules X1. Hercules X1 is a pulsar with a spin period of 1.24 seconds. And this Hercules X1 was observed to show a cyclotron line around 40 keV by Trumper and colleagues from Germany in a balloon experiment way back in 1978. And subsequently, the cyclotron line was studied by a large number of satellite experiments, and it was found that the cyclotron line energy changes. For example, here from 41 keV, it dropped to 39 keV roughly during the period from over 2-year period, and then again it changed, and you can see that by the time of about 2015, the line energy has changed to 36 keV. And again, after 2015, when Stobart analyzed the data, he found that line energy is again started moving upward. And by 2019, it is reached already around 37 keV, and AstroSat observed it and has been analyzed by Bala, I think Bala et al. And published in binaries. Stobart has also analyzed it. That is reached a plateau of around 37.5 keV. So AstroSat has shown that the line energy can be measured quite reliably, and one can study the variation of line energy with the pulsar phase, 35-day cycle, the luminosity of the pulsar, and so on. One may ask that has the AstroSat performed so far its capability of fulfilling the science objective? The answer will be yes, illustrated by result from LexPC A60. And I will have no time to go into detail, but CZT has produced some very interesting results on the polarization of X-rays. One of these was, of course, the detailed study of hard X-ray polarization of Krebs pulsar, which has been published in Nature Astronomy. And this was a very interesting discovery. And it has discovered high level of polarization in the gamma ray burst, which was described by Professor Deepankar Bhattacharya in his review talk. So large number of such polarization has been measured by in the gamma ray burst, and at least in Krebs it is well established by CZTI. A60 has studied large number. A60's capability of producing X-ray images with a resolution of few arc minutes. I'll show you from one of the sources. And it produces beautiful spectra of and studies elemental abundances in stars and supernova remnants and so on. So A60 is also performing up to its is designed. So based on PV and GT phase observations, several tens of papers have appeared. I think so far there are, I understand, more than 100 papers. ISRO keeps a track of them on the X-ray results from LXPC, CZTI, CA60. And many more are coming in publication as data pipeline and this is software issues are gaining resolution. There are also multi-wavelength results. Several appeared in print and more are coming as described in detail in a recent talk by Gulab Devanga. Now, in the last, I think, how much time I have? 5 minutes? Shashi, how much time I have? Okay. In the last few minutes, I'll spend time on some interesting recent results on some of the binaries.
You have 5 more minutes. Yeah.
5 minutes, okay.
Yes.
So we recently observed an X-ray binary known as RX J10 3-7427, which is in the Magellanic Cloud region, the AstroSat, and we think that we discovered a new ultraluminous X-ray pulsar in the Magellan Bridge. This result is appeared in papers appeared in binaries last year, and Amar Dev Chandra is the lead author. He was at CBS earlier, now is at ICR Calcutta, doing his PhD. This source is very interesting because it was discovered in 1993 in Rosenthal Sky Survey by Kavaka and Elker, and they found that there are 2 outbursts in this source during 1993, October, one lasting for 40 days, another for 30 days, March to October period, and they're separated by a gap of 200 days. They identified is the optical antenna of the 14 minute B star and says that it could be a probably B binary in the Magellanic Bridge. Now this star after this was undetectable for 26 years. Many satellites looked for it and it was not detectable. So it went into a dormant state and suddenly it came back to life in November 20, when MAXI instrument, the Japanese MAXI monitor, detected it. Okay, immediately following the announcement by MAXI that they detected new source. They thought the new source, and they gave it in Maxi name. But saw then Swift looked at it immediately, and Swift XRD could determine the position accurately, and they identified it with this source reported by 1993, which we were active in 1993. And they also, the NICER observed it, and they detected 9.23 second position in 0.2 to 12 K band. So in AstroSat, we made a target of opportunity proposal to observe it. So it was observed during December 14 to 16, and about 160 kilosecond data obtained. So you can see an image of the S60 of this source, which is very clear and it's very beautiful scene. And you can, the advantage is that you can, see the image and you can construct a light curve from it. So the light curves are shown here in 3 to 5 kV from LXPC, 15 to 40 kV for LXPC again, and hardness ratio constructed from it. So you can see hardness ratio, how it varies as function of time. So in this result, light curves for 16 LXPC are constructed in 2 second winds to see the pulsation. And you can see these are the LXPC observation. These are the 60 observation. These is the LXPC observation. So you can see right up to highest energy. You can see the pulsar, 9 second variability pulsations can be seen very clearly. And here is the folded pulses. So you can see pulse shape remains more or less very weakly dependent on energy, same. But pulse fraction changes, low energy, high energy, as high as 55-60%. At low energy around 10 kV, but drops to about half the value at 60 kV. Now, since the LXPC is a large collecting area, so you could determine whether the pulsar period accurately, pulsation period accurately. So in 10,000 seconds. So here is a plot of the LXPC. This is the LXPC observation. These are the observation from government's burst monitor and Fermi, which monitors the pulsars at the bright. So the LXPC observations are shown in insert here. Now you can fit a polynomial to this curve and find residual after, of course, making the corrections. And you can see that there is a residual show a periodicity, and we think that this is due to the binary motion of the binary, orbital motion of the binary, which may be over 25 days, 20 to 25 days, but it remains to be confirmed. Then we measure the spin-up rate from the linear fit. So spin-up rate was found to 1.75 to 1.8, which is a factor of 1,000 higher than that measured in typical pulsar. This implies the accretion rate in pulsar in the outburst is about 500,000 times than in typical pulsar. So the estimated accretion rate will be 2.7 to 19 grams per second, which is satisfies the accretion rate threshold for formation of optimally thick accretion envelope, because the NH value in the spectrum of the fit comes out 10 to 23 hydrogen percent square. It may be noted that if you calculate from the best fit spectrum, one can calculate the flux of this source, 0.5 to 50 kV from a 16 LXT combined fit, which implies X-ray luminosity of 1.7 to 10 to 39 X for a distance of 60 kiloparsec in this agreement. So it is a super Eddington luminosity. So now this is the spectral fit, combined fit for S60 and LXPC, which is shown here. You can see that there is a power law component, which is a 2.18 spectral slope, and there is a black body component. So this is the best fit spectrum and this is residual. Now, before this, before you observe this pulsar, there are 7 ULSs which were discovered so far. The first one being the M82. Now, ULSs are earlier thought to be intermediate mass black holes, but discovery of pulsations from 7 of these objects, and the 8th one which we did here, the Rosette discovered source, which is in the large magnitude cloud, small magnitude cloud bridge is shown here. So you can see that the pulsar periods fall within 1 to 10 second range, and luminosities are 10 to 39 to 10 to 40 Hertz, and orbital periods, of course, is widespread. So this object, RxJ 209.6, is all the characteristic of ULX pulsar, and we think there is most likely a ULX pulsar in the Magellan Bridge. SOSET has also observed the first galactic. There is only, of all these 8 sources, only one source, ULX's Swift source, this Swift source, which is studied by Baird et al. With SOSET, is in our galaxy, otherwise all are extra-galactic objects. So the Baird et al. Is studying in detail the positions and the spectra of the source. I will not have time to go through detail, but SOSET has produced interesting result on this. Most recent result is on an object which is, we think, is a magnetar, and you can see that the magnetars are neutron stars with a magnetic field of 10 to 14 to 10 to 15 Gauss, and the most important, most outstanding example of magnetar is SGR 1806-20, which is a soft gamma ray repeater, which underwent a gigantic outburst. So much that energy released in 0.2 seconds was 1,000 times the velocity of our galaxy. This magnetar SGR 1830-465 was observed in SOSET, and TO again, target opportunity observation. It was discovered by Baird and Swift, and initially thought to be a gamma ray burst, but the NICER showed that there is a 10.4 second oscillation in the position period. So it became clear that it's not a gamma ray burst, but except pulsar. So few observations are made at SOSET for total exposure of 249 seconds. And you can see that curve here. An important thing, I don't have time to go in detail, is the discovery of millisecond X-ray bursts. One of these bursts is shown here. This burst lasted for about 40 milliseconds and saturated the detector, counted as so high, the detector was saturated. So it is this burst released a counted of 1.6 into 10 to 4 counts within 2 milliseconds and saturated the speed detector. So it is most likely a rare giant soft X-ray burst detected in this new magnetar. Total cumulative count observed during this burst was 560 counts in theoretical in event, and duration was 35 milliseconds. To our knowledge, this is the strongest soft X-ray burst detected from this new magnetar. The best fit estimate the spin down rate is this. All magnetars show spin down. This is consistent with this, and pulse fraction is 30% and 24% low and high energy. So you can see the plot on a time scale. You will see this burst appearing here. This is also now verified from NICER. NICER burst is shown here, and the Lex burst is shown here. And pulse profile for the soft gamma ray repeater, which is magnetar, is shown here for the soft A60 observation here and NICER observation here, Lex observation here. They appear similar. And the spectrum is fitted with a power line and a black body model. So, this is most likely a new magnetar. So we wrote a paper and submitted to MNRS note later. And within 15 days, we learned, and these are from literature, that a similar paper was submitted to FJ later by American European group, which was published very soon. All people went to referee, and it was paper is under revision. So although we could not get the credit for discovering it first, but I think almost discovered around the same time. So I think with this I will stop, and if you have any question, I will be happy to answer. Thank you.
Yeah, thank you very much, sir, for your very nice review and the historical aspects, and that how did we evolve all the way from balloon-based experiments to AstroSat, and now we have many extra payloads on AstroSat, which it is very clear that the very remarkable results have come out, and it is continues to be like this, and hopefully in next few more years we will have many more new discoveries. So it's time for questions. 1 or 2 questions could be taken up. So questions, please.
Well, the Shyam Tandon here. Shyam Tandon here.
Yeah.
The last point you made, Pralaji, that you were delayed in publication. How much was the delay which costed you credit?
Well, I think we submitted and they submitted immediately probably, and they got accepted within 15-20 days.
I see.
Yeah.
So it was just question of acceptance, which okay. All right, thank you.
Hello, sir. I would like to know if various instruments on board AstroSat can be operated independent of each other. That is, different instruments could be pointed at different sources. Is that possible?
No. The 4 instruments, LXPC, 16 UVIT, and CZTI, they are all co-aligned and mounted on the top deck. So it is not possible to, independently orient them. They are not independently orientable. You can make only simultaneous observations.
Okay, sir.
Yeah, any other question? Yeah, if no more questions, then we extend our sincere thanks to Professor Agrawal to deliver this talk about AstroSat. Now it's time to move to the next talk. So, sir, please unshare your screen.
Yeah, I'm doing it.
Yeah, so now it's time to hear more about AstroSat, and one of our very senior scientists and instrumentation experts, Professor Shyam Tandon, is there with us, and he has been pioneering throughout, all the way from detectors to instrumentation to telescopes in the country. And today he will be talking with us about UVIT, ultraviolet imaging telescope on board AstroSat. It's primarily because of Professor Tandon that we are enjoying space-based optical infrared data, optical ultraviolet data. So, Professor Tandon.
Yeah, I'm there. What should I do? Share. What should I do? I share screen, right?
Yes, sir.
I have 2 screens. Just share screen. I put share screen.
I'm sure.
Something happening here. I don't know.
No, sir. You again try.
I see 2 things here. See, I see something. Okay, close this. Something white. I see. All right. So share screen, right?
Yes.
I'm sharing it here. Oh, many things are there. I see. Okay.
So you have to share that where the PowerPoint presentation is there.
Yeah. I have to find that. Yeah. I understand.
Scroll down.
Now you see something?
Not yet, sir.
Not yet. So this is open.
Click that box and then click share again. Share then.
No, I see. Okay, Annapurni. Share screen, but then I see a lot of things. I see you also there. My talk is somewhere down. When I open that, something has happened. Yeah, I line there. My talk is there. When I open that, that is not coming there. So let me try now. No. Yeah, some complication is there. Okay, share screen now.
Please select the window in which the talk is there, and then there's a blue button at the bottom.
My talk is I open on the screen. Is it okay?
Not yet.
No, my talk I open the screen.
Right. Then in Zoom you have to share. Click.
Zoom I say Zoom I say share screen. I say
Then you select.
But then something else. Oh, now then something must be. Okay. It's coming now. No.
Then you click on that. Then it will become blue.
Yes. I'm trying to click on the.
Yes. Now
Yeah.
Perfect.
Yes, sir.
Oh, you get something.
Yeah. Now it is there. You go now in full screen mode.
Yes. Yeah. Is there?
Yeah. Yes, sir. Perfectly fine.
Yeah, you got it.
Okay, thank you. First of all, I want to thank the organizers for inviting me to give this talk. And I will describe about UVIT. So the plan of talk is like this about AstroSat. Professor Akbar already gave you some introduction. I will very briefly mention these things. Then making of UVIT, observing the UVIT and its performance, and some results. I will give only few results. My idea is not to give exhaustive list, but just to indicate what kind of observations can have been made to exploit its special features of UVIT. So I will come to that. So only a few illustrations. I won't give many illustrations there. So we have an old tradition of astronomy from above from high atmosphere with balloons, which were also used for X-ray astronomy in 60s and 70s. And the X-ray astronomy satellites itself started in 1975. Actually, the very first satellite where India had some payload for observing the sun. Then, of course, 1996, X-ray astronomy payload was there, IXAE. In IRS P3, there's some long name is there. And that was a good success, actually, which I think Professor Agrawal already mentioned in some details. And after this success, there was thought that we should go for astronomy from space, particularly the X-ray astronomy, which had very serious limitations if we stuck to the balloons. And that started led to thinking of when the ISRO and elsewhere and with the astronomers, how to go about designing and setting on a satellite for space. Now, what was decided by the X-ray astronomy will be the main theme of such a satellite. Am I audible okay? Hello?
Yeah.
Okay.
Yes,
and then of course the idea was that we have multi-wavelength coverage, so we want to cover the long wavelengths also compared to X-ray. So UV wavelengths are included in that. So we have the UVIT along with the many X-ray payloads on the satellite. Now the UVIT itself is a twin telescope, 40 centimeter aperture each, and we simultaneously observe in 3 bands. One is called far UV, the shortest wavelength, the near UV, the middle wavelength, and visible. The visible wavelength is only for tracking the satellite. It is not actually for proper observation. So we should keep in mind that actual observations are being done only in the far UV and near UV. And its mass was about 200 kg. So there's some kind of specifications meant for that. So it has 3 bands I've already mentioned. So far UV is 125 to 180 nanometer. Near UV 210 nanometer. And visible 320 to 550 nanometers. And for in each of these bands, there are some filters which can select a part of the band for whatever regions you may have, science or other regions. And then we also had some gratings near the detector, essentially where you put the filters. To give slitless spectroscopy for bright objects, and I will give examples of that. It's not been used very much, but some observations have been made with that. Now, field of view is 28 arc seconds, and resolution is better than 1.5 arc second. FWH is better than 1.5 arc second. So this is a very important feature of it. And sensitivity, finally, what we obtained is about magnitude 20, AB magnitude 20 in far UV. It means something, but sensitivity is about 1/2 of what Galaxy had got. Look at it. Now, I have already mentioned, but why we are visible? Visible is not used for actual astronomical observation. It is only to find the position of the satellite. The satellite is actually drifting. It drifts a lot. It can drift by 1 arc second per second, can drift by up to 20 arc seconds, 15 arc seconds. And then if you make a image, you will not know where you're looking. So for every second, we should know where we're looking. And the only possibility was the visible photons. Visible light, there are a lot of photons. You can make an image in 1 second with this kind of telescope, but not for UV. So we have to include this visible channel for tracking the pointing. Remember, it is not for astronomy. So this is a kind of a drawing of the telescope, rough drawing. So you can see these baffles or tubes. Something happening here, yeah. Secondary mirror is here, primary here, so light will come like this here, go back and come to this tube in the primary hole. And here you have the filters and detectors. Primary mirror, secondary mirror, detectors and filters, the baffle to minimize light, and the doors are there. The doors have two purposes. One, to isolate the instrument from everything else in satellite, which can contaminate the optics. So the UV optics is very sensitive to contamination. Even monomolecular layers can damage the thing. And also when you are in the orbit, the sun should not fall in the baffle of sun has a lot of UV light that also can do some damage. So the actually sun shield also. So sun is always behind the doors. That's how the observations are made for when you say astroset. Now, before I go further, I will just mention the collaborating institutes. We IIA, International Center for Astronomy and Astrophysics, Tata Institute of Fundamental Research, and many centers of ISRO which give various kind of support, and then Canadian Space Agency. Now, I given actually how it made the making of this, making of UVIT, and here we started something like 2002, 2003. We started making the agreement between ISRO and CSA, and actually formal approval for AstroSat was the 2004. It's a government approval, and then of course it will launch in 2015. And I should mention that one detector has failed in 2018, the near UV detector. Same thing will happen. So now we have only for astronomy only far UV detector. So let me continue further. So this just to repeat how the UVT looks. So primary mirror here, secondary here, filters and the detector here. One is for far UV, other is for near UV and visible. And you can see in the optics this thing. This is optic 380 millimeter, 390 millimeter mirror. Secondary mirror here. This is about 1.2 meters. And this far UV, you have the filters here, detectors. So filter very close to detectors. Filter, of course, grating is also there. For near UV and visible, with the near UV comes here, visible is here, and the two, this looks bigger, of course, in this figure, but they are identical actually telescope, same diameter. It's not bigger here. It's an error of printing. Now, to give you an example, I mentioned that the filters to select part of the band. This is one example here. To go to far UV, they're basically low pass filters. So you have one filter here, and the rear, and the 140 nanometer, and this is 120 nanometer, 130 nanometer, 160 nanometer. So the different filters are there. And suppose you want to, one of the points about this is suppose you have some line here, emission line here. Then if you observe in this filter and this filter, you could make sense of how much is flux in the strong emission line. And it has been used like this for at least one source. I will come to that. Now I'm not showing a near UV filter, but they are mostly band pass filters, and the far UV filters are low pass filters. So you mentioned the detectors. This is pointing. I mentioned pointing, drifting a lot. So you have to take image very fast. You can't take an image for 1 second. So you take fast images every maybe 100 milliseconds or faster or something like that, and then add by shifting algorithm, which means you expose a very short. The image might have only 1 photon, less than 1 photon for some sort. So the read noise should be negligible. So with that requirement of read noise being negligible and imaging frames short, we are stuck with photon counting detectors, which are nearly zero read noise. So remember, the instrument is almost zero read noise, as well as dark noise is also very small. So you can take very long exposures and keep sensitivity. Now, the other thing was black coating is common, but here the contamination demanded that the coating should be inorganic. So there was some development at ISEC. Now the URSCF, ISRO, they did it further. So we have all the black coating inorganic, not organic, which means paint. Typical paint is not used actually. So there was, I already mentioned, the paint is inorganic. So there's a lot of concern about contamination. It can come from any plastics used inside or any epoxy, etc., used in the telescope, or from within the satellite itself from other instruments. So there was big program for this. I will not mention it, but the huge program for this, special laboratory made, special arrangement made, and a lot of work was done on that. It is one of the more difficult parts of the project actually. But it was all done very successfully, which you will see by the fact the sensitivity, we got expected sensitivity without any problem. So that was done, and so it is all ready, and we have to go for launch. So let me say something how to observe with UVIT. So the same thing as to say, the proposals ask for every once in a year. The time is gone, unfortunately, 1 month back. So this talk is probably late by a month. Then there's what is good target of opportunity. So wherever something unexpected is happening in sky, you want to see it, you can apply for observing it. Then for calibration, the instrument people apply for calibrations whenever they want it, typically a few times a year. And then the data arrives at the ISSDC center of ISRO. And then from there, PUC, after some processing, it comes to PUC at IAA, where it is further processed to get a final images. And the images are transferred to ISSDC again for dissemination to everybody who is concerned with that. So let me start with how observation started with the UVIT. So it was September 28 was the launch, I think. Then we had to keep the doors closed for 2 months to make sure there is no contamination from the satellite into the UVIT. So the door is opened on November 28th, 2 months after the launch. And we arranged whatever we wanted to do actually, and there was big drama for 2 hours. We had big trouble actually. Nothing came for the first time, then something else happened. Something called BOD means it appears something very bright appeared in the field which should not have been. But mercifully everything solved in 3-4 hours, and we were happy to get some image. This is not the image first we saw after opening, but there was early images. So now this I should like to explain. This is long-term image, and you can see each star has become a trail, funny crooked trail, and that is because drift of the satellite. So this is actually 2 or 3 hours total, a lot actually. So you can see why we have to take very short exposures and add them by shift. And after, so actual exposures are each one only 30 milliseconds. Only 30 milliseconds. And if you find the aspect every second or so with the visual channel, and then make correction for the drift, we finally got such an image. One of the early images, so you can see much better than that. And I think here the size is probably 2 arcseconds or something like that of the dots you see the star. Am I audible still? Hello.
Yeah. Yes, sir. Very much.
Okay. And how many minutes have gone?
Still, you have, sir, around 15 minutes to go.
Okay. Very good. So now, as I said, I'm not going to give an exhaustive list of observations made, so I will not give any number of observations, but it is in hundreds, some hundreds of targets to be observed. So I will concentrate on examples to demonstrate the image quality and how it can be used. The sensitivity 0.22 is 18.1, as I mentioned earlier. The stability of photometry has been very good. I mean, we have not been able to see any change in the sensitivity. And it's certainly less than 3% over 4 years. So very stable photometry is there. So any long-term time variations can be done with this very well, I suppose, if somebody doing it. These are UV channels. So distortion in the final images, which define the linearity of the scale, is less than 0.4 arc-second through the field. This is very important when you are looking for objects in crowded field, and you have to match with the visual observations or X-ray observations or something else. Unless you have very good positioning, you can't match very well. So for very crowded fields, it's very important thing. The flat field variation is only less than 10% finally, which is good. Other thing is that the dark current and noise are almost negligible, which means you can take very long exposures, and you see some examples, tens of thousands of seconds, and retain the sensitivity. No problem. Of course, you can have the dark, you can have the sky background, which varies. Near the galactic plane can be very large, and at large latitudes, very small, but that you can't help. So this is the PSF issue. I don't know whether you can make much sense of it, but the units are very strange here. The square of the pixels, of the square of the radius in pixels, each pixel is about 0.4 arc-second. I mentioned FWH 1.5 arc-second, so which is about 3.5 pixels. So here, I think somewhere here, this is about, I think, two pixels or something like that, or maybe less than 2. This square of the pixels is a little odd, because the way the graph is made. Okay, this is the flat field. So you can see that 1.16 here, which is, if you see this red thing, supposedly 1.16 is the extreme edge, and the blue here is about 1 point. So this center, which is normalized to 1. So it goes from 1 to about 1.16 or something like that, the far UV. In the near UV, it goes from, it's 0.94 about, something like this here, less, to about 1.1, you can say. So it's a much better 10%. So the flat field is quite good. The other filters also, there's only 2 filters, in the far UV and the near UV, but they're all very similar. Okay, so now I come to reality to illustrate. So what do we want to illustrate? Firstly, what you could do with a good spatial resolution of less than 1.5 arc-second? And what is the low dark noise? How would it help you? You take very long exposure, so I'll give you an example of that. The linearity of scale, which I told you, crowded field, it works, so I'll show you that also. Then the differential between the filters, as I mentioned very briefly earlier, can be used to assess how much is the emission of bright emission lines in some source, which is. Then spectral information of slitless spectroscopy. That also I will show you one example. So we'll start with that. This is from Kameshwar Rao. I got this, N.K. Rao. And here it essentially one of the important results is there is hydrogen cloud somewhere here, extending up to some arc minutes in the planetary nebula. So how do you find it? They find it by you compare this and this. These are far UV filter. One would carry the lines which may be from H2, but other will not carry. And the differential shows you that the hydrogen lines are there, and hence hydrogen cloud is extending in this direction. An example where the near UV filter and is compared with other filter near UV, one can conclude that the C2 line is strongly present in this extension. They can see C2 line is probably known, but they can find this distribution from this imaging with this resolution. Now here the image for that hydrogen cloud. So this is the red brown thing. You see that the hydrogen cloud for the infer, and here is the H alpha contours here. So they can detect hydrogen cloud in some sense, and they are very happy about it. They just to demonstrate the maybe the resolution of UVIT. This is of course Hubble image, and some of the sharp features Hubble dots can be seen by at least Kameshwar and party have seen these things. So it just illustrates the resolution. Now I will come to cloud clusters, which have a big concentration of stars. So you can see usefulness of high resolution. And when you go to UV, there are not that many stars. So the point is that given the high resolution and the fact that there are not so many UV stars, you can see individual stars and find their property. Unlike visible, where you get stuck somewhere in the boundary of the cluster and you can't go to the center. Here you can see, you can go quite deep in the. You can see one example here. You can also see all the stars actually. Near UV, the green, the blue is far UV. So it just the so the advantage, you can see all the individual stars, and then you can infer a lot more than what you can see the collected property. This is just a magnified version of the previous slide. So now the results, they brought the few results which I have collected. Here they are finding the UV stars. A lot of UV stars are found in this. What is the number of this? Something missing here. What is happening? Okay. So this is a global cluster. The name, I don't, what is happening? Here the name somewhere. No, I can't see name. Name is hidden there. Anyway, they find a lot of UV bright stars. I told you, you can see individual stars. Each star they can measure the UV flux and infer what it is like. Then the variable stars, they found the many variable stars, and one of the important conclusions they draw is the longest period variable stars are the weakest. Okay. So there must be observations of many days. Find this thing. Extreme oriental branch variable stars, the longest period are the weakest. So you can see they have seen individual stars. I mean, that's the point about that. Now I leave that. Now the interacting galaxies, star formation in interacting galaxies. So this is from Cauchy et al., George Cauchy et al. All the slides. Now this is one the famous galaxy, the atoms of peace. See this image, and you see here, this is the UIT image, and you see a lot of all these formations here, star formation. And some of these dots here, they are as big as dwarf galaxies. So in the interaction, you're creating dwarf galaxies, or creating either by breaking or making new galaxy. So now the same galaxy near the center, one can see a ring of UV stars, blue stars, which means the recent star formation has been there after the interaction near the center also in the galaxy. The other galaxy is called something, I don't know. Some names are there. So J0201. So here this slide is showing that this galaxy in a cluster of galaxy, and the gas is being stripped from the galaxy, and so there are a lot of activity. But so here you see star formation activity, but this is the center, the active center, and here there is a gap. So the idea is to say that the active galactic nucleus gives a feedback such that the star formation is blocked. It doesn't occur. Although you see a star formation here, but not here. So the active galactic nucleus tends to block star formation immediately in the neighborhood. So I'm done with that. Now I come to this interesting galaxy, which is at residue about 1.4, very faint galaxy. In the observations have been taken over 60,000 seconds. 60,000 seconds. They were mentioning, and the very faint galaxy. And when you want to compare the HST images, for instance, so you want to find out where the image matches with the HST source. So you need a very good ultimate estimate should be very good. That's where the importance of 0.4 arc second linearity comes in. So unless you do
minutes to go.
Okay, unless you do that, you can't be sure that you are looking at the same galaxy. So finally, the interesting thing about the galaxy is the 1.4 redshift, and then it has a Lyman continuum emission. So this is the first galaxy in that wavelength, Z range, which is being seen to emit Lyman continuum. Okay. Okay, so now I come to this thing which I know least about. See the measuring black hole spin of Farrell so and so with the associated UV X-ray spectrum. So one is able to measure the the black hole spin by combining all the spectra, the UV spectrum, UVIT, and the fit is there, and then they are fitting the UV spectrum and the X-ray spectrum, taking the SXT to the possibility of the various spectrum, and spin value the optimized. So they find some optimal value, spin and see, and put error bars on it. So it's very interesting. By UV spectrum, they use found the spin of the black hole. Now this is UVIT observations of this galaxy, constraints on the accretion disk inner radius. So what is this? Is the UVIT image, far UV here, near UV here. Then they near UV, they put radial distribution and then make it fit. So this line you see here, this is the fit to the emission of the nucleus. And what is here, this is for the galaxy. So this is what they use to find out what is the continuous accretion disk. And on that, basically they conclude the accretion disk only extended to so much radius, not up to the maximum limit to the black hole. Some numbers are there in the slide, but I will leave it at that. I only very short time left. I have one more thing to show. This is the temporal variation of UV and X-ray. Okay. So you see, this is what this same thing shown here with some filtering. So the first thing is the near UV, far UV and near UV, they're leading X-rays. So X-rays, near UV leading X-rays, near UV leading, so near UV, near UV, so far UV, near UV. I'm getting a bit confused now. I think the X-rays are here. The X-ray probably is here. And SXT near UV, far UV near UV, and SXT far UV. They compare. And the conclusion is that the near UV and far UV they lead the X-rays, and near UV lead the far UV, which is near UV is the first in time variation, then far UV, then X-ray. And that is the implication on the mechanism which is giving time variation. And in fact, the idea of AstroSat for having all this was multi-wavelength multiple observation. And this is one fine example. And actually last two also I showed to you. They are good examples of multi-wavelength observations with AstroSat. Okay, thanks. I will stop here. Okay, I have stopped. So if you any question, otherwise I can talk something more about these things.
Yes, thank you very much for your very nice overview about how the ultraviolet telescope onboard AstroSat evolved and what kind of difficulties we faced and what kind of results are we getting. So it's very exciting to see all these. And with these remarks, I think audience might have a lot of questions for Professor Tandon.
The audience is very quiet. Huh?
Yeah. Audience?
Yeah, Shama, this is Annapurni here.
Yeah.
Yes.
Just one question. So when during the making of UVIT, was there at any time considered to have a different detector for visual than the one which is identical in the far UV and near UV channels?
You know why we did a CCD as an example?
Yeah.
Yeah, it was just to minimize the technical effort. Identical things help a lot. Basically, we never considered photometry or anything like that. Other thing is, I don't know whether read noise will matter. I want to check on that. But typically, I think my estimate is about 30 electrons, 30 photons are good enough to be detected with this good signal to noise ratio in the visible presently. Now with CCD, we would have got more efficiency, of course. Maybe it was possible. I cannot say.
Yeah, I mean, basically reduce the complexity. It was decided to.
Yeah, basically that was the idea, and we never considered. But if it was a serious issue to get photometry, maybe it would have been different. Yeah.
Yeah. Right. Yeah. Okay.
Yeah, Mr. Abhay.
Yeah, sir, you said that for 2 months after launching in the orbit, we had to keep the UVIT enclosed, I mean, not open to the first light. Is there some reason? Can you explain us that?
Yeah, you see, what happens is that if you go to what be far UV, that is about 1500 angstrom or 150 nanometer wavelength, a lot of organic materials, even monomolecular layer, can block 50% of light, and there are 4 or 5 surfaces, so we will get nothing if it happens. Now, there's some control. UIT, we had a big control. It's a big program actually of avoiding any contaminants which will emit the molecule deposit. Other payloads also had, but not the same extent. So idea-wise, when the asteroid goes up in the orbit, the others, they will evolution of all the molecules and they will go out after a month or two. This is very common actually in space astronomy. So we were expecting that after 2 months, the asteroid will be clean in the sense that it will not be giving any molecules which will spoil our optics. So we kept it isolated. So to avoid any deposition of molecules which come out of a lot of water comes out, for instance. That is known, of course. But it was just a precaution. I cannot say that it wouldn't have worked the first day. It's not possible. It's a precaution.
Okay, sir. Thank
So,
you. Yeah,
since
yes,
nobody
sir.
asked a question, let me just explain the slide.
Yes, yes, sir.
So in this peculiarity there of UVT, it works in photon counting mode, as I explained that we have those detectors. In whatever in one frame, if you happen to have 2 photons, we can look at it only one frame, one photon. So saturation is a very serious matter. It is not like CCDs where you collect and then reach the limit. So if you have a functional counter rate in any object of say 5 per second, and you're taking 30 frames per second, there is some amount of saturation because some frames will have 2 photons nearby or in the same spot, and then you'll count it as one. That's the limitation of technique. So saturation is something very different from CCD, and you can't have a very strong source of observation. And we have some flexibility there. You can take frames faster. You can take frames every 3 milliseconds, 4 milliseconds, if you have stronger sources. But this S2 captain is an issue which people don't understand very easily, as I'm mentioning. Then any bright object can damage the photon counters. Too much current may go through the high voltages. So that is an important issue which has been tackled, and we keep on working on it. But people don't understand. Always there's some difficulty when they make proposals. There's some little bit difficulty. These things make little difficulty in proposal making. And of course, so selection filters from the same point of view. If you have a very bright object, you will not be able to good signal, useful signals. And so there have been some. Yeah, I mentioned these things are not very well understood by the community. So I'm mentioning some attention has to be paid for these things for making proposals. Maybe we have not been very clear probably explaining these things, but the peculiarity which have to be understood to make good proposals. Okay.
Thank you, sir. Thank you. Girish has a question.
Yes.
Girish?
Professor Girish here. Professor
Yes.
with your experience of UVIT, the realization, designing and everything, if you are asked to redo this, so how differently you would like to do, like make a UVIT?
Okay, firstly, I will decide that I am not making in 3 years. Whosoever tells me this thing, I will just ignore it, totally ignore it. I will go to make it in 6 years or 7 years. So I will have far UV detector which will twice as efficient at least and better resolution. Okay. Now anything else, I will be better person with our colleagues, I think. So it may help, I don't know. But not too much different, I think. I think maybe we will have different optics support. The mechanics will be slightly different. It will not be like what we have now. It will be different mechanical thing. Detectors, I think they're all good. Maybe we'll change the. You see, detectors, electronics had not the best grade of components. So maybe we'll change that to space grade. So if that way there, maybe the near detector wouldn't have failed. And lastly, I will have everything spare in pocket, which we did not have actually, and we had a lot of problem. We had 2 years delay because of that. Because on the ground, one visibility detector failed, and we didn't ready spare. So it took 2 years to get around that. So I will keep all the spares for those. So for you to get. I think these are the basic point.
Thank you. Anything regarding science, like photometry?
I know people say that if the demand is, it is demand. Customer has to demand, no?
Okay.
Demand, no, yeah, demand is because we were actually with the detector field, we're thinking of getting a CC detector, CMOS detector from SEC for visible channel. So you're right, it can be done with that probably. Can be done. We could probably, maybe, it would have worked. We would probably CCD. Yeah.
Thank you.
Thank you very much, sir. If no more questions, then now it's time to adjourn the session. But before we adjourn, we have a small announcement where in ISRO, there is an opportunity for research fellowship for AstroSat data utilization. It's up to 3 years of project, and PhD students and JRF net qualified are encouraged to apply, and submission date opening is just 12th of April, and last date is 10th of May. And for any further details, what kind of fellowship and what kind of data usage and so on is there, V. Girish could be contacted, and in fact, he himself asked to announce it. So it is announced, and with this short announcements especially for younger generation, it's now time to say thanks to all the eminent speakers and participants who participated during this pre-lunch session. So I extend my hearty thanks to all of you. And with these remarks, now it's time to have a lunch break, and let us gather again at 2:30 for the post-lunch session. Thank you very much. Okay. Next. Yes. 229.
Shashi, can you hear me?
Yeah. Hi, Girish. Good afternoon.
Hi.
So, good afternoon, all. Welcome to the afternoon session. And the afternoon session would be chaired by Dr. V. Girish from ISRO headquarters. So now I request Dr. V. Girish to please chair the session.
Thank you, Shashi. Thank you. Welcome you all once again for this afternoon session. This afternoon session has totally 5 presentations, each of 30 minutes duration, 20 minutes for, I will actually ping after at the end of 20 minutes. So the five presentations in the afternoon session covers a wide band like astrosat, gamma ray to radio, 2 extremes of the electromagnetic spectrum, including optical and IR. So at the end of 20 minutes, as I mentioned, I'm going to inform the speaker. Let me start with gamma ray astronomy. May I invite Dr. K.K. Singh for delivering his talk. Dr. Singh, floor is yours.
Girish, so it's a 30 minutes, so 25 plus 5 is the distribution.
Yeah, that is for the medicine. I said that at the end of 20 minutes, I will inform them.
Yes.
Hello.
Yes, Dr. Singh, we can hear you.
Okay, so I have to share the screen.
Yes, you have already shared the screen, it looks like.
Okay.
So please put it into full screen mode.
Okay. Now it is okay?
Yes.
So a very good afternoon to all of you. Let me take this opportunity to thank the organizing committee for giving me this opportunity to speak on the gamma ray astronomy with imaging atmospheric Cherenkov telescope. So I think that today's session is basically dedicated to the observational facilities in India. So I will be talking about the gamma ray astronomy, in particular the ground-based gamma ray astronomy, using a state-of-the-art technique called atmospheric Cherenkov technique. So my presentation will be in 2 parts. First, I will be giving an overview of the gamma ray astronomy program. Then in the second part, I will focus on the Indian perspective. So Indian perspective means again only on the ground-based program what we are doing. So as we do any astronomy, so there are some questions in our mind that we want to address. So the first question is like the basic questions in the gamma astronomy are twofold. So first we want to know what is there in the universe. Once we know some source is there or some object is there, then if there is something happening, what is the physical process, how these things are working there. And to know those things, the universe is constantly communicating to us through various means. Like they are coming, that signal is coming in the form of wave. It can be the electromagnetic wave or the gravitational wave, or directly particles in the form of protons, electrons, and neutrinos. And then they carry some masses. So what masses they are giving is like that there are different types of sources in the universe which are giving these signals, and then different physical process happening in different sources. And then if we have the different messages from different sources, is there any possibility if we can do some unification and okay, these are the unified process which are happening throughout the universe. So for this, we want to get some data, we want to get some observation. So we need different types of instruments. So in the present era, we have entered in the so-called multi-messenger era or multi-messenger astronomy, where a large number of instruments worldwide are continuously monitoring the universe, and they are giving different types of data from space-based observations, from ground-based observations. So this at the present, so we have three types of observations. We have the electromagnetic spectrum observation from radio to gamma ray, and then we have recently this gravitational wave observations coming. So we have another addition to the observational astronomy, and there are some neutrino observations. So there are three signals coming from the space, and there are some common things in all the three. So if we can get these informations simultaneously, or we can combine these informations at different times and do some physics. So here I will be just because it's gamma astronomy, so I will be focusing on the highest energy window of the electromagnetic spectrum, which has not been fully explored so far. So these are the astrophysical gamma rays, which constitute the high energy part of the electromagnetic spectrum. How they are produced, what is the information they are carrying from the sources from different sites in the universe. And there are different sources already which have been identified, like supernova remnants, pulsars, active galactic nuclei, gamma ray bursts, and some unknown sources like dark matter and other things. So there are some basic physical processes that we know, like bremsstrahlung. If they are producing this non-thermal process which can produce gamma ray photons, or the synchrotron radiation by relativistic electrons or protons in the presence of magnetic field, or some other process, some called the inverse Compton process, inverse Compton scattering, where the high energy relativistic particle can Compton scatter the low photon so that we can get high energy photon, or some other process is hidden there that we don't know. So to identify the physical process and do the further physics, we have the gamma ray astronomy program now coming up, which is basically a recent addition. If you compare with the other astronomy like optical astronomy and X-ray astronomy, this is very recent addition to the multi-wavelength astrophysics. And because of its neutral nature, the gamma ray photons do not experience the presence of any magnetic field or electric field in the universe. So they can be used to directly probe their sites or their sources in the extreme environments in the universe. And if to understand the physical process, how they are emitted, then we have to understand the radiative process in the high energy density plasma, and if how these relativistic particles of plasma, how they are relativistic particles are produced. So we have to understand the relativistic particle acceleration, which is not known and is an outstanding problem in astrophysics. And if we talk about the like active galactic nuclei, where there is a supermassive black hole at the center, and then along this relativistic plasma coming out of it. So what is the connection between the black hole and the plasma coming out of those? And these are the prime sources for gamma rays. So these gamma ray observations can be used to understand this phenomena. And in the high magnetic field regions like pulsars, how these gamma rays are produced, or in the strong gravity systems like binary systems. And if these gamma rays are traveling over cosmological distances, if they are being absorbed on the way to the Earth, or they can travel without any attenuation, if they are absorbed, the main process is the presence of extra-galactic background light, which are low energy optical and IR photons, which interact with the high energy gamma ray photon, and there is a pair production. So high energy gamma ray photons are absorbed on the way. So these are the processes which can be addressed by doing the gamma ray astronomy. And if we look at the gamma ray universe, so daily there is some sources in flaring states which is continuously changing, and there is no upper limit. With the advancement in the observation, the high energy of the gamma ray photons which is observed, it is continuously increasing. So there is no upper limit defined. So the gamma ray astronomy, yeah, it is basically done in two parts or in two ways. We can do directly from the space, or we can do from the ground. So most of the gamma ray sources, when producing these high energy photons, the distribution of photons is basically described by power law. So because of the power law nature, that means at low energy there is high flux, and if you move at higher energies, you will have lower flux. So if you have low energy in low energy range, we have high flux. So it is possible to have a small detector or small collection area, so we can flow in the uh, in the space, that means outside Earth atmosphere, and directly detect the gamma rays. But as we move for high energy part, then the flux of gamma ray photons, because of the power and nature, significantly decreases. So it is very difficult to move very large detectors in the space. So we want to do from the uh, ground. But the high energy gamma rays, they don't directly, unlike the space detectors, they don't directly come to the Earth atmosphere, but there is some another indirect method which can be used to probe to do the gamma astronomy from the ground. So when the Earth atmosphere is constantly bombarded by the high energy gamma ray photons and the cosmic ray photons, so they are basically absorbed by the presence of atoms or molecules in the Earth atmosphere. And there is something called production of extensive air showers. So that means particles are lost in that Earth atmosphere. The secondary thing is originating, that is the extensive air shower. But if we get some information, if we can detect the signal coming from these extensive air showers, so we can get the complete information about the primary particle. So just to have an idea, if one gamma ray is coming, so parallel to that, there are 1,000 cosmic ray backgrounds are coming. So that means if we are there is one gamma ray shower produced, simultaneously there will be around 1,000 hadronic showers produced in the Earth atmosphere. So if we want to detect these showers from the atmosphere, so the Earth atmosphere is now working like a tracking system or the calorimeter or detection medium for us. And because our detector will be on the ground, and only thing which can be used as the direction of these showers. So cosmic ray showers are isotropic. They will be randomly coming from any direction. And whereas the gamma ray photons, they will be coming from a particular direction. So if we keep on counting gamma ray events from a given direction for a long time, then certainly they are going to dominate over the isotropic gamma ray background. So that is the basic thing where this gamma ray astronomy works. So when the extensive air showers are produced in the atmosphere, so it is basically this is the textbook problem, how this extensive air showers are produced in the Earth atmosphere. And when they are produced, then this is basically the shower of charged particles. And when these charged particles move with a velocity which is more than the velocity of light in vacuum, then they produce something called Cherenkov light. So if this Cherenkov light can be detected from the ground, produced from the essential air showers, then we can do the gamma ray astronomy. So that's why we are not directly detecting the gamma ray photons, but we are detecting the Cherenkov photons on the ground produced from the showers which have been initiated by the gamma ray photons or the cosmic ray photons. So there are two parallel techniques which have been evolved for doing the gamma ray astronomy. First is the sampling the arrival time of Cherenkov pulses at different locations in the light pool. So when the one shower is produced, the Cherenkov light is distributed on the ground over a circle of around say 100 meter. So if we put any detector in this Cherenkov pool, you can get this. You can detect the shower. So one technique is the wavefront sampling. You put different telescopes in this pool and do its arrival time information analysis. Other is if we can directly image the shower formation. So that is called the imaging technique. So this wavefront sampling technique, I think in the next lecture, Dr. Varsha Chitnis is going to talk more about the wavefront sampling. So here onwards, I will be only focusing on the imaging technique. So how this imaging technique works? When this gamma ray or the cosmic ray enters the atmosphere, the shower is produced, the Cherenkov light is coming on the Earth. You put a detector or the telescope and just collect some Cherenkov photons on the ground and make the image. So this will be making the image of the shower development on the camera plane, where is the array of some photo sensors like photomultiplier tubes. So this will be a quite regular image of the shower if it is produced by the gamma ray, and if it is produced by a cosmic ray like proton, then the shower image will be quite random. And apart from these two signals, so for one gamma ray, we are getting many cosmic ray showers also simultaneously. So what signal we are getting in the detector plane is the shower information produced by the gamma ray as well as cosmic rays. And additional contribution is continuously coming from the light of night sky, which is a contribution of stars, Milky Way, and other ambient light at the eye. So it has many challenges. So first of all, the flux level is very low. So we need very high collection area to detect significant signal. And the Cherenkov light, which is produced from the charged particles produced in the extensive air showers, the spectral band is very small. It is around 200 to 4 nanometer. So we need a reflectance, optimized reflectance of the reflector, and very good efficiency photosensors so that they can detect this signal very fast. So we need very fast electronics also working at the gigahertz domain, and then huge cosmic ray background. So how to get for getting gamma signal, how to get rid of these things? So we have the information about the gamma ray showers, which has very regular, as I mentioned earlier, it has very regular shape, and they are basically oriented towards the source in the camera plane. And the shower development timing is less compared to the hadronic showers, which are developed for a longer time. And the night sky background is very constant. It's kind of a DC noise, and it is unrelated with any of these two. So first thing, we have to remove the contribution from the night sky background. That is something called the image cleaning procedure. When we clean the image, that means we remove the contribution from our night sky, from stars, galaxy, and other things. Then we are left with the images of either cosmic ray or the gamma ray showers. So how to reject the cosmic ray showers, because we are interested in getting the gamma ray signal. So that is something called Hillas parametrization technique, which is basically a moment analysis technique for the distribution of photons in the camera plane. So we calculate the lateral and longitudinal distribution, something called the length of the shower and the width of the shower, and orientation and different parameters, defined by the Hillas. And then one important parameter is the alpha parameter, which is basically the orientation parameter. So for randomly coming cosmic rays, the alpha parameter will be very uniform. It will not have any particular direction. But for gamma ray, this would be confined in a small region. So from simulation, we decide what is the alpha parameter for gamma ray showers. So basically, it comes out to be around less than 10 degree. For cosmic ray showers, it is random. So if using this technique, we can get the signal from the small alpha region site, which is basically the gamma signal, whereas the random distribution or the uniform distribution of this alpha parameter of the cosmic ray events can be used to get the background information. So when we have this technique, so but again, we do not know is that they are gamma ray photons, cosmic ray photons. So we never count the gamma ray photons exactly. We talk about the only statistically about the gamma rays. So how we get the signal? It is basically the signal to noise ratio, and in the gamma ray astronomy, this is standard practice that if signal to noise ratio is 5 times, basically noise is the fluctuation in the cosmic ray background. And if the signal excess events is 5 times the fluctuation, so we say the first, and this is the detection of the gamma ray from that source direction. So first aim in the gamma ray astronomy from the ground is to claim there is a 5 sigma detection. That means we can say about 99% confidence level that whatever gamma ray signals are coming, they are genuine gamma ray signals. They are not because of the fluctuation in the cosmic ray background. Once we claim the detection from the source, then we try to estimate the energy, what is the energy of those gamma ray like events which have been recorded, and then we determine their energy distribution, that is called spectrum. Then from the spectrum, we know what is the emission process. So first to claim the detection, then go for the emission process, and then go for next is use these gamma rays which have been detected as a probe to do some fundamental physics in the universe. Like we can do some cosmological problems, like we can prove the dark matter or the fundamental physics, something called because of the quantum gravity effects, the Lorentz invariance violation is happening. because this gamma ray are the high energy photons. And if we assume that these sources are producing the electromagnetic radiation from radio to gamma ray simultaneously, then if we have optical photon and the gamma ray photon emitted simultaneously from a source, and if there is a time delay in the detection, that means there is some the speed is energy dependent, which is contradictory to the special theory of relativity. So that why it's called the Lorentz violation. But I will not be going into detail because it's only the observational facilities. But these are the some interesting physics that can be done using gamma ray observations. So with this background, if we see the historical milestones in this field, so first gamma ray detection from a cosmic source was done in 1968 by a single pixel camera uh, by Kremian group. And then after around 10 years, the first imaging technique, the imaging atmospheric Cherenkov telescope was developed by the same telescope was converted to a multi-pixel camera, and with a 37 pixel camera, that means an array of 37 PMTs at the focal plane of the reflector, the gamma detection from the Crab Nebula was detected by using this imaging technique in 1989. After that, the program of gamma astronomy started, and then first generation telescopes like Whipple, Hegra, Kangaroo, they were developed worldwide for detecting gamma rays from the ground using ICT technique. India also at the same time proposed the first imaging technique called TACTIC at Mount Abu in 1993, and the telescope saw first light in 1997, which I will be describing soon. And in the second generation telescope, the large scale reflectors with a diameter around 17 meter, 12 meter were developed. And then India also proposed to develop a 21-meter diameter mesh telescope in the second generation. Now in the third generation, these systems have gone into the stereoscope mode. That means in place of using the single telescope, we use the two telescopes in stereoscope mode. We can get better angular resolution and better energy resolution, and then the capacity of this technique increases drastically. So the first, after detection of first so gamma ray emission from the Crab Nebula in 1989, after about 30 years, more than 200 sources have been detected so far using gamma ray astronomy. So in 30 years, there is a very significant advancement in this area. So in now coming to the Indian perspective, so the first telescope, this TACTIC is the TV, it stands for TV Atmospheric Cherenkov Telescope with imaging camera. As I mentioned, it was proposed in 1993, soon after the first detection of gamma ray signal using ICT. And the telescope was completely installed at Mount Abu, Rajasthan in 1996. And the first light was in 1997 using a 81 pixel prototype imaging camera. As Whipple telescope used 37 pixel camera, but the TACTIC telescope started with 81 pixel. And this was the first imaging atmospheric Cherenkov telescope in India, not only in India, even in Asia. Then with the experience of working with TACTIC telescope for more than 10 years, then MESH telescope was also proposed, and that this MESH stands for Major Atmospheric Cherenkov Experiment. And this telescope has been recently installed at Hanle, Ladakh, and presently the telescope, all the trial runs are going on, and the telescope is currently in the commissioning phase, and we are expecting very soon it will go in the science operation phase. So recently we have written a very nice review article about our 20 years of gamma ray astronomy program, which I think today it has appeared in Universe. So if I request one can have a look on this the national perspective of gamma ray astronomy with imaging techniques. So this is the photograph of TACTIC telescope at Mount Abu. The array at the center. This telescope is used as an imaging element for detecting gamma rays. So this is the site at Guru Shakar, Mount Abu. Its geographical coordinates are 24 degree, the altitude is 24 degree north and longitude 72 degree, and the altitude is around 1.3 kilometer above sea level. And telescope at that site is very well connected with major cities in India, and regular observations are going on. And this site provides around, because we need observations in the dark conditions, so this site provides around 1,000 hours per year as duty cycle. And other technical features are basically This is azimuth mount system. The reflector diameter is 4 meter, and focal length of the telescope, that reflector, is 3.8 meter. And the reflector uses the tessellated mirrors of circular size, 34 mirrors, which together gives a total collection area of around 10 meters square. And then at the camera of the telescope uses around 349 array of PMTs, which provides a total field of view of around 6 degree to 6 degree, and the telescope has an angular resolution of 0.2 degree at 1 TeV, and energy resolution is around 25%. So as far as the performance of the telescope is concerned, with 81 pixel prototype camera, I detected the first light, and it was a very historical flare from one of the blazer called Mercurian 501 in April 1997. That was also detected with this prototype camera. And then since 2001, the camera was fully installed with 314 pixel, and the telescope started regular observation with a trigger energy threshold of around 1 TeV for gamma ray photons and 1.8 TeV for the hadronic showers. So telescope has a detection sensitivity of detecting signal, gamma ray signal from standard candle like Crab Nebula in 25 hours, and the rate which if you detect in this time, so it was coming to be like Crab unit, which can be a gamma ray, 10 gamma ray per hour. In 2011, the major upgrade were undertaken, and in the software hardware part of the telescope, and with this upgrade, there was significant reduction in the threshold energy. So it was around 850 GeV, and the sensitivity of the telescope also drastically improved from 5 sigma detection in 12 hours. We reached to 5 sigma, from 5 sigma in 25 hours, we reached to 5 sigma detection in only 12 hours. And then the Crab rate also increased from 10 gamma to 15 gamma. There were some additional changes in the software and data analysis part, like we use artificial neural network-based algorithms for gamma separation. This also helped in improving the sensitivity of the telescope. So just to show an example.
Dr. Singh, 4 more minutes. Dr. Singh, 3 more minutes.
Okay. So these are some results from the tactic telescope recently we have done, and it is still operating. So next is the MACE telescope, which has been installed at Hanley around 4.3 kilometer. So this is a 21 meter diameter and 25 meter focal length telescope. It uses around 1400 metallic mirror facets of half meter by half meter area, which keep around 350 meters. So it's a quite jump from the collection area point of view. The camera is 1088 pixel camera, and its field of view is around 4 degree by 4 degree. And the expected from simulation, the expected performance of the telescope is it has a trigger threshold of around 20 GeV, and it can detect 5 sigma signal from Crab in around 1.5 minutes. So the point expect function from pole star is around 46 mm, which is less than the size of 1 pixel at the camera. So the performance is very good as far as the telescope design is concerned. So it has many important achievements. So the telescope has been indigenously developed in the country. So it's a perfect example of our Atmanirbhar Bharat. The telescope mirror segments used in this telescope are the metallic mirrors which have been used, which have been developed first time in the country. And the large reflector area, 21 meter, makes it the telescope third largest in the world after Hess and large size telescope with this. The altitude is the highest in the world. Lower threshold energy of the telescope, around 20 GeV, provides good energy overlap with the space-like observations like Fermi light. And we are using artificial intelligence techniques like artificial neural network and random forest for background rejection. So this telescope is going to provide us a unique opportunity to explore the universe in the energy range 20 GeV to 200 GeV, and some deep observations beyond redshift 2. So to summarize, the gamma astronomy has emerged as a viable discipline in its own right for probing the non-thermal universe at GeV-TeV energies. Imaging atmospheric challenge telescope has been developed as a consolidated tool for the ground-based gamma ray astronomy. In the national perspective, the tactic telescope, which belongs to the first generation of imaging telescope, has proven to be a very successful experiment with many important results at TeV energies, and the upcoming MACE telescope at Hanley will be a game changer in the Indian gamma ray astronomy program. So in the next decade. So I think at this moment it's very exciting time to have a national multi-messenger astronomy program with an active collaboration among various academic and research institutes to do a effective multi-messenger astronomy. Thank you.
Dr. Singh, thank you very much for opening up the exciting gamma ray astronomy to us and talking about upcoming MACE mission. We have time for 1 or 2 questions.
Yeah.
If anybody has questions, please unmute yourself.
Hello, sir. I would like to know, how do you define the directionality of the gamma ray source in a gamma ray telescope?
Yeah,
is there some uncertainty in that, and how do you overcome that?
Yeah, as I said, if you see these telescopes have very good angular resolution. So they are at around of the order of 0.1 degree or 0.2 degree. So from the Hillas parameter, the alpha parameter first defines the directionality, and from the whatever excess events we are getting from the alpha parameter analysis, then we do the sky mapping of individual events, then decide the direction. So it is, I think, less than even 0.1 degree that we can do.
Okay, thank you.
Yeah.
KK, this is Amit.
Yeah.
Hi, a very good talk. You mentioned that the threshold is 20 MeV. Is it a triggering threshold or analysis threshold?
No, it is not MeV. It is 20 GeV.
Sorry,
Yeah.
GeV. Sorry.
Yeah, it is trigger threshold. Analysis threshold is around 30 GeV.
So is it dependent on the pipeline or the algorithm which you are using, like ANN or RF?
Yeah. Actually, this is dependent on the algorithm and the spectrum also, as you know. So this is for a power law spectrum. If you change the spectrum, it will also change. So it is a power law spectrum and log parabola. If you see the log parabola, then it is going from 20 GeV to around 30 GeV.
Okay.
So to begin with, the power law source, it is around 20 GeV trigger energy threshold.
Okay, it's a very exciting. Thank you.
Okay, thank you.
Krishna, very exciting talk, very useful. I was just curious. I'm Bhalchandra Joshi from NCRA. I was very curious if you have any archive of the tactic data with timestamped photons. And I'm particularly interested about GRB observations done by tactic in a period between 2015 to 2019 or 20.
Yeah, we have the data, but not in the form of archive. If you want it, we can provide you the complete data, but not in the form of archives that public use. But we have the data because we want to also publish it and other to calibrate the system performance. We have the data available. If you want,
is it time tag?
Yeah.
Is it time tag?
Yeah. So
okay, thanks.
If you want, we can provide you.
Yeah, sure. I'll talk to you offline.
Okay.
Pankaj, last question. Pankaj. Do you have a question?
Yeah. Can you hear me?
Yeah, please.
Yeah, a very nice talk. So I just wanted to know about the current MACE status and what the things are going to be in the immediate plan.
Yeah, actually, current status is MACE is already taking data from CRAB to optimize its performance. And we have some signal, but because this is being in BRC, so first it should be inaugurated with a final signal announcement. So I think soon you will be hearing about the signal from the source. Already it is taking data regularly from the CRAB and other sources, but we have not been able to announce it because of some institute formalities and other things. But it is taking continuously. The system performance has been very exciting.
Okay, and what about the coordination was supposed to be that Hagar is there, so anything on that and MACE?
No, that Hagar first time actually in the first phase from until December we want to operate in the for some other low redshift source like Mercurian 41501 to fully optimize the source this telescope performance. Then we will enter into the coordinate observation with multi-wavelength group.
Okay, thank you.
Yeah. Thank you very much, Professor K. Dr. K. So it's a very exciting talk. May I request you to unshare the screen? Yeah, from one atmospheric Cherenkov telescope to another atmospheric Cherenkov telescope, may I request Dr. Varsha Chitnis to deliver her talk? Hagar and Pat. Dr. Varsha Chitnis, your mic is muted. Dr. Chitnis, can you please unmute your mic?
Hello.
Yeah.
Hello, am I
Please go.
audible? And is my
Yes, you are
screen
audible
full?
and it is visible.
Okay.
Please go ahead.
Okay. Sorry for this confusion I created just now. Okay, I'm good. Okay, first of all, I thank organizers for giving me opportunity to speak in this workshop. I will be talking about study of blazars using PACT and Hagar, and also about future plans. We have already just now heard about TACTIC and MACE. So like these two telescopes, PACT and Hagar are also designed to study VHE gamma ray emission from celestial sources. Like TACTIC and MACE, these two telescope arrays are also based on atmospheric Cherenkov technique, but it is slightly different than what is used for TACTIC and MACE. So I will little bit elaborate on this technique, which is called wavefront sampling technique. We were operating PACT at Pachmadi for more than a decade. So I will briefly give the details and some of the results from PACT, but major part of today's talk is on Hagar. So I will elaborate on instrument details and then talk about the study of blazars carried out using Hagar. Presently, our group is developing an imaging camera for 4-meter class telescope, and this telescope will be dedicated for monitoring of blazars. So this is going to be the last part of my talk. So gamma ray coming from celestial source generates shower of charged particles in a terrestrial atmosphere. These charged particles cause atmosphere to emit bluish Cherenkov light. It is basically this Cherenkov light is peaked in UV blue region of the spectrum, and this is detected using a telescope which is very similar to optical telescope. There are two variants of this technique, imaging and wavefront sampling. Imaging technique, we have just now heard about it. So telescopes like TACTIC, MACE, then present generation big telescopes like HAZE, Veritas, MAGIC, and upcoming telescope array, Cherenkov telescope array or CTA, all these are based on wavefront sampling technique. Whereas PACT, Hagar, and previous generation large arrays like Celeste, Stacy, they followed wavefront sampling technique. So in wavefront sampling technique, we have distributed array of small size telescopes which samples Cherenkov light at various locations in Cherenkov pool. Now, as KK Singh has already mentioned, this Cherenkov pool is a circular region with radius of about 110 meter to 130 meter, depending on the altitude of the place. So using this distributed array, arrival time of Cherenkov shower front and Cherenkov photon density is recorded at various locations in the pool. Then this arrival time information, it gives you arrival direction of shower axis, which is same as the arrival direction of gamma ray. And using this Cherenkov photon density information at various locations, one can get estimate of primary energy. Between these two techniques, wavefront sampling is the older technique and imaging is newer technique. We were operating PACT or Pachmadi array of Cherenkov telescopes at Pachmadi in Madhya Pradesh. Altitude of this place is about 1 kilometer. This array consisted of 24 telescopes, which were spread over an area of 80 meter by 100 meter. Each of these telescopes consisted of 7 paraxially mounted parabolic mirrors. And using this array, we used to record arrival time of Cherenkov shower front and Cherenkov photon density at each mirror. This telescope array was operational during 2001 to 2012. and its energy threshold, that is the peak of the differential rate curve, was at 750 GeV. Sensitivity of PACT was moderate. In fact, all wavefront sampling arrays have sensitivity much less than imaging technique. This is because we do not have very efficient methods of eliminating cosmic ray showers. So this cosmic rays former, actually KK Singh had given some numbers also. So this cosmic rays cause huge background against which gamma ray signal is detected. Now coming to results from PACT, we had long coverage for Blazar Mercurian 421. So here you can see 6 years light curve from PACT from 2000 to 2005. Then we have also studied spectral energy distribution during flare state in 2001 and quiescent state in 2003. And these SEDs are fitted using synchrotron self-Compton model. Okay, I won't go into the details because I'll be showing much better sampled SEDs when I talk about Hagar observations. We also had long duration coverage for some more blazars like Mercurian 501, ON 231, 1ES 1426 plus 428, etc. But we did not get any statistically significant detection from these sources, and we could give only upper limits. When we observed some pulsars also, and we searched for pulsations from Geminga at a period of 237 milliseconds, which is the known period from other wavebands, but we did not have any statistically significant detection of pulsations. In fact, even today, with present generation telescopes, which are far more sensitive compared to PACT, there is no detection of pulsations from Geminga at very high energy in VHE band. We continued operation of PACT till 2012. By that time, our group was fully occupied with Hagar. So because of lack of manpower, we had to stop PACT observations. As I have just mentioned, PACT had energy threshold of 750 GeV. In 1990s, most of the atmospheric Cherenkov telescopes had energy threshold in the range of 500 GeV to 1 TeV. There was strong scientific motivation to reduce this energy threshold of these telescopes and have an overlap with satellite-based detectors like Fermi. So energy threshold in the neighborhood of 100 GeV or less was desirable. So scientific motivation was to detect very high energy gamma ray emission from distant AGNs and GRBs, and also to study pulsed component of pulsars. Now there are two ways of reducing energy threshold. One can go for large size mirrors, and this is the alternative followed by most of the groups in the world, but this is little expensive. Other cost effective way is to go to high altitude location. So here you can see in this picture, as one goes to higher altitude location, Cherenkov photon density in the cone increases. Also, atmospheric attenuation of Cherenkov photons is much lower at higher altitude. Because of this, it is possible to detect gamma rays with much lower energy from high altitude location. So, for Institute HYGRO, that is Himalayan Gamma Ray Observatory collaboration, was found to set up such atmospheric Cherenkov telescopes at Hanle in Himalayas, taking advantage of infrastructure already developed by IA at that place. So this HYGRO collaboration, okay, HYGRO stands for Himalayan Gamma Ray Observatory Collaboration, and Hagar is the first phase of HYGRO, which is led by TIFR and IA, and MES is the second phase, which is led by BRC. Now, Hagar is also a wavefront sampling array like PACT. It is located at Hanle Base Camp at an altitude of 4.3 kilometers. It is an array of 7 telescopes, as you can see here, and spacing between these telescopes is 50 meters. Each telescope consists of 7 paraxially mounted parabolic mirrors. Diameter of each mirror is about 90 centimeters, and at the focus of each mirror, UV sensitive PMT is mounted. Field of view of Hagar is 3-degree full width maximum. Tracking system used is based on alt-azimuth design. Installation of Hagar was started in 2005 at Hanle and was completed in 2007. And since 2008, we have been conducting science observations. We have estimated various performance parameters, energy threshold, collection area, sensitivity, etc., using simulations. So energy threshold of Hagar is estimated to be 210 GeV. This is factor of 4 reduction compared to PACT threshold, and this reduction is largely achieved by going from 1 kilometer altitude to 4.3 kilometer altitude. Now coming back to details of Hagar, pulses from all these individual PMTs of 7 telescopes are brought to the control room where they are further processed. This control room is situated below the central telescope, and here you can see the photograph of this control room. So this is DAC, that is data acquisition system. This is DAC PC. Then there is high voltage controller. This is the motion control interface unit for central telescope. And using this PC, tracking of all 7 telescopes is controlled. So data acquisition system is based on CAMAC. Trigger is generated when at least 4 telescope pulses out of 7 cross pre-decided threshold in 60 nanosecond coincidence window. Once trigger is generated, data is recorded, and this data includes absolute arrival time of event accurate to microsecond, relative arrival time of shower front at each mirror at sub-nanosecond accuracy, then Cherenkov photon density or total charge in pulse at each telescope. We are also recording profiles of telescope pulses in 1 nanosecond bins using waveform digitizer. We are mainly observing blazar class AGNs and pulsars using Hagar. Anyway, here everybody is familiar with blazars. First day of this workshop was completely devoted to AGNs and largely to blazars. So I will go through this slide very quickly. So blazars are AGNs with jets directed towards us. They include BL lags and FSRQs. They show flux variability on all time scales in all wavebands. Their SEDs show double hump structure. BL lags are classified as HBL, IBL, LBL, etc., depending on the position of these peaks in SED. The blazars we are observing with Hagar are mainly HBL type or high frequency peak blazars. Here, first peak of SED is at X-ray energies and second peak is at gamma ray energies. First peak is normally attributed to synchrotron emission from energetic electrons in jet. Second peak could be leptonic or hadronic in origin. Amongst leptonic models, we have synchrotron cell Compton or SSC model. So according to this model, synchrotron photons are Compton upscattered to higher energies by same population of electrons, and this gives rise to the second peak. So the SSC model is normally used to explain SEDs of BL lags, particularly HBLs. Other model in under leptonic category is external Compton or EC model. So here seed photons for Compton upscattering come from regions outside the jet, like accretion disk, dusty torus, BLR, etc. These external Compton models are normally used to explain FSRQs. Then there are hydraulic models like proton synchrotron, proton induced cascades, etc. Now coming to Hagar results, first important result is detection of Mercurian 421 in flare state in 2010. Mercurian 421 is a nearby blazar. It is known to show frequent flaring episodes. The flare seen during February 2010 was the second largest at that point, at that time. Largest flare was seen in 2001, which was observed using PACT. February 2010 flare was detected by large telescopes like Veritas Hayes and as well as by Hagar and TACTIC. Here is the light curve from Hagar spanning observation period of February to April 2010. And then bottom panel shows corresponding X-ray light curve from RXT ASM. In both the bands, flaring behavior is seen in February 2010. So using 8 hours data from Hagar in February 2010, we have detected source at 12.7 sigma level. This flux is quite often given in terms of Crab units. So maximum flux was seen by Hagar on the night of 17 February 2010, and it was at the level of 6 to 7 Crab units. Now for big flares from the sources, we are able to give night-wise flux from Hagar with good statistical significance. We also carried out multi-wave band study for this flare. So here is the multi-wave band light curve from various instruments from radio, optical, X-ray, high energy gamma ray, and VHE gamma ray light curve from Hagar. We have divided this flaring episode into 4 states to study evolution of SED. So these states are pre-flare state, moderate flare, TeV flare when we saw maximum flux from Hagar, and then post-flare states. So for all these states, we generated multi-wave band SEDs, and these were fitted using SSC model, so which assumes emission to be coming from spherical blob, which is filled with electrons and randomly oriented magnetic field. So one of the SEDs is shown here. This corresponds to the peak of Hagar flux. So this SED is based on optical data from SPAL, X-ray data from SWIFT XRT and RXT PCA, and high energy gamma ray data from Fermi-LAT, and VHE gamma ray data is from Hagar. So this SSC model, it has there are jet related parameters like Doppler factor, magnetic field, Then there are particle distribution related parameters like electron density, spectral shape, and then one parameter is size of emission region. We have fixed the size of emission region according to variability timescale of 1 day, which is normally seen in this kind of flares. So here are the parameters for 4 states given here, and this entire flaring episode could be due to passing shock. We have been continuously observing this source with Hagar, and here is the light curve from 7 years data from 2009 to 2015. So we have carried out multi-wavelength study for this long-term data using again data from radio to gamma ray. So your last panel is Hagar light curve, which includes data from 21 observation seasons of Hagar. Here are some of the results from this study. We found that variability increases with frequency as we go from lower energy to higher energy. Then spectral hardening is seen in X-ray band and not in gamma ray band. Then we studied time lag between various wavebands using discrete correlation function. And we found that radio flux lags behind gamma ray flux by 52 days. Then flux distributions from various wavebands were found to follow log normal distribution rather than Gaussian distribution. And this could be some indication of disject connection. We have generated SCDs for 21 observation seasons and fitted those using one zone SSC model. So one typical SCD is shown here. And here you can see these are SSC fits for 21 observation seasons. Here main finding was that flux variations across 21 observation seasons are mainly due to changes in underlying particle distribution rather than changes in jet parameters like magnetic field and Doppler factor. Now, another important result is detection of another nearby blazar, Mercurian 501, in moderately high state of activity in 2011. So here you can see light curve from Hagar spanning 3 observation seasons, March, April, April, May, and May, June. So we have seen highest flux level of 1.5 crab units in April, May 2011. So here you can see multi-wavelength light curve, and we have generated SCDs for all these 3 observation seasons of Hagar. Here you can see the SCD for April-May 2011 season. So we tried to fit these SCDs using SSC, and we found that single zone SSC model cannot adequately describe these SCDs, and we had to add one more zone to our model. So parameters for these 2 zones are given here. So basically conclusion is that emission is a little more complex. It's coming from multiple regions in jet. So apart from this, the blazars, we observed some more blazars, but we did not have statistically significant results from these other blazars as of now. Then there is another published result from Hagar, and that is detection of Crab Nebula, which is standard candle source. So here is the Hagar light curve spanning 9 years of data. And we have detected this source at 20 sigma significance level using more than 200 hours of data. And from this bottom panel, you can see that Hagar flux measurement, which is shown by red point here, it is consistent with flux measurements from other experiments. We also searched for periodicity in crab data, and pulsations were detected at a period of 33 milliseconds with more than 6 sigma significance level using something like 260 hours of data. We carried out search for pulsations for other sources, including Geminga, but it produced null result. Now, what exactly was achieved by going for Hagar? So here is the comparison of PACT and Hagar. So energy threshold of PACT was 750 GeV, whereas Hagar has energy threshold of 210 GeV. Now Hagar is at higher altitude location. So as one goes to higher altitude, size of Cherenkov pool decreases. So the area over which gamma ray showers are collected is smaller. But advantage offered by lower energy threshold outweighs this effect. As we go for lower energy threshold, we are collecting many more gamma ray showers, and this results in improvement in sensitivity, even though rejection of cosmic rays is roughly similar between the PACT and Hagar. So this sensitivity is given here in terms of time required to detect Crab Nebula equivalent signal at 5 sigma significance level. In case of PACT, we needed 41 hours observation duration, whereas Hagar could achieve this within 17 hours. In case of PACT, since sensitivity was poor, Even during 2001 Mercury 421 flare, we could give result only with the significance level of something like 3.5 sigma. Whereas with Hagar, we are able to give results with much better statistical significance. And Hagar also gave us experience of operating telescope at high altitude location. And this basically paved the way for telescopes like larger size telescopes like MES at Hanley. Now, presently, our group is also involved with imaging technique for our next project. So we are developing SIPM-based imaging camera for 4-meter class telescope. Normally, PMTs are used in such cameras, but SIPMs have very recently, they have emerged as viable alternative. In fact, SIPMs have many attractive features, like they have higher quantum efficiency, then they need much lower bias voltage, and most importantly, they can be operated during in bright environment safely. This is not the case with PMTs. So with SIPM camera, it is possible to have larger observation duty cycle. One can conduct observations during twilight and partial moonlit part of the night. One such telescope called FACT is operational in Canary Islands for last few years. And here you can see light curve of Mercurian 501 from FACT, which has SIPM based camera, and lower panel is the light curve from MAGIC, which has PMT based camera. Pink bands are the moon times when MAGIC is not available, not operational, whereas FACT is operational almost throughout. So it gives us much longer coverage for blazars. Now coming back to specifications of our camera will have 256 pixels. Each pixel will consist of SIPM and one light concentrator mounted in front of it. Size of each pixel will be 0.3 degree. Field of view of our camera will be 5 degree by 5 degree. This camera will have modular structure. Each module, as you see here, will consist of 16 pixels and associated electronics. And this entire electronics will be mounted just behind the pixels in focal plane. This camera will be installed on in the focal plane of one of the vertex elements of tactic at Mount Abu. So after thoroughly testing the camera there, we have plans to ship telescope and camera to Hanley and dedicate this telescope for monitoring of blazars. We have carried out simulations to get expected performance parameters. So energy threshold of this telescope is expected to be around 600 GeV at Mount Abu, and it could be in the range of 200 to 300 GeV at Hanley, depending on the trigger condition used. Also, this telescope is expected to detect crab at 5 sigma significance level in 1.5 to 2 hours duration. But it should be kept in mind that these are preliminary estimates. Once we carry out field test, these estimates may get revised. So presently we have 4 modules set up, assembled and being tested in TIFR lab. So this basically has 64 pixels. So this is 1/4 of the entire camera. So now we have a plan of testing this mini camera at Mount Abu just after monsoon this year. Entire camera is expected to be ready by end of next year. And then this will be followed by tests of entire camera at Mount Abu. And after that, we can think of installing this telescope at Hanley. So this telescope will be giving long coverage for blazars. It can be operated in coordination with similar telescopes across the globe. One telescope I have already mentioned, FACT in Canary Islands. And then European groups have proposed one similar telescope in Mexico. So if we can operate these 3 telescopes in coordination, we can have long duration stretches for blazars, uninterrupted stretches for blazars. Also, this telescope will complement MES telescope. MES being one of the largest size telescopes in the world, normally will be operated in discovery mode. So whenever SIPM telescope sees flare from the blazar it is monitoring, it can alert MES and other telescopes to conduct deeper observations. Now, finally, this is just comparison between PACT, Hagar, and then SIPM telescope at Mount Abu and Hanley. So energy thresholds are given for all these cases. Most important thing is like improvement in sensitivity. So in case of PACT, we needed 41 hours to detect Crab nebula at 5 sigma significance level, which reduced to 17 hours. Both these are wavefront sampling arrays. So here cosmic ray rejection is rather poor. We are able to reject only something like 15% of cosmic ray showers. This sensitivity improves to 1.5 to 2 hours using imaging telescope, like based on SIPM camera. at Mount Abu and Hanley. This is mainly because of huge cosmic ray rejection, which is possible with this technique. So based on the image shape and orientation, it is possible to reject more than 99% of the cosmic ray showers, giving like a very significant improvement in sensitivity. Okay, so I'll stop here. Thanks.
Thank you, Dr. Chitnis, for sticking to the time. So we have time for a few questions. If any of you have any questions, please raise your hand. If there are no questions, Dr. Varsha, I have one question.
Yeah.
So I'm surprised to see that there is no effect of on sensitivity, that altitude variation between Mount Abu and Hanley. Is it because?
Okay. Yeah, actually sensitivity, I would say these are preliminary estimates. And for Hanley, we had used supercuts and dynamic supercuts technique. And very recently for Mount Abu, we used random forest. So we have not used exactly same technique at for both the cases. And other thing is night sky background could be different in case of Hanley and Mount Abu. So, okay, right now we have assumed roughly similar numbers. But main thing is this, like random forest versus, so right now I'm just saying like it could be within 1.5 to 2 hours, but I'm not able to say really, like we need some more, we have to carry out field tests and then we have to see how much is the night sky background, etc. Because that decides our trigger threshold.
So we can expect improvement in when you move to Hanley.
Yes. Okay. Yes, improvement could be there.
Okay, thank you. Are there any other questions? So if not, let's thank Dr. Varsha one more time, and thank you very much for sticking to the time. And now may I request you to unshare the screen? So we'll now move on to the other extreme of the electromagnetic spectrum, to the radio wave. So may I invite Professor B.C. Joshi to deliver talk on Indian and international pulsar timing array. Professor Joshi, you can share your screen.
Yeah, can you hear me?
Yes, I can hear you. Can you please share your screen?
Yeah. Can you see the screen?
Yes. Can you just put it in the full screen mode? Fine. Please go ahead. Thank you very much. Yes.
Okay. Okay. Good afternoon, everyone. At the beginning, let me express my gratitude to the organizers to give me this opportunity to communicate our excitement on behalf of all my colleagues, which are listed here in the from about 15 institutions in India and abroad in the Indian Pulsar Timing Array Consortium. The latest window in the universe, as far as multi-messenger astronomy is concerned, was opened in February 2016 when LIGO and Virgo Consortium announced an audible chirp signal from merger of two black holes. This latest kid in the block actually adds a significantly new flavor to astrophysics. And soon after this discovery, efforts to open up the entire spectrum of gravitational waves got a significant boost by this discovery. So in the talk today, I would describe a telescope to herald an era of very low frequency gravitational wave and the Indian perspective, as well as the international efforts in this particular direction. Okay, so let me just start with an introduction to the gravitational wave itself. So when LIGO Virgo Consortium announced GW 150914, which was a merger of two 35 and 30 solar mass black holes with a signal shown here on the right, ramping from 35 to 250 megahertz in about a fifth of a second on September 14, 2015, a new messenger to look at the universe was found. And ever since that discovery in the last 5 years, more than 6 years, more than 50 such events in the 3 science runs of LIGO have been seen. And all the different sources are listed here on the right at the bottom plot. And what is heartening is that one is moving beyond the discovery. So there have been, say, for example, the first evidence, real evidence of a black hole in terms of quasi-normal ring-down modes, two double neutron star merger systems, which are with potential to put constraint on equation of state. And Arun talked about this on the first day of the conference. Neutron star black hole candidates, and getting the multipolar emission from a particular system, GW 190412, which promises to determine the inclination angle and hence the distance to the source fairly accurately, and work as a standard candle for with exciting possibilities towards cosmology and evolution of the universe and so on. So clearly, there is a shift from just discovering many more sources towards doing some real significant astrophysics from gravitational waves. And in this sense, the gravitational wave field is sort of maturing. Now, much like the electromagnetic spectrum, the gravitational wave spectrum also spans orders of magnitude. And the methods and the sources are very different in different parts of the spectrum. What is shown here is the gravitational wave spectrum, where the LIGO discoveries are in the high frequency end, which is of the order of hertz, and time scales of the order of spans, seconds and days, and wavelengths of the order of several thousands of meters. What is of more interest for the talk today is the low frequency end, and in particular the very low frequency end, which is between nanohertz to few microhertz, time scales of the order of decades, several years, 5 to 10 years and so on, and wavelengths of the order of several hundreds of, several parsecs. Okay. And it is in this lower part of the spectrum that no gravitational waves have been detected so far. And I would focus on this, and pulsar timing arrays fall in this part of the spectrum. Okay, so pulsar timing array is actually a telescope in the sky. It is a celestial instrument which is sensitive to nanohertz gravitational wave. And these gravitational waves are being generated from a background, which is a superposition of all the supermassive black hole binaries in the universe. And the way this occurs is that we use radio pulsars, which are very periodic sources, and I'll say a little bit about them to introduce them, because I realize that no one has talked about pulsars here too much. So the gravitational waves actually cause delay and advancement in the time of arrival of these. And if you have ensemble of pulsars as shown here on the graphic in the right, a correlated signal would be the imprint of the gravitational wave which you want to detect. A few words about radio pulsars. These are highly magnetized rotating neutron stars where you see the radio emission in the form of very periodic pulses, and the stable periodicity is because of their large mass and very compact nature. And in fact, these rival some of the best terrestrial atomic clocks. And it is this stability as a clock which is very useful in sort of detection of gravitational waves. Okay, so with that very brief introduction to pulsars, let me get back to the pulsar timing array. So the gravitational wave signature or the imprint is tiny deviations in the frequency of the pulse from a radio pulsar, which is given by this expression here. This is a fractional change in frequency, which corresponds to the fractional change or distortion in the metric of the space-time through which the wave is passing. In this expression, the blue terms are the amplitude of the gravitational wave near the Earth, or what is called as reception term, and the red is the amplitude near the pulsar, which is also known as the emission term. Now, the tiny distortion in the space-time near the Earth would actually lead to an advancement and delay in the pulse frequency. And what is more important is this would be correlated across pulsars separated by angular separation of say 5 degree, 10 degree, 15 degree, and 20 degree. Not only the deviations will be correlated, they will be correlated in a very precise form, which can be calculated from first principles. And that is the expression which is given here at the bottom. And this characteristic quadrupolar spatial correlation is known as Hellingsand down curve, which is also plotted in the right plot here. So this Hellingsand down overlap function is the characteristic signature of the nanohertz gravitational wave as detected by this celestial telescope consisting of many radio pulsars widely separated in the sky. Now, this has some important implications. First of all, PTA is an essential telescope in the sky, and you observe millisecond pulsars, which are very, very weak radio sources. So since it's a telescope in the sky, it is a facility which is accessible to everybody in the world, provided you have a very large and sensitive radio telescope, because you need to observe these very, very weak sources. Also, naturally, because of this, it is an experiment which by definition is an international project in nature, and the different large telescopes in the world cooperate to achieve the kind of sensitivity which is required here. One is measuring deviations in time period of the order of few nanoseconds, and this requires cooperation of and collection of data from various sources. In fact, combining data from the largest radio telescopes in the world terrifically improves the sensitivity of the PTA. And that's why this, by definition, is an international project. Okay, so once you have got the you've got basically the idea of how the PTA works, how do you form a particular PTA? So to form a PTA, a judicious sample is required of pulsars, and these millisecond pulsars need to satisfy the following criteria. Since we are dealing with very accurate clocks, we need pulsars with exceptionally high rotational stability. We also want to time their pulses with great precision. That's why you need bright pulsars as far as possible, and pulsars with sharply peaked pulse profiles or light curves, which do not change with time. Moreover, you need pulsars which are nearby for two reasons. A, because they will be brighter than the faraway pulsars, and B, the signal will traverse less of the interstellar medium and hence suffer with smaller amount of dispersion. More importantly, it is less likely to have lines of sight towards these pulsars with unusual ISM structures which change as a function of time. So these ISM effects actually compromise the uncertainty in the TOA, and hence it is best to avoid these. But more importantly, and most importantly, you need to have a sample of pulsars which is widely distributed in the sky, so that you can sample the Hellingsand down overlap function which I showed earlier. All these constraints are very challenging, and because of that, although there are 2,900 known pulsars as of today, this leaves only a small sample of 75 pulsars which you can use for a pulsar timing array experiment. Okay, so the deviations in the pulse frequency of the radio pulsars are the signature of the gravitational waves. So to extract this gravitational wave, you use a technique known as pulsar timing. I don't have much time to go into the details of this technique, except to say that this technique involves assigning a time of arrival to the average profile by reference to an atomic clock in the observatory, such as a hydrogen maser. And this topocentric time of arrival is then referred to an inertial frame, which is the solar system barycenter, after applying a series of corrections. And these barycentered time of arrivals are then used to keep track of the rotation cycle of the pulsar by comparing the prediction of time of arrival from a rotational model of the neutron star with that observed of the observed TOA to refine a model. So in this whole process, you get a difference between the observed and the predicted TOA, which is called timing residuals. So you assume a model, a rotational, positional, orbital, and interstellar medium model, and using the differences or in the fractional phase or the timing residuals, you get the best fit parameters by fitting the residuals in a least square sense. So that's what essentially the pulsar timing technique is all about. So if your model does not if your data has an unmodeled parameter, then it will appear as a systematic effect in residuals, and gravitational wave is one such effect. Okay. Please note that since we are looking at very low frequency gravitational waves, this will produce residuals which are slowly varying with typical timescales of decades. So this means that these experiments naturally are long-term experiments. You need several years to do this, 5 years, 10 years, 15 years, and 20 years, and so on. Now, this kind of a low frequency nature of the residuals, or what is called as red noise, presents several challenges. So although the millisecond pulsars used here are excellent clocks, they do exhibit a wander in their rotation rate, which is known as timing noise. And this timing noise can mimic a red noise process like the gravitational wave, but without a Helings and Downs spatial correlation. In the last 3 to 4 months, the average common red noise and the timing noise relationship has become a very hot topic of debate as far as this community is concerned. In addition to the timing noise, you could have slow variations of the atomic clock, which you are using to get the time of arrival, and you can have clock errors. And these also will give a correlation between the pulsars. Fortunately, the correlation overlap function is monopolar, which is very distinct from the Helings and Downs curve. So you could in principle discriminate between the two. A third uncertainty comes from our imperfect knowledge of our own solar system. So since the orbit of the massive planets like Jupiter and Saturn are 12 years and 29 years, any variation because of uncertainty in solar system ephemeris will also show up as a red noise, covariant with the gravitational wave signal. But again, the spatial correlation here would be dipolar. So one could use the nature of the spatial correlation to sort of distinguish it from the gravitational waves. Last but not the least, and most important point which one needs to do, which is very relevant for GMRT, is the turbulent interstellar medium, which slowly varies. So it leads to slow variation in dispersion and multipath propagation. And this may well be correlated for nearby pulsars. The spatial correlation of this is much more complicated than the earlier two cases. So it is very difficult to say whether you can distinguish this with the Helings and Downs correlation or not. So the best way is to try and characterize this as best as you can. Nevertheless, removing these variations is critical to the sensitivity of the PTA. Please note that these effects, the interstellar medium effects, are very strong functions of observing frequency and are predominant at a lower frequency. So a low frequency telescope like upgraded GMRT below 1 gigahertz with niche capabilities like the ones which Jairam described or mentioned in the morning is very important for PTA experiments. So giving this brief background, I would just come to the current international perspective. So there are 4 such experiments operating at the moment. The European Pulsar Timing Array, which uses the large telescopes in the Europe, Jodrell Bank, Effelsberg, Sardinia, and so on. The Indian Pulsar Timing Array, which uses the upgraded GMRT, and I'll describe that a little later. The Nanohertz Gravitational Wave Observatory, which uses the Green Bank telescope, and till last year, the Arecibo telescope before it collapsed. And Parkes Pulsar Timing Array, which uses the 64-meter Parkes Radio telescope. All of these, they carry out combined analysis by sharing their data in an international effort called as International Pulsar Timing Array. And just last month, PTA became a full member of this global instrument. Very briefly about few words about each of these experiments. So PPTA times about 26 millisecond pulsars at all frequencies above 800 megahertz and has been in operation for about 16 years. And their latest result is a common correlated red noise process with an amplitude of 2 into 10 to the power minus 15. It's not clear whether this has anything to do with gravitational wave signal, but they do see something like that. The nanograph also times 47 millisecond pulsars for the last 16 years, and they also are reporting a common red noise process in their recent results. EPTA, on the other hand, has a varying timeline of pulsars. It times about 42 millisecond pulsars varying over baselines of 7 to 18 years, and also sort of report recently a common red noise process. So that brings me to the Indian perspective. So about 6 years back, we started this experiment, Indian Pulsar Timing Array experiment, which primarily uses the upgraded GMRT and the ORT for timing a sample of PDA pulsars. And it's a pan-India collaboration of about 25 research scientists and also from 16 institutions in India and abroad. The main point here is that it uses unique niche capabilities of UGMRT, such as the wide sky coverage, low frequency, the wideband feeds, the new wideband feeds which have been installed, and more importantly, the multi-band and multi-subarray, multi-beam nature of the upgraded GMRT. Some of these modes were described in the talk in the morning. And it uses the new upgraded hydrogen masers to accurately time tag the data which we are getting from the GMRT. Most importantly, it provides a seamless low frequency coverage from 300 to 1400. And precisely this frequency coverage is very useful for characterizing the effects of the interstellar medium on the precision of the TOAs. And I will have something more to speak about it. This is just the a small snapshot of all the members involved in our collaboration. Okay. So how do we actually use UGMRT in a unique way as far as the PTA is concerned? So as I said, all the PTAs, they share their data in IPTA to collaborate with each other. And they share it so that one can increase the cadence of the data, one can observe large number of pulsars, but more importantly, use complementarity in different radio telescopes to improve the overall sensitivity of the PTA experiment. And in that sense, GMRT provides a very nice complementarity of the low frequency part, which neither the nanograv nor the EPTA nor the PPTA has. So we cover that particular band with great sensitivity. So one of the reasons why we are useful is to characterize the ISM effect. And the first of these effects is the dispersion smear, which is the dispersion caused by the electrons in the interstellar medium, which causes, as shown here on the right plot, a progressive delay in pulse arrival time. And this dispersion is a very strong function of frequency, so is more dominant at low frequency. It smears and broadens the pulse and thus reduces the precision of the TOA or increases the uncertainty. More importantly, the turbulence in ISM as well as solar wind variability and solar energetic phenomena cause slow variations in DM, introducing what is known as DM red noise, which is also covariant with the gravitational wave. In addition to dispersion, there is another effect, which is the multi-path propagation in the interstellar medium. And this broadens a sharp pulse, again, sort of increasing the uncertainty, and also introducing a bias in the dispersion measurements. Shown here on the left are the pulses from 477 to 327 megahertz observed using GMRT, and you can see the pulse progressively becomes wider and wider. And if we actually model this pulse broadening, we can fit a power law to that, and we can actually characterize this to remove the effect, this multi-path propagation effect, and improve the precision of the TOAs. Okay. Now, the most important thing here is not just the scatter broadening or dispersion, dispersive effect at low frequency. The more important part is the epoch to epoch variation of about 1 part in 4 in dispersion measure, which causes a systematic shift of about 200 nanoseconds. And remember, I said that we need order of tens of nanosecond precision in timing to be able to detect the gravitational waves. So removal of this becomes very critical and important. But more importantly, the epoch to epoch variation causes the profile change, and it causes systematic shift in TOA, which also varies with hand in hand with the variation in the ISM effects. And since these effects vary slowly, this presents a kind of a DM noise, which needs to be sort of removed. Given the strong frequency dependence, given the...
Dr. Joshi, 4 more minutes.
Oh, okay. Yeah, I'm almost, I would be done in that minute. So given the strong frequency dependence, UGMRT uniquely provides this frequency range and provides a niche capability for characterizing these effects. So here are some of the recent results. So we have been not timing as long as nanograph, PPTA and EPTA have been doing. They have been doing over 16 years. We started our experiment relatively recently in 2014 and so on. But the results are fairly encouraging. The plot on the left-hand side shows the dispersion measure variations of pulsar J1643 minus 1224 over a time span of about 15-16 years. The red points and the black points are using GMRT. The red points using only one band of GMRT, which is band 3, 300 to 500 megahertz, whereas the black points are using 300 to 1400 megahertz. And one can see that the measurements are not only consistent with the other PTAs, they are with similar uncertainties or are even better. The right-hand plots shows similar measurements for the for 3 other pulsars. And what would be very interesting to sort of note there is that the recent data, especially the last 1.5 year data, we are getting DM precision, which is much better than any of the other PTAs. So we can uniquely provide the DM information to the other PTA experiments. So that's where I think the GMRT's unique selling point is there. Okay, and so the typical precision which we are getting is for a single band. That is, if we use only 300 to 500, we get 1 part in 3 to 4. But if we use 300 to 1500, we get 1 part in 4 or 1 part in 5, which is unprecedented. And this precision is nearing that which is required to even probe things like frequency dependence of DM or to probe solar energetic events. And I'll have an example to show here. So recently, when we were analyzing the data from a pulsar J2145 minus 0750, we noticed an outlier in the dispersion measure, which, as you will notice from the y-axis on the plot on the left, is just 1 part in 3 away from the general trend in this particular plot. And when we investigated further, we found that this increase in DM resulted from an increase in the electron density in the solar system because of interaction between the earth-bound CMEs as well as the fast and slow solar winds. Okay. So it ties very neatly with this entire thing. So it so happens that with InPTA, we can actually do, we can even sort of measure CMEs traveling towards the earth and so on, okay, if we have a really high cadence. So this was an interesting and exciting result which we got from that. So that's the kind of precision which we are getting. So that brings me to the fact that how this can be used as a facility. Okay, so I see that I am part of a session where various facilities are being discussed. So InPTA is also a facility in that sense. And first of all, it is a part of IPTA, and both InPTA and IPTA will release its data. They are releasing and will release its data periodically. And this data is long time span, so it can cater to several astrophysical studies with low frequency gravitational waves. So you can do gravitational wave astronomy with the kind of data which is coming out. And I've just listed some 2 or 3 of applications there. I don't have time to go into details, but I can take questions on them if somebody wants more detail on that. Essentially, the amplitude and the shape of the spectrum depends on the history of the mergers in the galaxy evolution. And that depends on the scaling relations which you sort of adopt from the large scale surveys of galaxies and so on. So how the galaxies have been evolving and so on. It also depends on the eccentricities of supermassive black hole binary systems. Okay? And so given if we can constrain the spectrum of the gravitational wave in the PTA band, one would be putting very severe constraints on them. In fact, actually the limits right now which we have are already telling us that maybe in the final merger phase of a supermassive black hole binary system, the dynamic friction in the centers of the galaxy actually stalls the merger. So the time scale is not purely gravitational dominated, but is also dominated by the dynamic friction which the surrounding gas and stars are providing to the 2 black holes. So one can do exciting astrophysics with this, and you can come up with ideas and then test it against the data. So in that sense, the PTA can actually work as a facility. I've already given one example of how it is useful to study the solar energetic phenomena. But more importantly, since the solar system barycenter is the dynamic reference point for all the pulsar timing, our data can be used very well to put constraints on our own solar system bodies. Okay. And very tight constraints have been put, say, for example, on the Jovian system, where you can see one can go down to the 7th decimal place in terms of the mass of the Jovian system. And these are just two plots to show the improvement which one can get as compared to the ephemeries of the solar system which are already available. So on the plot on the right shows the different ephemeries and the corresponding mass measurements for the solar system bodies. And if we do a joint analysis with the PTA data, what kind of precision we can get. And you can see that there is almost a 20 times better mass determination which one can get from the PTA systems. A final word on possibility of gravitational wave detection. So LIGO has already detected gravitational waves, but in the PTA band, we have not yet detected gravitational waves. However, in the last 6 to 8 months, things have started becoming exciting. The NanoGrav and the PPTA have released 2 new data sets, 12.5-year data set by NanoGrav and 15 years by PPTA. And earlier data sets have been combined by IPTA as the DR2. So there are 3 data sets which are now publicly available. And all of these show significant detection of a correlated red noise process across all the pulsars. What is not clear is whether this common red noise has a gravitational wave nature. So the plot of the spectrum from the data for this common red noise process is shown here on the left, where the x-axis is the nanohertz frequency and the residuals are shown on the y-axis. And the middle plot shows the results of the Bayesian analysis for different models which have been fitted there, which is broken power law for 5 frequency and power law for 30 frequency. Okay. And all of these analysis clearly point out that one can rule out the clock errors, which is the monopolar spatial correlations, and the errors due to solar system ephemeries, which is dipolar. So certainly these are not the source of this common red noise process. What is right now being debated is whether timing noise or interstellar mediums could actually produce a common correlated signal. But more importantly, no quadrupolar helix and down spatial correlation has been seen in this data. So we are near, but yet not there. So with that, I sort of leave my conclusion here that PTAs aim to discover ultra-low frequency gravitational waves and employ the clock-like stability of millisecond pulsars to do that. There are 3 experiments which are established for a long time, and PTA has recently joined this using TIFR's facilities. And our main contribution from the Indian perspective has been in removal of red noise due to propagation effects with low frequency observations, and giving DMs up to a precision of 1 part in 5, which is unprecedented so far as the PTA measurements are concerned. Okay. There has been a high significance detection of spatially uncorrelated common red noise process, but there is no spatial correlation which has been shown to be consistent with gravitational waves. So it is still early days to call it a gravitational wave signature, but there is a likelihood that in the near future, such a signature will become more significant. Now, given these data sets, one can use the PTA as a facility because the data becomes periodically public once every 2 years or so, and it can be used to do a lot different kind of astrophysics. Okay? You can understand planetary bodies much better and study the solar phenomena. The stochastic gravitational wave background spectrum can constrain the galaxy evolution much better. And I didn't have time to go through the individual sources and say gravitational burst with memory that can constrain supermassive black hole binary models as well as the intergalactic medium. So there could be interesting gravitational wave astrophysics using this latest messenger which has come about, which could be done using a PTA data. So I end here. Thank you very much for your attention.
Professor Joshi, thank you very much for an exciting and talk, which has a potential for future discovery. So we are running late. So we have time for only 1 or 2 questions. If any of you have any questions, please unmute yourself. So are there any questions? If not, Professor Joshi, I have a very a naive question. In one of the slides where you showed how much is the improvement of the masses, I think, of the planet. So I didn't see Uranus and Neptune. Is there a particular reason for that?
Yeah, no, the uncertainty. Yeah, I can go back to that slide.
Yes.
This one you're talking about. So there is Uranus and Neptune there. Okay.
On the right side. On the right side, I didn't see them.
Yeah. So Uranus and Neptune masses are very badly constrained by even the existing ephemeris. Okay. So and even with PTA, you can't as you go further and further. You cannot constrain. See, the problem basically, as far as PTA improvement is concerned, is the time scale. Okay. So there was a time in 2010 and 11, we couldn't even constrain Jupiter because Jupiter has a 12-year orbit. So you need at least 12 years of data before being able to constrain its mass. Uranus and Neptune are even further away. Even Saturn is 29 years. Okay, so it will require another decade before one can constrain the Saturn's mass itself to a large extent. Okay, so Uranus and Neptune are even further away with a much larger orbital period. So it would be few decades before one can actually get that out. That's the reason for very large.
With the partial observations, you can't do this.
Yeah, with the partial observations, you cannot. You can put some constraints, but you can't get more accurate than what is available right now.
Oh.
Same is the problem. Same is the problem for the JPL or for the space people. They also can't do the same thing because the time scales are very large.
Okay, great. Thank you. I see no other hands raised. So thank you very much for this exciting talk. May I request you to unshare? And I would like to thank all the 3 presenters in this part of the session. So before we break for tea, I'm handing it over to Professor Dr. Shashibhushan Pandey.
Sorry, actually, Dr. Pandey is not here currently, and he has actually instructed to break for the tea. Yeah.
Okay. So since there are no other announcements, we'll break for the tea, and we'll meet back in say 15 minutes.
Yes.
Okay. So it's 4:10 now, 4:25. Thank you very much. Hi, Shashi.
Hi, Girish.
So we'll be starting in another 2 minutes.
Sure.
ನಮಸ್ಕಾರ. ಇದೊಂದು ವಿಶೇಷ ಪ್ರಕಟಣೆ. ನಾಳೆ ಬೆಳಿಗ್ಗೆ 10 ಗಂಟೆಗೆ ಫುಡ್ಕೋರ್ಟ್ ಹತ್ತಿರ ಬಿಬಿಎಂಪಿ ಸಂಜಯ್ ನಗರದಿಂದ ಕೋವಿಡ್-19 ವ್ಯಾಕ್ಸಿನೇಷನ್ ಅನ್ನ 45 ವರ್ಷದ ಮೇಲ್ಪಟ್ಟವರಿಗೆ ಹಾಕ್ತಾರೆ. ಎಲ್ಲರೂ ದಯಮಾಡಿ ತಮ್ಮ ಹೆಸರನ್ನ ನೋಂದಾಯಿಸಿಕೊಳ್ಬೇಕಾಗಿ ಕೇಳ್ಕೊಳ್ತೇವೆ. ಟೆಲಿಫೋನ್ ನಂಬರ್ 2423ಗೆ ಫೋನ್ ಮಾಡಿ.
So you are now to, we can just hold him the friend and give it to go. Any side effects?
All right.
Okay. Those will have the side effects. This is there for both, right?
No, that's very much. If people have
Shashi, shall we start?
Yeah, please.
Is Shianand around?
Yeah, can you hear me?
Yes, I can hear you. Okay, so welcome back to all of you. So this second session after lunch, have two speakers. Professor Shianand will be talking about the usage of 8 to 10 meter telescope. Without delaying, Professor Shianand, may I request you to share your screen? Yeah, I can see that. Can you put it in full screen mode?
I will do that.
Okay.
Is it fine?
Yeah. Thank you. Please go ahead. So I will inform you at the end of 20 minutes, and you will have 5 more minutes to finish, and then 5 minutes for question and answer.
Okay.
Thank you. You can start.
Yeah. So good evening. My title of the talk is Science with 8 to 10 meter class telescopes. But I will mainly focus on SALT because this session is also related to our own facilities. SALT is basically situated in Southern Africa, meaning basically in the southern tip of Africa in South Africa. And it is run by a consortium of several institutes in which IUCA is a member. And we have a share of about 6.5%, but now it is gone up to about 7.5 in the latest last year or so. And we are hoping to make it to 10%. Typically, SALT is a telescope which is effective aperture is something like 12 meter, but it's a telescope which is not steerable. So in some direction, effective aperture will be like 6 meter. In some direction, it is like 10 meter or something like that, right? So typically it has 92 mirrors, and you have a detector which is kept in the prime focus, and there are, at present, we have 3 main instruments. One is known as Salticam, which is like a imaging camera, which is also used as an acquisition camera. A Robert Stobie spectrograph or RSS, which allow you to do long slit spectroscopy, multi-object spectroscopy, and Fabry-Perot imaging and spectroscopy. One can also do polarimetry. Then high-resolution spectrograph, which is called HRS, which allow you to do high, medium, and low resolution. Basically, it varies between 20,000 to 60,000 resolution. And it is a fiber-fed instrument, so it has a good stability. And now you have possibility to do high accuracy wavelength calibration using laser comb. And you have some fast photometers. And at present, SALT is also building a near IR arm of the Robert Stobie spectrograph. So Robert Stobie spectrograph now operates between 3,200 angstrom to 10,000 angstrom with different grating combinations. Whereas RSS NIR will operate between J and H band in the NIR. And it should be available. It has been a bit delayed, but it will be available soon. Typically, what we have with IUCA, because IUCA observing time basically is shared by all the members of IUCA and members from the Indian universities, and also some institutional people from different institutes have also participated in SALT observation through some collaboration, either with people in the universities or with people in IUCA. Typically, a year consists of 2 cycles. Each cycle, IUCA has about 90 hours of observing time. Because in the case of SALT, we don't talk about nights, we talk about observing time, because observations are carried out in a queue scheduled manner, whichever is the best suitable observation that will be performed at a given time. If you take 8 hours per night, so we have about 23 nights per year. Typically, what happens is that even though we have 90 hours, we allocate time for 90 hours per cycle. It is not that all the blocks will be executed. And typically, we are getting between 60 to 70%. Conservatively, if you take 60% of observing time, that means like we have mean effective nights of about 14. Because this is, you remember, if you go to an observatory, this 90 hours means that it is not setup time and in between things are not there. It is 90 hours means it's basically direct observations. So even in normal observatories, the efficiency, if you take how many hours you expose your CCD to the sky compared to the total, you will be somewhere, best observatories will reach about 70%. So the 60% is what means like 14 nights of data we will get, meaning the equivalent of exposure times, right? So this observing time, whatever we have, is divided into 3 categories: priority 0, 1, priority 2, and priority 4. Typically, priority 1 has 30% of time, priority 2 has 30% of time, and priority 4 has 40% of time. And basically, 1 and 2 observatory will make sure that if you are in a category either 0, 1, or 2, you will definitely get data within 6 months. Means like there is a 90%, 90 to 95% chance that you will get. 0 is assigned for whatever you call target of opportunity. So typically, band 3, priority 3, I put priority 4, sorry, it should be priority 3, typical completion rate will be about 50%. Okay, so this is just for give an idea that what kind of observing nights one has. So what kind of programs one is carrying out, because there are, so we have to also allocate times for bright night and dark night and things like that. So we have programs from IUCA plus our associates covering a very bright source science and to a very faint source science. I will give some examples of these things we have done in the recent past. There are programs to monitor emerging outflows, ball outflows. And we have also program, I will just explain to them. We have a program to discover high redshift quasars, which may not be very bright. And we have also programmed to target high redshift galaxies to measure the star formation and other properties. High redshift means we are talking about redshifts of around 2 to 4. And also there is a program we have dedicated, at least we give some 10% of the time for observatories dedicated transient sources, because you may recall that first kind of spectra for the gravitational wave event, first gravitational wave event was also actually taken with salt. So other sort programs people have carried out. These are not by IUCA members. These are either from IIA or from TIF or from other people. So for example, measuring redshift of peculiar galaxies, metallicity estimates of young stellar object using high resolution spectrograph, galaxy morphology, and coordinating between AGN observations with SALT and AstroSat. We tried one, but it was not very successful. I think there is data taken on one attempt, but I don't know anybody has analyzed it, where we have some concurrent data with AstroSat and SALT. Coordinated observations on some rapidly varying compact objects. So here, basically, this is part of networking, where either from GRB community or from supernova community or from the gravity wave community, people have performed observations. So let me just highlight few science cases we have carried out in the recent time with SALT from IUCA side, and what is the impact it has produced. And just to give a flair of these things, one of the thing my colleague Neeraj Gupta and myself are involved is what is known as Meerkat absorption line survey. This is a survey of H1 21 centimeter absorption gas in the high redshift towards radio loud quasars. Then we have about our aim is now to get about 1,000 sight lines observed, and we need targets for these observations. What happens is that, as you all know, that typical quasar surveys are based on optical colors. We are not sure, like when we do color selection like SDSS, you are not sure like whether you are detecting all quasars. So there, it is possible that there are some quasars which are obscured by dust, or either in the quasar itself or in the medium between quasar and us. So we miss such object, which means that when you do absorption line study, you will be looking at objects which are clean and may not be detecting highly dust and molecular rich objects. So we started a program with SALT to search for unknown quasars in the past, but not necessarily selected through color selection in optical. So what we have done is that we have actually looked at Weiss color. Basically, this is a near infrared Weiss bands, and we can plot color plot of Weiss, and the green contours which is shown in the left side of the plot basically peaks if the objects within this region of the color plot intersecting with that magenta color will give you higher redshift quasars. Since our absorption line survey is aiming at gas up to redshift 1.5, we are looking for quasars beyond redshift 1.5. We have, at present, we have detected about 300 quasars. The redshift histogram is shown in the right panel. And these quasars are reasonably red, reasonably faint, and they are at higher redshift. The median redshift of our sample is about 1.8. There are about 100 quasars at redshift about 2, and there are about 200 quasars above redshift 1. This sample will be supplemented with other known high redshift quasars in our survey. And for this community, what will be interesting is that you have discovered about 27 blazar candidates, because these are not known blazars. We went and looked at the optical spectrum, and we realized that there is no features other than continuum. And in the photometric thing in available in ZTF, and we see that they are highly variable sources. So this is some these objects what we are concentrating are extremely bright in radio. They are basically 20 millijansky kind of flux density. So these are one of the most radioluminous quasars known in the universe. Of course, we have in this survey has discovered the highest redshift quasar at redshift of 5.06. This actually has close to 1 Jansky in some of the relevant radio frequency ranges. And since the redshift is very large, this is one of the, I think it is the radio brightest object in the sky now, because we have not yet published, because we have allocated time in VLT. Because of COVID, the observations are not executed, but we are expecting the data to be available in the coming months to measure black hole mass and other things using infrared spectra, where we will be probing the optical wavelengths. Of course, we have discovered several broad absorption line quasars. But what we are finding is that the typically broad absorption line quasars are 10% of the total population, but in this survey we are detecting only about 3%. It is intriguing because people thought that you are dust unbiased, so you should be detecting more Ball quasars towards radio detected objects. But what we find is that it's quite possible that our radio sources are cleaned up the region and the Ball fraction may be very low. So we are investigating Ball fraction as a function of whatever you call radio loudness and radio orientations, right? And we also discovered something known as damped laminar alpha absorbers. These are nothing but this kind of strong absorption, which is shown in the left-hand side, will occur when our line of sight passes through the region close to galaxies within 50 kiloparsec to 50 kiloparsec to a galaxy. And again, here again, our survey now is completed only for 30% of our quasars. Remaining 70%, we are continuing our survey. Already, we are detecting twice the number of more DLAs than what is known before. This again points towards the fact that the universe which we think we have observed with SDSS may be slightly different from the universe we will be observing if you have dust unbiased samples. So this is too early now. When we finish this survey, we should have at least 4 to 5 times more detection that will confirm these tentative identifications. The second thing, so basically what is the summary here? We have found the redshift 5.2 quasar, and this will be the most luminous quasar known. With GMRT, we have searched for 21 centimeter absorption from all the redshift 2 greater than 2 quasars. These were discovered by SALT. Followed up in GMRT, we have detected absorption, 21 centimeter absorption in a quasar where it is the gas is infalling at a velocity of 1000 kilometers per second and has a temperature of 100 Kelvin. Again, the temperature measurements are based on spectra from GMRT and spectra taken with SALT. So we are finding excess number of absorbers at the redshift of the quasar itself. It looks like these quasars with strong radio emission are living in some sort of high density environment, because of which you find a lot of absorption with redshift, even redshift greater than the redshift of the quasar, which is indicating that you have peculiar velocities. As I mentioned before, we have less number of Ball quasars, and we are finding excess number of damped laminar alpha absorbers. So these are again interesting thing for people who are interested in quasar absorption spectroscopy. The other thing which we try to follow is that it is well known now that if you go close to the quasar can actually ionize the surrounding region, and if there is enough gas in the surrounding region around quasars, they will start emitting Lyman alpha line due to recombination. So which means that if a quasar is living in a overdense region, and if this region is illuminated by quasar light or shock heated by the jet which is propagating, then it will get ionized. When it recombines, you will get Lyman alpha, and this is what is known as Lyman alpha halos. And people usually detect this emission up to several tens of kiloparsec around quasars. And here is one of the examples. In the left-hand top panel, you see the radio image of our quasar. The cross is the location of the optical source. The two horizontal lines you see are the positions of our long slit. When we take the spectrum, the long slit spectrum is shown in the left-hand side panels, and you can clearly see in the case of Lyman alpha and carbon 4, the vertical extent is about 10 arcsecond, whereas our seeing is close to about 1 arcsecond. 10 arcsecond at these redshifts correspond to something like 80 kiloparsec. So basically, you are seeing extended emission around these quasars going up to 80 kiloparsec. And in the bottom left panel, you remove the quasar contribution and look at the diffuse emission contribution, again confirming that you have gas which is extending up to 80 kiloparsec. Now that we know there is an extended gas and we know the wavelength, SALT also allow you to do the narrowband imaging. This is what is shown in the left and bottom panel, where we have whatever contours you see in the dark is the Lyman alpha emission coming from these galaxies in the narrowband imaging obtained with SALT, overlaid with UGMRT images. And again, the longest extent we are measuring is close to 100 kiloparsec. So what is happening now is that we have 24 quasars in our sample for which we can do this exercise. Of course, each observation will take about 2 to 3 hours, because even with 10 meter, we have to go pretty deep. And SALT is not necessarily 10 meter at all orientation. So we are treating it like something like a 6-meter telescope. Typically, each object we observe for about 3 to 4 hours. We have a total of 24 objects with redshifts which are ideally suited for this. We have done this long slit spectra, narrowband imaging, and it will be part of one of my student Gitika Shukla's thesis. Of course, here I show the examples of cases where we can see this extended emission. The maximum extent we are seeing is up to 120 kiloparsec now. So what do you do with these things? We measure the detection fraction. Now we calculate for each of these halos. We calculate what is the total luminosity, which will be proportional to total amount of gas which is present. What is the energy which is falling in? We can also map the velocity. We can see that whether this gas is infalling or outflowing with respect to the quasar. And then for quasar, we have measured all the properties related to black hole mass, UV ionizing luminosity, radio power, radio size, Eddington ratio, how much associated absorption is present, and things like that. That means we characterize the property of the quasar, we characterize the property of the diffuse emission, and then one can make a correlation between them. The strongest correlation we find are among our 24 quasars. There are about 6 quasars which show that extended radio emission, and we find that the Lyman alpha emission luminosity is directly correlated with this extended emission. In fact, there is also directional dependence between the alignment between the radio jet positions and this Lyman alpha emission. So we are basically studying this in detail, and the detailed paper is about to be submitted, and the thesis of Gitika will be submitted in coming months by August. The other thing we look at is that when we look at quasar absorption lines, one is whenever you look at a quasar, you find absorption produced by intervening galaxies. One can ask the question, if you say that here is metal line absorption produced by a galaxy, do you see the galaxy? So what basically you do is that you look at the left-hand side plots, whatever we call it as Q is the location of a quasar. And in the spectrum of the quasar, we find an absorption at some redshifts, 0.5. Then we can ask a question, is there a galaxy at this redshift which is responsible for this absorption? So this is the program we have started with SALT again. What we do is that we have narrowed down a small redshift range where we identify all the absorption seen in the SDSS quasars. Then we look for the galaxies which are responsible for this absorption. And here is an example of nearest galaxy. And in the top panel, you see there is clearly a single galaxy present close to the quasar. So we can put a long slit between aligned with quasar and the galaxy, and the spectrum is shown in the top right-hand side. So we are able to get such a spectra up to 23rd magnitude where you can even do absorption line, not only this emission line things. And you can see that we have O2, H alpha, H beta absorption. We can also emission. We can also see calcium, H gamma, higher hydrogen Balmer line absorptions. So this we can use to study the association between quasars and quasar absorber and galaxies. In some cases, we don't have one galaxy. We may have several galaxies which satisfies the requirement of the redshift of the absorbers. Then what we do is that SALT allow you to do what is known as multi-object spectroscopy. And here is an example of this. All the red squares are the slitlets we made, and we align the sky plane in such a way that we can observe several galaxies in one go. In principle, we can observe up to 40 galaxies. The maximum we have tried is about 16 galaxies where we could get spectra in one go, and the example is shown in the left-hand side. So what has happened is that this is a PhD work of another student of mine who was just started 2 years back, Labanna Guha. And he first started with looking at 26 galaxies, and we are able to detect something like galaxy association for about 17 cases without any ambiguity. Once we have these images and spectra, we are able to measure various quantities like the star formation rate, stellar mass, dust reddening, impact parameter, what is the distance between galaxies and this, whether the galaxy has a wind, all these things. And then we can establish the connection that what is causing this absorption. And considerable progress is made in this field. And for people who are working in this field, we are actually concentrating on a particular kind of objects known as strong MG2 absorbers, ultra strong MG2 absorbers, which has some specific reason that these are the absorbers with extremely large outflows. So these are associated with galaxies with extremely large outflows. And the SALT is now allowing us to detect galaxies. And in fact, we are able to do spectroscopy of objects even when they are not completely decoupled with respect to quasar in the quasar PSF in the spatial domain. So this is very very interesting. And last cycle we tried to do this with 3.6 meter also, but probably we have not detected the galaxies. But this we will try with brighter galaxy to see whether some of the brighter candidates can be done with 3.6 meter telescope. The last case, last set of program which basically we do it during the bright period is what is known as variability of broad absorption line quasar. Here we know that 20% of the quasars show very large outflows, and these outflows goes up to 0.1 C. So we identified what is known as ultra fast outflows. At least this community, you know about ultra fast outflows detected in X-ray bands. These are typically above 10,000 km per second velocities, going up to 0.1 to 0.15 C. And here is an example of one of the quasar where you can see, like in the extreme left end, there are some absorption. These are absorption produced at very large velocities. I'll just explain to you in the next plot. So here are some examples.
Dr. Srianand, 3 minutes.
Yeah, I'm there. Here are some examples of ball variabilities, and you can see that you can just focus on the left-hand panel. In the top panel, you don't see any absorption. In the second panel, you suddenly see an absorption. And the third panel, you see that absorption is moving towards the left-hand side. What is plotted here is nothing but a spectrum of the same quasar taken at different timescales, focused in a small wavelength range. This quasar suddenly shows an emergence of an absorption. This absorption is moving in towards the lower wavelength side. That means this gas which is producing absorption is Doppler shifted towards you, and its velocity is keep on increasing with time. This is what is known as acceleration. And if you focus your eye on the left-hand side, right-hand side panel, and focus on the thing which monitored as C, you see an absorption which is present at one epoch. And if you go to the next spectrum, you see that suddenly this absorption disappears. So this is known as the disappearance of absorption lines. So what we are focusing on is that we have a sample, we monitor them, and we try to see the emergence, quantify emergence, disappearance, and acceleration. And these are extremely important for quantifying the models of accretion disk winds. And our monitoring is extremely at a short time scales. We monitor objects at a rest frame time scale of between 1 month to several years. So this is one of the biggest data set we have created now, about 65 objects monitored at very frequent interval, and this will be analyzed. This will be what of Aramal's thing. So just to summarize, we are following up about 60 objects with velocities greater than 10,000 km per second, and these objects we are monitoring time scale go up to 10 years. We wish to quantify the frequency of occurrence, emergence, disappearance, acceleration, optical depth variability, etc. And this variability will be correlated with photometric light curves, which are obtained from PTF and other all-sky monitoring programs. And our main aim is to identify the location of the outflows in the galaxies so that we can talk about what effects they have in what is known as AGN feedback. I went through very rapidly because I want to give the flavor of what all can be done with SALT. And that's all I wanted to say. Thank you very much.
Thank you very much, Professor Srianand. We have time for a few questions. If any of you have questions, please raise your hand, or you can unmute and ask the question. Gopu, I see you have unmuted. Do you have a question to ask?
Oh, yeah. Nice talk, Srianand. So this is the question about, you talked about many of this, high redshift quasars after, more than 2. Do we have, identified with SALT or other telescopes, the parent galaxies, and do we have any bulge luminosity measurements of those parent galaxies?
Not for all galaxies. We have identified, so these are radio galaxies and quasar. For a redshift below 0.6, we have about 30 to 40 new very red objects.
Mm-hmm.
So galaxy identification is a bit difficult because we are in the southern sky. With our SALT, we have identified some galaxies, but we have now tied up with DESI program. You know the DESI survey.
Mm-hmm. Mm-hmm.
So MALS and DESI we have combined, and we will have a host galaxy for at least redshift below 1 objects in our sample. Redshift 2-3, it will be very difficult.
Very difficult, yeah, that's right.
Only one radio galaxy we have discovered, which we published just now. This is one of the biggest radio galaxy at redshift 3.2. That is the host galaxy property we could measure because it was completely dark in optical, but produces a huge amount of Lyman alpha halo. Because this you won't see in optical image. We did the blind offset pointing, and we detect this galaxy only in Lyman alpha emission. Then afterwards we realized that it is visible in the infrared. Now we are trying to observe them in the far infrared, and these galaxy properties are well characterized. We have measurements of reddening and other quantities.
No, I was just curious if you have the black hole masses not around 10⁶ or 10⁶, but slightly higher, and then you have a bulge luminosity and see whether there's this correlation exists, which is usually in the lower part of the graph. So it has not been pushed to the higher.
No, we measured the black hole mass. Most of them are very massive. They are in the other extreme actually, because these are by construct we have picked.
Correct. That's what I felt. Yeah. In that case, if you measure the bulk, so this the famous Cormandy kind of correlations can be checked at high black hole masses.
Measuring host galaxies of these objects will be very challenging.
I agree. I'm just wondering, if you have been lucky enough with so many of them. Yeah.
So that's what I said. There are two quasars. See, one quasar, one radio galaxy where we could do. We have identified two type 2 AGNs. Again, we are trying to see whether we can get the host galaxy, because here the quasar optical light is removed. So where you get a chance to detect is that quasar optical light is faint, but we know from the narrow line regions that these are extremely powerful AGNs. We are also seeing Lyman alpha emission extending up to tens of kiloparsec. So this is powerful AGNs with high black hole mass. But now we will be able to look at the host galaxy through infrared. So these targets may give you some hint on what kind of objects they are. So this we are trying.
Okay.
So till now, I think 3 objects we can do.
That's good enough. I mean, because there are not many samples at that kind of high masses. So yeah. Thank you.
If there are no other questions, let's thank Professor Shriyanand, and thank you very much for sticking to time. So we'll move on to the last presentation of this session. Professor Devendra Oja will be talking about the ground and space-based infrared telescope. Professor Oja?
Yeah, can you see my slide?
Yeah, I can hear you also. Please go ahead.
Okay, thank you.
I'll inform you at the end of 20 minutes, and you will have 5 minutes to close and 5 minutes for question answer.
Thanks. Thank you
very much.
Okay, so good evening, and first of all, I would like to thank organizers for giving me opportunity to talk in this conference workshop. So basically, this is the outline of my talk. So I will talk about instrumentation activities which we have been carrying out in TIFR, which is based on balloons as well as ground, and now more recently on satellite. So balloon program in TIFR has been running since last 4 to 5 decades. And it started from basically the bolometer arrays to mapping star-forming regions. Now we are basically have gone to spectroscopy of star-forming region. Then late 90s, we started our ground-based program because at that time 2-meter class telescopes were installed in India, and we thought that we should set up NIR facilities, dedicated NIR facilities in India on these 2-meter class telescopes. And with this experience, late 2000, when we have opportunities from ISRO under a small satellite program, we actually went to the satellite-based programs. You can see one of our small satellite payloads. So I will briefly talk about these different programs in this talk. So basically the activity which we do, basically participate in instrument development for ground and space astronomy for Indian facilities, but most of these facilities we develop is not specific for our own science goals. They are basically driven by the science from other research areas, and they are basically the general purpose facilities which has been used by other observers, astronomers. So considering that in last 7 to 8 years, we have basically concentrated mainly on ground-based instrumentation as well as parallelly on space-based instrumentation. So for example, like TIRISPEC, which I will touch upon very briefly in my later slides, were basically meant for one of the side ports of Ares DOT right now, 3.6 meter telescope, but it turned out that the side port of Ares telescope was not compatible for TIRISPEC, so it was shifted to 2 meter Himalayan Chandra telescope in 2013, and we had a first flight in 2014. And then TIRCAM2, which is a very unique camera which works beyond 2 micron also, up to 3.7 micron, actually have gone from Mount Abu to IGO, telescope, and now its home is at Ares. It is a permanent instrument at the side port of Ares telescope. And TENISPEC, which is the major workforce right now, is very important instruments. I will give some detail about this instrument, which has been opened partially for Indian and Belgium astronomers, is giving quite interesting results. And this is quite unique instrument because it operates simultaneously from optical to infrared wavelength. And of course, I will talk about IRSIS, which is basically the payload for a small Indian satellite. And after spending time for more than 1 decade, finally, we have actually come up with the completion of the laboratory model phase of this payload. And there are a lot of challenges because this was the first infrared satellite, and there are many other challenges like cryogenics, cooling, and other things. I will give some details about that in my talk. And also we have been keeping our interest on scientific ballooning, and it has gone many revolutions. Scientific ballooning in India is almost like more than 5 decades old. It has started from cosmic rays to X-rays and infrared astronomy. So currently only infrared astronomy experiments are being carried out with balloons, and it's still quite competitive because advantage with balloon is that you can actually map the large area of the region, either star forming region or galaxies. So I will try to convince why ballooning is so important. So let me start with our space program. So this is the payload which we have developed. So we had an opportunity in 2006 when there was an announcement opportunities for a small satellite program from ISRO. And so we proposed an infrared spectroscopic imaging survey program. Basically, this is a survey telescope because at that time there was no survey programs in infrared wavelength, although there was an ISO satellite which was launched by ESA, European Space Agencies, and Akari was later on launched. However, those kind of programs were basically covering the same wavelength range which we have planned for this IRSIS, like 1.7 to 6.4 micron. However, they were dedicated to specific science project, not for the all sky survey. So in IRSIS, we plan to have a spectroscopic survey from 1.7 to 6.4 micron, basically covering 50% of the full sky in 2 years, including the galactic plane. And this is a very shallow program. I will tell why it was shallow, but for the uniform depth, so that was the importance of this survey. Uniform depth, because we are doing with the same sensitivity, the survey for all sky regions. The resolution of the spectroscopy was moderate from 100 to 120. The key science tool for IRSIS, because this wavelength is very rich with all kinds of lines from molecular, atomic, and ionized lines. So basically, idea was to detect several broad spectral features and strong lines due to interstellar gas and dust component of the ISM. So we have like water, carbon dioxide, and many hydrogen decomposition lines within this wavelength range. And also, if you have a seamless infrared spectra, then one can actually classify the stellar populations of the galaxies and talk about different populations. Right now, one can actually study classification of stellar populations using kinematics or photometry like Gaia, for example. But once you have a seamless spectra, infrared spectra, one can actually pinpoint the nature of each individual sources in different population of the galaxies. And another advantage of doing this survey is to have a complete census of low mass objects like brown dwarfs in nearby molecular clouds, so that you can actually characterize these brown dwarfs in different directions of the galaxies. Apart from these key science program, also this IRSIS can give target of opportunities class of studies, because one can study time critical phenomena like nova, supernova, and so on. So that is also one of the possibilities which exists. However, the major challenge with the small satellite program is that there are constraints from ISRO, because it is supposed to be one of the co-passenger on PSLV. So there are constraints from size, mass, and power because it is one of the co-passenger. So considering this constraint, we have come up with a medium-sized telescope of 30 centimeter diameter, which is cooled at 100K. This is a passive cooling. I will talk about why we are going for passive cooling. And instantaneous field of view of this IRSIS is 15 by 15 arc minute. And this is because we are using an integral field unit, which are basically the coupled with infrared fiber bundles, and which is another challenge because fibers has not been used in this space so far. So this was another major challenge. However, fibers can give you the multiple object at the same exposure time, so that's why you can cover a large field of view. The sensitivity of IRSIS is around 14 magnitude for 3 sigma in 10 seconds. That's why it is a shallow program, but nevertheless it's covering a quite whole range of objects, basically covering all the 2 mass object which has been detected. And also one can study the diffuse emission within this wavelength range. And I have already talked about from ground, you can observe this through this wavelength in K, L, and M bands. However, it's very difficult to observe beyond 2 micron from ground because of the high thermal background. And like I said, ISO and Akari has actually covered some of these wavelength band. However, these are the dedicated programs for specific science project. Another importance of this wavelength is 1.7 and 6.4 comes from the, basically it is the cutoff of the HST NICMOS camera and the cut-on for Spicer Space Telescope IRAC instrument. So that's why this wavelength has not been covered in detail so far for survey kind of observations. So considering all these constraints and difficulties, we have come up with this kind of topology for IRSIS, where the light from the telescope is coupled with the micro lens, and then the infrared fiber bundles are coupled from micro lens to the other end of the micro lens here, and then they terminate as a multiple slit before the spectrometer. And since we are talking about almost like a 4 octet of wavelength here from 1.7 to 6.4, so we have decided to go for 2 channel of spectrometer, like short wave from 1.7 to 3.4 and long wavelength from 3.2 to 6.4 micron. This is because of the cutoff of the mercury cadmium telluride array also, which we plan to use. And considering this topology, actually the advantage is that you can get simultaneous spectra from all sub-areas of the sky, basically from different fibers. And we plan to have no moving parts in this payload. And a detector here, optical component here for dispersion is we are using grating, and detector is cooled at 80K, which is the optimum temperature for H1RG array, infrared array, whereas telescope has to be cooled at 100K through passive cooling. So after doing almost like a more than 1 decade of our work, so just to tell you that in 2006, when we submitted this proposal to ISRO, then the ADCO subcommittee actually gave us a go-ahead for demonstrating the laboratory model for IRSIS, because there are many challenges. One of the challenges I told about the infrared fibers, particularly the rigidity and stability of this fiber during the launch of the satellite. And another is the cooling, basically how to achieve the 100K in the low Earth orbit, because we are planning for this LEO orbit for this. So considering that, we developed a laboratory model by downsizing our parameters, particularly from 1 to 2.5 micron. And at that time, those kind of fibers were only available to demonstrate in the infrared wavelength. And so these are some of the components which were developed in our own TIFR workshop. Like this is a spectrometer, complete spectrometer with integral field unit, is the telescope. And finally, we submitted our lab model closure reports to ISRO in this year, in February 2021. And next step is to go through the PDR of this IRSIS for engineering and flight model. So let me tell you about the fiber, because these fibers have never been explored in space so far. And the most difficult part is to couple these fibers to microlens through glue so that they stick there during the vibration and so on. So this is just to show you that during the laboratory phase model, we have used actually 45 fibers. Actually, in the final model, we are going to use more than 1,000 fibers. So this is just to show that, for example, this is the cartoon where F12 beam from telescope is coupled from microlens array plate, and then there is a fiber plate here where fibers are glued to microlens, and other end of the fire actually terminates at slits, and that's why you disperse light through the grating. So this is what we have actually achieved in the lab. Finally, these fibers up to 2.5 micron work perfectly fine, because you can see that GMAX modeling actually showed that what we have achieved as a first light is quite exciting. This is the image taken at the K band, so we can see different orders here. Similarly, we have used other filters also available in P band. We can actually get light through the infrared fibers, multi-slit kind of orientation in this light as per our expectation. Another major challenge, of course, was having a passive cooling. So we have decided that it should go to the low Earth orbit at 650 kilometers. So basically, it is like 6 a.m. to 6 p.m. kind of orbit, and the one complete orbit takes 100 minutes for its to around the Earth axis. The only challenge here is that it has to be always away from the Earth and Sun because of the lot of background. And so when it goes to this kind of orbit, it has to maneuver multiple times from each pointing. So we decided that we go for the typical, design for the thermal passive cooling, which is called V groove. And this V groove are actually developed first time for Planck mission. Of course, Planck mission was targeted for L2 point, where there are not much difficulty because it's already a cool point. However, in more recently, Sphere X, which is actually going to the low Earth orbit, has actually demonstrated that with a smart thermal designing, one can actually achieve like 75K kind of cooling into the inner radiator, which is called photon shield here, which are called sun shield. So based on these, we have actually designed this VV groove thing, which we have done a lot of modeling in our lab here. And of course, this is not our expertise. So now we are actually taking ISRO's help to how to model this so that we can achieve 80K, because detector is sitting in the inside of the last sun shield or radiator, and it has to be cooled at 100K, whereas telescope structure has to be 100K. So that is the quite a big challenge. However, ISRO is quite keen to take up this challenge, and I think if it works, then it will be good. It will become actually pathfinder for any L2 mission which ISRO is planning, for example, like ExoWorld and so on, because they also need this kind of V group design for the passive cooling. And on the same time, we are also working on developing a cryogenic thermovac chamber with industry in Nasik. And this will be one of the unique thermovac chamber only outside ISRO, where it is completely cooled by the liquid nitrogen, so that we can actually hold this telescope inside this thermovac and get the simulated results. And these facilities will be open to any other person who is using for cooling purposes of their telescope or detector. Now let me move to the ballooning part. So before going to our own experiment, let me just tell very briefly that scientific ballooning has been in continuing in TIFR balloon facility, which is a dedicated national and now international facility in Hyderabad since last 4 to 5 decades. For example, as you can see, I have just plotted here some statistics in this pie chart that from 1999 to 2018, almost we have 41% of astronomy experiment, although after late 2000, we don't have enough astronomy experiment because of AstroSat and other things. So we are continuing with the infrared experiment. But one of the important to sustain this facility, which was established in 1969, there are many challenges, and to really having to make it competitive worldwide, one has to really augment balloon technology and instrumentation. So as you can see in pie chart, we have always experiment which are basically to augment this balloon technology and instrumentation. So half of the experiment, like 22% out of 40% of astronomy experiments are actually the technology driven experiment. We always augment our technology, not only on balloon aspect, but also on the instrumentation aspect. And another advantage of this facility is that all things are under one roof, like balloon production, launch, data collection, emission and recovery of payload you can do. So there's no other facility in the world where such kind of all I mean things you can do under one roof. And we have now made basically 2 seasons for balloon experiment, but nowadays we also have balloon experiment during monsoon because there are a lot of experiment on atmospheric science of national importance. So let me come to our own experiment, far infrared astronomy using balloons. So this is in collaboration with our Japanese colleagues, where we are basically using this 100 centimeter TIFR balloon for right now for Fabry-Perot spectroscopy. The primary mirror is 100 centimeter. So this is the heaviest payload which we have launched from balloon facilities. The mass of payload mass is 850 kg. However, the total payload becomes 210 when it is integrated with balloons and other accessories. It has been used in 1983, but it has gone in many revolution and advancement in technology. And we have our own robust signal processing and image processing schemes developed in-house. And based on that, we can actually get the diffraction limited kind of resolution on our spectroscopic observations. And right now we are using a very special Fabry-Perot spectrometer, which is called scanning Fabry-Perometer, unlike the fixed Fabry-Perometer. So this fixed Fabry-Perometer is tuned to the C2 line. So our main target is the singly ionized carbon line to basically study the photodissociated regions. It is tuned to 157 micron. However, since we are using the scanning Fabry-Perometer, so we can actually scan the line around region around this C2 line so that we can get not only the emission from the gas as well as from the continuum emission. So one can study both gas and energy budget of gas and dust emission. So this is just to show the kind of experiment like we started this spectroscopy from 99, but in last 2 years, 2017 to 18, we have actually 4 balloon flights for this Fabry-Perot spectrometer, and it just shows the it's a very large scale experiment. I mean, total length of this experiment is like 200 meters. And our main target is basically the star forming region in the southern hemisphere. So that is the advantage from Hyderabad because it is just 9 degrees above the equator. So one can actually access all the many important star forming region in the southern hemisphere. And the main our target for this balloon observation is to study the kinematics of photodissociated regions or photon dominated regions. And basically the PDR is the interface between ionized region and molecular region shown in this cartoon. And one can actually see in real observation like this image in the left where you see ionized emission, free emission in radio in the center. Then blue is the C2 emission, which basically traces the PDR, and then you have a green in the molecular emissions. So this is the kind of a structure you see, and this PDR is very important to study, particularly in the high mass star forming region. And this is basically originated from the photoelectric heating of the via power emission in the dust. And also it is because of the cooling of the C2 line, basically the fine structure lines. And since ionization potential of carbon is less than hydrogen, so it easily dissociates. And one can actually see, and then it becomes a major coolant, dominant coolant line in the star forming region, particularly at the low density. And that's why it becomes very important to study the physical and chemistry properties of this star forming region through PDR. And of course, now from Sophia and Herschel, one can actually get such kind of images. However, the advantage with the balloon is that you can actually get the large scale structure like here. So basically you can scan the large region using balloons. For example, here in this plot, which is compared with the Herschel dust emission, you can actually go through half degree by half degree region and map such a large regions and study. So it is very important to understand the global properties of the photodissociated regions, and that can be done by the balloon observations. And then one can also compare these C2 maps with the available other data like dust emission from, for example, in near infrared like warm dust, then you have cold dust in longer wavelength region and PA. An advantage with our joint collaboration is that we have a direct access of Akari data, particularly for these kind of observations. So this is just to show one example of a star forming region. For example, advantage with balloon is one, I said, the large area you can map. Other is, for example, this is a typical scan map using fabric spectrometer, one scan. So if you do the fast scanning mode, actually you can have a very good filling factor in the map, and you can get very good dynamic range using balloon observations. And another major results which we have got with our experiment is basically, of course, it was known in the literature earlier that C2 correlates with PA at all scales, but never seen directly with the observations. And this is the first time with balloon observation we found that C2 basically correlate with the PA at all scales, actually better than the dust. And why it becomes important? Because the role of PA in photoelectric heating of gas is very important in PDR. And now we understood very well that why PA is very important in this region. Now let me go very quickly to the infrared astronomy from ground. So our infrared astronomy from ground, as I said in the beginning, has been basically developed for the Indian telescopes. So basically, just in brief, I'll tell that the program has basically evolved from a very small array like 52 8 by 62 90s for a small telescope like Mount Houck telescope 1.2 meter to a larger array like 2K by 2K, and with the largest Indian telescope 3.6 meter telescope. And I will tell you now, maybe it's time to go to the multi-slit kind of development of spectrometer. So this is about one of the development which I think Professor Ram Sagar have spoken in the morning. So I will just talk about the uniqueness of this TIRCam2. Basically, one of the uniqueness is that it is the only camera available which works beyond 2 micron right now in India. Another advantage is that it has a PA filter and NBL filter. This is the NBL is used as a continuum for PA. So one can actually study the PA emitting regions using this camera, although it's very difficult to observe 3.3 micron from the ground, but nevertheless, surprisingly, we have actually observed these regions from the DOT, which is just at the altitude of 2400 meters. So this is, of course, the capability of TIRCam2 can go quite deep. This is just left-hand side is just 10 to 15 minutes of exposure, and one can still go 19 magnitude in J and 80 magnitude K. But this is what is most important is that we can actually detect photons at 3.6 micron, which is very difficult from ground because of the thermal background. Nevertheless, we have gone up to 9 magnitude detected from there. And the advantage of this that most of these bright objects, which are very important objects like protostars, or young stellar objects which are saturated in WISE and Spitzer observations can be actually observed, and they become very bright in this longer wavelength and can easily be observed by TIRCam2. Another advantage, which is our own interest, is to observe in PA emissions so that we can study the PDR regions. This is one example, very short total exposure, 13 seconds. One can actually detect PA from the star forming region like SAR plus 61 region, which is compared with this Spitzer. So advantage with TIRCam2 is that it has a dedicated continuum filter. So what you see in the left hand side is only the PA emission after subtracting the continuum, whereas Spitzer 3.6 micron is a wide band which has both continuum and PA. So you see a very strong continuum source in the right hand side of Spitzer image. And this image already shown by Professor Sagar in the morning is about PA emission also detected from the planetary nebula. So one can see this last panel where you see the shocked ring-like of structure which is expected in the PA from this planetary nebula. And now we are actually, there is a lot of users demand to have a fast readout for TIRCam2. So we have developed now, our software has been debugged and incorporated the sub-array mode in TIRCam2. So full frame is actually 512 by 512, but now we can actually go up to 16 by 16 pixel in sub-array mode. And these are some example which has been actually shown in the morning, like one can do occultation kind of observations, but this kind of capability like spectral imaging, which is shown here in the left panel. So such rapid acquisition now will be very useful to record light curves of fast events that occurred in few millisecond kind of observations. So right now, TIRCam2 can faster readout is 10 millisecond. We are trying to go much faster by actually debugging our hardware also. So this is another unique properties which has been implemented in CAM2. TIRISPEC, Professor Sao has already mentioned, it is right now at SCT since 2013, and first light was in 2014. A variety of science programs were done with TIRISPEC. So I just want to highlight is that TIRISPEC will now go as a major upgrade. Actually, this upgrade is due from last year, but unfortunately, pandemic has hit very badly. So we are basically replacing now Hawaii 1 PACE, which is the first generation teledyne array on TIRISPEC, which has some difficulty because of nonlinear and nonlinearity and other problems. Now we are going to one much more sophisticated array called Hawaii 1 array, and we have already procured, of course. So it is very difficult to procure such arrays nowadays because of ITER restrictions. However, we have got in last year, and now it is, and basically all this upgradation will make TIRISPEC as a new instrument, because we are going with additional camera electronics and also faster readout. Right now we are using 4 channels to 16 channels, so readout will be 4 times faster with this array, and hopefully this year or later this year, I think we will be able to go to Hanley to upgrade this, so that this becomes basically a new camera for SCT. And I will just highlight some important result about TIRISPEC, which is really the most important instrument right now, which is TIFR near infrared spectrometer developed by TIFR and MKIR. So this is basically gives a wavelength coverage from 0.55 to 2.5 micron, basically from optical to infrared. So simultaneously in the same night, you can observe in optical and infrared. And spectral resolution expected was 2750, but we have now got much better results from our commissioning nights, and it is in cross disperse mode. So there are 2 modes. So if you want to go deeper with low resolution, one can use the prism mode, but cross disperse mode is the quite important mode in TIRISPEC. And one of the challenge in TIRISPEC was, of course, to get the simultaneous coverage on optical in a 2K by 2 array. So one has to pack different orders in one detector array, which is just 2000 by 2000 pixels, and this was actually achieved by a very smart GMAX designing. So you can see in the right panel, this is the GMAX simulations, dispersion maps, and one can see almost like 10 orders here, order 12 to 3 from optical to infrared, and this has been achieved during our first light. This is a lamp spectra where one can see all the orders. And so initially when we designed TIRISPEC, our expected range was 0.55 to 2.54 micron, but we can actually go 0.4 micron now, because this is the capability of array. So this has been demonstrated by LAMP. Of course, we have to see with the star spectra. But so far, star spectra, we have actually demonstrated that one can actually achieve simultaneously 0.55 to 2.5 micron wavelength. So this is just some examples. Right now, this is a sample of spectra just to show here, like blue regions. These kind of stars are very important, like Wolf-Rayet stars or early type of stars. And then you go to the longer wavelength, like you have a late type star. So one can see all kinds of lines here, molecular CO vibration bands to atomic lines to the ionized lines. And this just shows the resolution which we have achieved during the commissioning night. So as you can see that mean resolution is 2800, more than what we are expecting, but one can actually sometime achieve 3000. And now we have actually characterized it also, and we know what is the sensitivity. For example, in J band signal to noise ratio of 10, you can achieve only in 10 to 15 minutes. So this has been improved further. So this is the older results. And also interesting programs can be taken by this kind of instrument, because it gives you simultaneous coverage. So for example, this is one of the important program where we are characterizing the Kepler red giants so that you can actually study well the host properties of the exoplanet host stars. So for example, one can see molecular lines from these red giants, as well as atomic lines and other recombination lines of hydrogen with a good resolution. You can resolve these lines, and then you can better characterize the properties, spectral properties of the host stars which are hosting the exoplanet. So This was the expected sensitivity. So we have achieved almost up to this level, like 20 magnitude in J, in 10 sigma in 10 minutes, and spectroscopy like 14 magnitude in K band. So this is just one example of very deep imaging from TenSpec. TenSpec has both imager and spectrometer, so it's a 2-in-1 spectrographs. So we are using 2 arrays. So this is the imager, which is very deep here, and so this is the observed sensitivity, like 21.5 in J, quite deep. And so advantage is that because simultaneously you can observe in optical and infrared, so one can actually also do the optical photometry. So these are the rough sensitivity right now. We have to characterize is better, like 23 in arm band and 22.5 in this. So this is my final slide. So in future, of course, our balloon program is going in a upgradation phase. So right now we can actually do the kinematics of PDRs with a velocity resolution of 170 km per second, because we have a resolution of 1800, but now we have upgraded this spectrometer to very high resolution, 10,000, and also with a larger array, like 5x5 array. Right now we are using only single channel in Fabry spectrometer. So actually with this kind of thing, now we can actually study the gas properties and dynamics of the C2 from PDRs. So we are planning our first flight sometime later this year or early next year. And also we have another satellite after ISIS. We have actually proposed a concept design of IFU spectral satellite when we have an announcement opportunity from ISRO in 2018. And this is for basically for L2 orbit and concept design. And this was actually presented in ISRO subcommittee. And we are working on that right now based on the input received from ISRO. And finally, now we want to move from single slit to multiple slits. So we are developing multi-objective infrared spectrometer based on configurable multiple slit. And it is actually in an advanced stage right now. Optics design and CSU both are actually completed. Thank you very
much. Thank you, Professor Roja. So we have slightly exceeded our time, allotted time. So there is no time for only one question. If any of you have any questions, please unmute yourself. Goku, please go ahead.
No, I didn't ask question. I just.
Oh, you're just clapping. Yeah. Thank you. So, if there are no questions, Professor Roja, may I ask you
one small question I have? Sir, in the balloon experiments, how do you make that the telescope is steadily pointing at the object, and how do you ensure a safe recovery of the telescope?
Yeah, so telescope is actually operated as the way we operate on the ground. So basically from the radio commands. So there are sensors in telescope. So like we have a guider as well as sensor like gyroscopes and so on. So basically through the radio command, we have a dedicated receiver and transmitter. So we actually give the command from the ground, the way it's basically satellite is pointed. So various sensors are used like star tracker, gyros, and so on. So based on that, we points and we operate the telescope. So there is a full control from the ground. And for recovery, we have other sensor like GPS and GSM devices nowadays. So we have better maps like ISRO's Bhuvan maps and Google Maps. We exactly know locations of the payload where it is going to fall. We know the trajectory of the balloon once it fall and so on. So all these are simulated and recovery is done safely based on all these information.
Okay, thank you, sir.
Thank you, Professor Roja. So I just have one small question. So you mentioned about gluing fiber to sensor. So this is for the space-based experiment, right? Have you tried to see? Yeah, have you tried to see whether they are space qualified? So did you vibrate it and see whether they survive?
Yeah. So basically, right now we have actually done that in our lab. So basically, in balloon facility also we have a vibration table. So these are space qualified because it has been one of the French experiment they wanted to use lever, which is the only company is developing, and this concept basically came from that only. So that's why they are developing it. But only thing is that right now these space qualified fibers are available only up to 2.5 micron. So that will downsize to that thing. And of course, we did a lot of these vibrations and other thing in the lab to check the rigidity of these fibers.
Okay. Thank you very much. And that's the end of the session. So let's thank all the 5 speakers, Dr. KK Singh, Dr. Chitnis, Professor BC Joshi, Shri Anand, and for Devendra Oja. Thank you all. So Shashi, over to you.
Yeah, thank you, Girish, and thank you, speakers of this afternoon session, to have this nice overviews and talks about various facilities, all the way from gamma ray to radio, and then what we can do and what we are doing with 8 to 10 meter class telescope like SALT, and then the infrared facilities all the way from ground to space. Now we have a session called joint discussion and poster viewing. So I request among participants to look at the posters, around 17 or 18 posters we have in the Slack channel. And those are based on, of course, largely by students, and they are based on the facilities like preliminary results from 3.6 meter dot and what students and registered participants are doing. And based on that, and even otherwise, we plan for a joint discussion about primarily that how, with the help of these existing Indian facilities, how in a more coordinated fashion we can have a larger impact. So that's the kind of broad question what we discussed yesterday as well, and today also. If participants are not too tired by now, it would be nice to extend our discussions a little more along this broad question what I just placed. So I think with these long sessions, people seems already very much tired. So anyway, among participants, I would request you all to just go through the posters leisurely and as per your convenience. And if somebody has some questions or discussions, it can always be continued through the Slack channel. And do anyone of you have any other points for today? Yeah, if not, then Girish, the chair of the last session, and participants, thank you all for your very good participation, discussion, presentations, and so on. And see you all tomorrow with the last day, and where we are planning to discuss about upcoming observation facilities and future plans. Thank you very much. Bye.